Are you ready? This is going to be amazing. Machine learning with Python, an awesome 15-lesson journey together. It's going to be amazing. We are going to explore k-nearest neighborhood classifier, linear classifier, support vector classifier. What is all that? Don't worry, we'll get there. We will explore linear regression, reinforcement learning, unsupervised learning, neural networks, or DNN, CNN. What is that? Don't worry, we will cover all that. PyTorch classifier, RNN or recurrent neural networks, natural language processing. Yeah, you need to master all these things. Text categorization, information retrieval, information extraction. You will learn all these things together with me on this journey. It's going to be amazing. So how does this work? Well, this course is structured in 15 lessons, this being the first one. In each lesson, we will explore some new concept together and then building up to a project where you try it first and then I try to solve it with you afterwards if you don't know how to solve it, right? So this is going to be 15 projects together. It's going to be amazing. So are you ready? I thought so. Let's get started. So you want to get started immediately? I like your style. Let's get to it. So in the description, there's a link to my GitHub repository and it looks something like this. You see here, there are a lot of files and these are the notebooks we're working with. So each lesson will have two notebooks, the lesson and the project that we're going to make together. And below here, how do you get started, right? So you download all the Jupyter notebooks by clicking on this link here and you see immediately, boom, it will start downloading. And in the meantime, while it's downloading, let's just ensure you have Anaconda installed with Jupyter Notebook. If you don't, you can get it from here and you just click here and you just download it here as well. Boom. And downloading starting. Okay, good. I have it already installed, so I don't need to. So just go to the file location here and check that you got your files from machine learning with Python here. You have all the files here again. So it's all clear and you click the first one here and then you're ready for the first lesson here. So let's start together and dive into this. It's gonna be amazing. See you in a moment. So here in our first lesson, we're gonna explore a bit what is the difference of machine learning and classical computing. Why is it so amazing and what is the power of it? And why is it so difficult to solve these problems in classical computing paradigms? And after that, we're gonna jump into our first model. It's the k-nearest neighborhoods classifier, which is actually conceptually really easy to understand, which surprises many people. They think machine learning is very complex to understand. And yeah, it's because people often confuse how you implement the models and how you use them, right? So is it difficult to do machine learning? No, not at all. It's actually quite easy because the concepts are easy to understand and then you can do the magic with the libraries. Many people get confused about that. So think about it like this, right? To drive a car, do you need to be a car mechanics? No, not really. You need maybe to understand there's an engine that makes all the car moving, but that's all. Inside the car, you just need the dashboard and that's all you need to use, right? To get from A to B. Machine learning is the same thing. You need somehow to understand what is it that the models do, and we'll cover that here. And when you understand what the models do and can help you with, it's actually quite easy to get that from A to B, right? So, are you ready? I hope so. Let's jump to Jupyter Notebook and get started. Here we are in our first Jupyter Notebook, the k-nearest neighborhood classifier. Okay, the goal of this lesson is understand the difference between classical computing and machine learning. To know that there are three main categories of machine learning, dive into supervised learning, classification with k-nearest neighborhood classifier, KNN, and how to classify data. What are the challenges with cleaning data and create a project with real data on a k-nearest neighborhood classifier. That sounds like a lot, right? So let's get started. First of all, let me just mention that you can skip ahead if you want. There are some chapters in the YouTube video below. So if you know what machine learning is and you don't want to cover that, well, skip ahead. Right now, let's get started with the machine learning part. So what is machine learning? Well, often it's easiest to understand something if you relate it to something you know already. So I don't know how familiar you are with what's called classical computing, but think of it like this. If you needed to explain a child to do something, right? You'll say, do this when this, and predict this when you see that, right? You want to say, if you want to explain your kid to go over the street, you say you will stop at the cross section. You have to look each direction. You need to make sure that there are no cars. If there are no cars or the cars stop for you, then you can walk across, right? And keep safe at all time, right? Don't run, don't do that. You have to explicitly tell the child every single move what to do. That's kind of like classical computing, right? So you tell each step to do and what to do for each single thing, right? Machine learning, on the other hand, well, you feed algorithms, right? So you just give them data, basically, and it's indirect computing, and it predicts based on this data. So you see, so there are different models, right? We'll cover them just below here in a moment. But in theory, it's just like you feed data, and maybe you tell them, when you see this data, this means this, and then it figures things out themselves. It's like learning by itself. Wow, right? So on a high level, machine learning is often divided into two phases. There's like a learning phase and a prediction phase. So in the learning phase, it's quite easy. It's often divided into sub-steps again, right? So you have the get data, pre-processing, train model, and test model. So the get data, it's like data collection, right? So it's like, okay, you need to explore something about the world economy. Where do you find information? Well, go to the internet. You have these 600 or 6,000 or 6 million web pages with information about it. So that's data collection, right? So now you have, let's say, 6 million web pages, which contains information about world economy. That can be articles, it can be data from the governments, it can be anything. It can be the largest companies that influence the world, and so on. A lot of data. Well, wait a minute. So if you have that, you need to kind of prepare the data. That is, clean, prepare, and manipulate sometimes. So you imagine, right? So you need to have the data in the same structure. It will be the same for you. If you're looking at financial data like balance sheets and all that kind of stuff, well, that will be one mindset. But if you're reading articles, that will be different. What is it you need to extract from these articles? Does it say it's good or bad? Or, I mean, it depends, right? And when you do want to train a model, the model needs to understand it. So it needs to be prepared in a similar fashion. Most models take data which are very similar. So that's what the pre-processing is about. Train the model, right? Well, there are three main categories here, right? They're explained down here. It's supervised, unsupervised, and reinforcement, just like it says here, right? Supervised is often the one you start with, and we will do that again here. Well, here you actually give the algorithm a lot of data, and you says, when you see this, this is this kind of output, right? So it can be classification like we're going to do, right? And it's going to be like, here you see a picture of an monkey, and here you see a picture of a car, here you see a picture of a bird, here you see a picture of an airplane, right? And you give a bunch of that. So you actually tag the pictures and say, this is the result you want. And then you feed a lot of input to the algorithm, and it figures out when it sees something new. Well, what is this? Well, you see this picture, then yeah, this is a monkey. So that's the training part. And then there's like the test, the model. Well, often you divide the input set in a training set and a test set, because you need some data which you already know what the result should be. It's just to test the complexity of it, right? So does it fulfill, does it predict well enough? So that's the magic, right? You make some kind of model, and then you test if the model is good enough. You need to test on some data that you know the results of, so you can see if it predicts correctly. Yeah, exciting, right? Because this is after that, just maybe mention that often here in the test model here, you'll just realize you're not satisfied. So you go back and train the model again, or you find out your data is not clean enough. It doesn't understand some of the data. You need to do something here, or you find more data sources. So this is process that goes on and go back and forth right here, right? You get more data, you figure out that you need to pre-process data more specifically, or you need to train the model in a different way, make a new model because it doesn't predict well enough, right? So this is what we are doing. I mean, this is the fun part, right? Because afterwards it's just prediction, right? So you get some input which should be similar to the input that you gave in the training phase, and then it will be making some predictions, right? It gets input and predict, right? You understand that? I think so. Good. Amazing. Next step here. So now we're going to talk a bit about supervised learning. What is supervised learning? Well, I told you already here, but let's dive a bit more into it. So said simply, in supervised learning, you are giving input-output pairs and learn a function to map input to outputs, right? So you give them, for instance, a bunch of images, like this is an airplane, this is a bird, this is another airplane. You give a bunch of those and say, these are, when you see a picture like this, you should predict it's an airplane. When you see a picture like this, you should predict this is a bird, right? Yeah? Okay. Then there are different tasks, but we start to focus on this classification, right? So it doesn't only have to be the task that I'm doing here, but this is classification. You say, when you see this, this is this classification. If you see this, then you see this one, right? And now we're going to start our first example. Are you excited? I hope so, because I am. I'm really excited about this. So we are going to predict if it's going to rain. And just be sure you know it. This is real data. So also, I'll also reveal to you, we're not going to predict 100% accurate. Did you ever have a weather forecast that was 100% accurate? I don't know where you're living, but I'm living in Denmark, and I would say in more than 50%, I would say almost 50% of the time, the weather forecast in Denmark is wrong. It's off. They predict rain. It doesn't rain. They predict no rain. It starts to rain. So it's a difficult task. Okay. Here we have some historical data, and in the first task here, we're going to limit it to only two metrics, right? So it's going to be the humidity and the pressure. So given the humidity of 93% and the pressure of 99.7, it was raining. The day after, it was raining. So this is predicting the day after, right? So this is the data here is current day, and the rain or no rain, it's the day afterwards, right? So this is the prediction. We say humidity, pressure today, does it rain tomorrow? Or no rain, right? So we have some data here. In this case, it was rain, rain, no rain, rain, right? I cannot say it. Okay. So our goal is to have a supervised learning as it has the labels, right? So we have the label here, rain, no rain. Said a bit differently, the task of supervised learning, right? Simply explained, I did that above there, but let's do it more mathematically. So if you're uncomfortable about all this writing I'm doing right now, don't worry so much about it. It's just some people, they prefer it in a mathematical way. So we have a function here, a function, and ideally we have a function. This function should ideally just take the humidity and pressure and predict, right? So if it takes the 93, 99.7, it should predict, as we see here, it should predict rain. And if we take the second row here, it should say no rain, and third row here, no rain, and so forth. That's ideal. But as you probably know, at least I haven't seen a weather forecast that was 100% accurate. We cannot make this function here. It's basically probably impossible. There are too many variables that you have to take into account, right? Maybe you heard about the butterfly effect, right? So, oh, that's a sidetrack. But the butterfly effect is that the wings of a butterfly in, I don't know, in Amazon can affect a hurricane in Antarctica or something like that. I don't remember exactly the locations, but that's a thing, right? So you see, the key thing is that small things can influence the results. So finding the 100% accurate function here is not something you should aim for. So what are we aiming for? We are aiming for approximating this function f, and we often denote it h. So let's start by visualizing that, okay? So this is always a good idea just to say, okay, we have two metrics here. So let's try to visualize the results. When we have two metrics and a classification, we can actually do that in a 2D plane, right? Which we can see. Often when you have more metrics, you cannot. So that's why we start with two. It's easy to visualize. So what's going to happen a lot along the course here is like there are going to be some programming nodes, and these programming nodes are easy for you to look up if you're not familiar with the things, right? So for instance, we're going to use pandas. If you don't know what pandas are, well, you can look it up here. So what is pandas? And you can look a bit yeah, get the book and buy the book and all that kind of stuff. I'm not related to them, so don't think of that. And then there's Matplotlib. And also some of the things which I find is more useful is like, okay, if you don't know Matplotlib and the way I like to use it, well, I have a lecture on visualization here. So you can click that and it will start immediately playing. And also we use a lot of CSV files. What is a CSV files? There's a lecture on it here. Simply said, a CSV file is simply just a comma separated file. So let's find the weather data here. Here we have it. And it can look a bit scary when you look at it here, right? So this is actually the data we are looking at. And it has a long row here of the column names. It has date, min temperature, and all that kind of stuff. And then have the data down here. And it can be confusing to see. If you don't know what it is, I advise you to go and look at that lecture and come back here. And then we're going to read the CSV. We're going to apply the read CSV from the pandas here. And again, there's a link to the page if you want to read a bit more about it. So these are the doc pages. I know in the beginning, if you're new to programming, it can be a bit confusing to see, wait a minute, what I'm supposed to look at and at these pages here, right? But basically, if you scroll down, there are examples. Okay, this one is quite a simple example, right? But basically, often the examples of what you need to know is written down here. So here, for instance, read PD, read CSV. That's all you need to know. And I must say, if you see this the first time and this is the first time you're programming, well, this is not the best example, but most of these documentation actually have quite good examples there. So I would advise you to read them. And then we're going to use list comprehension, and we're going to do that a lot in this course here. So I also advise you, if you're new to list comprehension and dictionary comprehension and set comprehension, I would advise you to go to this lecture. This lecture is structured exactly the same way that these lectures are done. So there's some information, and then you do a project, and then you can see how I would solve the project together with you. Okay, awesome. So when you see programming notes, well, it's for you to enjoy. If there's something new here, I would try to have links to everything we are using here. So if this is confusing, well, read about it, Google about it. I try to have links to everything you need to know. Perfect. So are you ready? I think so. Now we are getting to the coding part. This is the exciting stuff, I know. So what are we going to do? Well, we're going to import pandas as PD. So you probably notice it says PD.readCSV, right? And it's because when you import pandas, the standard is to do it as PD. So it means actually when you import pandas, it is as PD. You probably know that. I don't know. I don't know who we are, but now you know. Good. And now we are ready to read the data. Okay. So PD read CSV, and you see you can autocomplete here, and we know it's in files, and we know it was weather data, right? And you can autocomplete by tapping here. And let's just try to read it here. And what I like to do is just to take the head. It's often how you do it. So there are a couple of things here, right? So when you read data, one thing which is often happening is the date here is not parsed as a date. Actually, we're not going to use the date here, but sometimes it's just nice to parse the date. So often what I use is parse dates to be true. Another thing is, okay, so the date is actually the index column, right? So you can say index call, I think, yeah, 0, right? And how do I know all these things? Well, I auto tap. You can also get the doc string here, so you can see, okay, and like specifically with this read CSV, there's so many things here, so it can be a bit confusing. But most don't have that many things. But if you look at, for instance, here we found index call here, and it says an integer or string, so you can actually also set it as the column name, and or sequence of ints if they have multiple, right? And then you can set the index. So let's just try to do that. Okay, so now you see the difference here. The date is out here, and actually the date now is a date index. It should be, at least. Let's just try to see that actually. Data index. You see here date time index. So now it's a date time index, right? It looks like strings, but it is date time because it says date time here. Awesome. Perfect. I like it. Perfect. So let's get started. So what is it that we want to do now, right? We wanted to look at the columns that were defined up here. We're called humidity and pressure. We don't exactly have those, but we have humidity at 3 p.m. and we have pressure at 3 p.m., also 9 a.m. Okay, so let's actually take that. So how can you do that? You can say data set, for instance, and you assign that to data. And then you make what columns you want to pick here. And I'm really good at typing wrong. Okay, so let's just copy them. And we also need actually the prediction, right? Rain tomorrow, and it says yes, no. Okay, so that's our data set. So looking at our data set now, you see here, now it's way cleaner to look at, and I often advise, if you're not using data, just remove it, because it makes your life easier and you don't do confusing things, right? Good, so here we are. So let's try to visualize it, and I like to use matplotlib. Import matplotlib pyplot as PLT, and in Notebook you can have different modes. Matplotlib inline. I just take inline here. Often I also like to use it in the Notebook, because then you can have interactive, and the charts look actually more amazing actually. So, and please check out my lecture about how's it called, matplotlib visualization, because it's amazing. Because I like to use it like this, because many people use it directly on the data frames, but I like to make a subplots here, because the reason I do that is because often when you have multiple plots in the same notebook, it gets confusing, because sometimes it starts drawing on the one previously you made, and if you create a new subplots, it's never going to happen. So it's to take out a lot of confusing. Okay, so now we take the data set, right? And we want to map some of it, right? So what is it we want to map? Well, we want to take the data set and rain tomorrow. And if it's raining tomorrow or not, let's start with not, then we want to plot all that data. And actually we want to make a scatter plot. And what is it we want to have here? No, it's not it. Humidity. Can you autocomplete? No, you cannot autocomplete that. So let's just copy it here. So you take that column for X, and for Y, you take the pressure. And then we need to put a color. So when it's rain, what color should that be? Should it be blue? Blue? Blue. Blue it is. And then I like to put alpha here to be 25, because we do scatter plots, so we scatter all over, right? You'll see in a moment why. And then here's the trick. We put axis to axis. We assign the axis of this chart to be here, right? So I just show you here immediately. So these are all the days, or all the measurements where it didn't rain, okay? Perfect. And let's do the same for when it rains, right? So we say yes here instead. So I just copied the line here, and we take the humidity and pressure, right? Humidity and pressure, and then red for rain. Actually, this should be opposite, right? Rain is more bluish. It doesn't matter. Now it's done. Okay, so here we see it, right? So what do we see here? So what we see here is actually every time we had a measurement where it didn't rain the day after, we plotted it blue, and we plotted red if it did rain afterwards, right? So we actually see it's not totally random, right? You see more red points here, that means rain, and less red points over here. So actually you see an indicator, the more humidity, the more likely it was to rain the day afterwards. And the less humidity, the less likely. And there's probably also something with the pressure. It's difficult to see, but maybe it could be something like that, right? Okay, so now we will start. Now we explored the data. Now we will start with our first classifier. And this one is amazing. It's called the nearest neighbors classification, or classifier. Okay, given an input, choose the class of nearest data point. So in its basic form, let's assume this is our data now, only here, right? So we have some blue points, which was raining, and blue points was not raining, and red points were raining, right? So in this form here, in the nearest neighbor classification, if you get one new measurement right here, it will predict it based on what is nearest to it. In this case, it's a red one, so it will say it's going to rain tomorrow. So you might think, when you look at this picture, it's difficult to say, and there's no right or wrong here. You might say, well, it actually looks more that this is an outlier, that the red points are more likely over here. So how can you deal with that? Well, there's something called K nearest neighborhood classifier, and that's a K, right? So if in this case we take K for 3, so instead of only look at one closest one, you look at the 3 closest one, and then you take the majority of that. So in this case, we will actually predict it to be non-raining, right? The blue color was non-raining, so we will predict it to be blue instead of red. So you see, sometimes the nearest neighborhoods classification is not what you want. You want to take it over a few points. Okay, so that's what we're going to do, right? So the K nearest neighborhood classification, given an input, choose the most common class out of the K nearest data points, right? So this is actually what it does. This is the concept of K nearest classification. Isn't it easy? I told you it was easy, right? So you're wondering, how am I going to implement this? You're not. You're going to use a library. Now you know what it does, and I'm going to show you how to do that, and then we're going to do a project. This is scary? No, not at all. Right. It looks easy to understand. You don't need to implement anything here. That's the key thing. You just need to understand how it works. So a couple of things, or one of the main things when you do these things, people get so excited, right? So they just want to make, when you have a data set like this one, you want 100% accuracy, right? You want it to be perfect. You want to predict everything perfectly, right? You remember when I told you about, you often have a training set and a test set. So you train the model on a training set, and then you test it on your test set, right? And you get so obsessed with this process that suddenly I'm gonna fit it 100%. That's what I want. So that is the biggest problem in machine learning. And the thing people do immediately, right? You think the higher score, the better. The higher score, the better. But this is not the case. A model that fits too closely to a particular data set but fails to predict on future values, right? So you make this amazingly, let's say here the K nearest neighborhood classification, we make it amazingly fit everything. But what it doesn't do is actually predict future values, right? Again here, for instance, we say we fit everything perfectly, but let's say we use this model here, but it didn't predict new data. It didn't predict it. So what can you do? There are a few approaches, and something called regularization, and it's like penalizing hypotheses that are more complex and favor more simple ones. That's always good to have. When you create models, right now we really don't create a big model or anything, but later in the course, when you create models, often when they become too complex, maybe you can simplify it, and maybe you don't score as high, but simpler is better. And what we're going to use is holdout cross-validation, split data into training and testing sets. So I also have some links here if you want to read more about it. But this is the simplest way of doing it, and this is what we are going to do mainly in this course. Is like we have some training data and some testing sets, right? So you have the data set divided into a big training set and a bit smaller testing set to test, validate your things. But again here, this has the same danger. You can still be overfitting because you've overfit specifically to this training test set. So there's something also called K-fold cross-validation, and it's basically doing the same thing just K times with K different training testing sets, which you divide differently, right? So this way you minimize it. Okay, are you ready? And again here we have some programming notes. Most of the time I'll not go through it in details, but because this is the first lesson, I'll just say again here, we're going to use a NumPy. If you're not familiar with that, you can also see a lecture on that. And sklearn or scikit-learn is an amazing library. It's default installed on in Anaconda, Jupyter Notebook. So it's nothing you need to do. Also NumPy and Pandas are that. Then there's Dropna, which is an easy way to clean data. So we already talked about what do you do when you need to clean data. Well, you need to clean it, right? So the easiest thing you can do is just, if data is missing, as often you have measurements and some measurements were lacking, right? It didn't come in. You know how it is. You remember the long row of data we have up here, this one here, right? All this data here. Is there something actually here you see not a number. This means that there are missing values here, right? So that happens. You have enormous data sets, and that happens all the time. You're missing data. So what is the easiest thing you can do? Well, it's just to skip them. Skip rows which are missing data. Okay? Skip them. It's the easiest. Not the right way to do it always, but you know. And then we have this list comprehension again, right? You need to do that. And then there's train, test, split, yeah. This is where we divide the dataset into train, test, and split from sklearn. And then we have the k-neighborhoods classifier, the one we're going to use. And then to measure the accuracy, we're going to use this metrics accuracy score from sklearn. Good. Are you ready? I am. So let's get started. So as with anything, I think we should import something. Import NumPy, and you do that as np. And I actually think we should import some more from sklearn. Is that correct spelled? Model selection, import train test split, right? So how do I get this easy typed in here? I use auto completion with tab. I get this question all the time. How do you do that? How do you do that, right? So I think this is basically what we need. We also need the classifier. So from sklearn neighbors import, how it's called, k-neighbors classifier. And actually we need the metrics, sklearn metrics, import accuracy score, right? Good. Perfect. I think those are the things we're gonna need. Often it's a good idea just to import in the beginning. Let's have it here, right? So what is it we want? So often when you work with these things, you have like the data set in X and the labels in Y. So before that, we need also to remember we need to clean the data. So let's call it data set clean. Let's call it data set clean, and then take data set and call this Dropna. And I'll just put the length here of data set and length of data set clean. Why do I do that? I want to show you that actually you have like in the data set, the original data set, you have 3,337 rows, and you actually skipped 28 rows, right? You dropped those. So you dropped all the rows with that data. So now you have less rows of data. But for our purposes, it's like 28 rows. It's okay, I think. So don't worry about it. And now we need to make this X data set and this Y data set. So you ready for that? So X, what is that? Oh, I keep typing wrong here, this keyboard here. So it's the data set clean now, right? And we need square brackets, and you need to have this humidity. I'm annoyed it doesn't really autocomplete it, so let's copy here. Humidity. That's the X data set. And then the Y data set. Clean, it is rain tomorrow, right? So this is it, right? So now we actually have these things, but there's a catch, right? So let's look at Y here. So Y here is yes, yes, no, 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 and so on here. And we actually don't want that. And this is actually where we're going to use a transformation of it. And we're going to use, how's it called, list comprehension. And if you're not familiar with that, I advise you to look into that. And it's amazing. And you're going to see why now. So we're gonna make an array here, and inside the array we're gonna make this list comprehension. So what are we gonna do? We're gonna set 0 if value equals no, else we're gonna put it to 1 for value in y, right? So what do we have now? Did you see? That went fast, right? So we made a NumPy array now instead. And then we took for each, you have to read it from here, right? For value in y, that's for each of this one here. We actually say if the value, this value we assign, we take one item off the yes and no's that was there. If it's equal no, put it to 0, else we put it to 1. And there you have it. You have a NumPy array here. 1, 1, 1, 1, 0, 0, 0, and so on forth down there. Perfect. Are you ready? I think so. So let's continue our journey. Now we need to make the training set. So for that, we need to use this one here. So let's do that. Train x test y train y test equals train test split, and you take x, y. And what I like to do is actually put a random state here to something. And why do I do that? Well, we can actually read about it in here. Random state, you can see your random state here. And what does it do? I show you this because I want to make you familiar with this, right? Random state int, random state instance or none, default none, right? Controls the shuffling applied on the data before applying the split. Pass an int for reproducibility output across multiple function calls, right? Because if you run it once, you get some data set and some training and test splitting, and you made some results, and then later you want to reproduce it. Didn't work well, and you want to reproduce it, especially when you're debugging. It can be dependent on the random state. So in this case, when you have a specific random state, it will be a specific split between the train and test. So it will be the same each time I run it. So if I run it again here, let's see here. Can I do this? Actually, I don't know. No, I cannot. Because these are NumPy arrays, right? No, not NumPy arrays, were called ilog. So here we see it here. So if I run, the first one here is these measurements. And if I run it again, it's the same, right? I run again, it's the same. If I didn't have this one here, you see it changes from run to run, right? But if I have the random state here, random state 42, it's always the same. Okay, so it's to reproduce the same thing again. So I like to do that. Perfect. Awesome. Good. Now we have the test training set and the test set, and now we are ready to make our model, and it's going to be amazing. Okay, so let's call it an A. It's called KN classifier, and it's just use it by default. You can actually read what options you can set there. You can put neighbors, right? And this is maybe something to, so remember we had this 3 up there, so now we're going to use neighbors as 5. You can try something different, so you can put that as an argument here. I'm not going to do that here because I'm just going to use the default one here. And it was not supposed to call nay. It was supposed to call nay, and then we fit it. So all the models, most of the time is you create the model. In this case, we just create this pre-made model here, and then you fit it, and you fit it on the training data, right? X train, Y train, right? So you feed the algorithm with the training data. And after you do that, actually you want to make some predictions, right? You need to measure the model. How well did it perform, right? So you do an A, and then you predict here. And when you predict, you take the test data, right? So X test. So what this does is actually it makes the mapping from X test to Y pred. And we have the real results here in Y test, right? Okay. So what we can do here is actually accuracy score, and I forget the order. So it's a true with the predicted, right? So it's Y test with, sorry, Y spread. Good. So actually see here, this is actually, I'm actually surprised. But we'll just check one thing more here, right? So the prediction, the accuracy of the prediction is almost 81%. That's pretty good actually. And there's often a catch here, because sometimes some data is like, well, in maybe 81% of the time, it's actually sunny, no rain. So actually it predicts always no rain. I mean, we only have two categories, right? This is what a bit tricky about these easy models. We only have two categories, and only in 90% of the time it's raining, and all the other times it's not raining, right? So you need to be aware of these things. So you just look at, whoa, it's 81%. It's pretty good. So let's just calculate how often actually it is raining, right? So how can you do that? So let's say we have the real results in Y. Did we have them in Y? Yes, we have all the results in Y, right? So just here's an array, right? So what you can do is you can sum this array here. So you say actually that's how many times it was raining, right? One was raining, yes. And then you can divide that by the length of Y. So here you see actually 25%. You can also say sum equals to 0 if you want the opposite here. So it's 74% times it's raining. So that means it's not predicting just no rain all the time, because then the accuracy would be 74% here, as you see, right? You get that? So this is when it's not raining. If the model just said no rain all the time for all data, then it would have this then it would be 74% accuracy. But it has actually, so it does predict something. And what I also like to do is sometimes to visualize this. This is actually quite funny. So I'll show this. I mean, this is actually what you need to know in order to do the project. So if you're all excited and want to get started, go to the project. If you want, there's a link in the chapters down below there. But if you want, let's visualize our chart here. It's actually quite funny. So how do you do that, right? So let's call it XMap here. And XMap, what does it do? Well, let's take random 10,002. So what does that do? It does an enormous map here. So XMap. And you see here, it's an enormous map here of 2 coordinates like this, right? So what I want to do is actually I want to shift this map to be inside the range of our predictions. So how do I do that? I multiply this one, and now I don't remember the values, 150, and actually I add 0.990, right? So now actually these values here, all of them should be in the range of, actually I took the rand n here, it should be rand. It's not normalized, right? So here we have it. Now we have all the values are in the range. So this is in the range of humidity, and this is the range of the pressure. So let's actually try to map this. So fig axis, actually, PLT subplots, and then we do AX scatter. And we take x equals to x map, and actually we take all the first coordinates here, and then y to be x map all the second coordinates. Oh, oops. It should be square brackets :1, and yeah, let's start by that, right? So here we actually see all the mappings, and now you'll see why I always do alpha, because it makes it a bit more like this. So this is a map, right? So this is a map. So let's see how it predicted here, right? So actually we can do that by like a y map, and we do our model called naive predict, and then we predict our x map, right? And then we actually add a color here, color to be y map. Here we go. So actually now we actually see how the model predicts, right? So when the value is no rain, it's predicted over here. So this is how the model is, and it's rain over here, right? So if you look at this, actually comparing to the original data here, so this is actually quite okay. And this is based on the k, which is 5 nearest points here. And you see, so it's not predicting the same thing all the time, and this actually does a pretty well job. I would say that my weather prediction in my home time is less than 80% accurate for the rain, no rain. Actually, I didn't do research on that, but I think so. Okay, good. So a last thing you could actually do is so what value for k should I choose? And I'm not going to tell you exactly that in this one here. We're going to dive into that later. But let's look instead of, let's try different ones, right? So let's do that as a last exercise here. So 4k in range, should we take 1 to 100? I know that's a lot, but let's just do that. And actually we need to do all the same things here. So we just copy this in here, and actually take score here, and then we need to remember to add the n neighbors to be k here, and then we take the scores, append score, right? And let's run that, and you see it takes a bit longer when it's a star here. It's not, oh, it's pretty fast anyhow. And now it ran 100 difference, and let's see how well it does, right? So fig axis plt plots here, and then we take axis and we plot the scores, right? So what is it that I want to show you here is like, so if k was 1, it would be around 75%. That's actually close to probably predicting. No, it's probably not predicting exactly the same. And then here it goes up and up. You want it as high as possible. You see something strange here, right? So going from, what is this, 4.5 k at 4.5 here until 20 or 100 doesn't really make any difference, right? So you see you get most of it here, right? So again, simplicity counts. You don't gain having a classifier with the 100 nearest points. It's around, yeah, what do you think? This is 1, 2, 3, 4, 5-ish. I think this is 4, 5-ish, right? This is 5 down here, right? Because I think we were just below 80. So actually, if you took on the specific data, it would be 4 would be better and 6 would be better. And again, don't overfit. Again, this is specific on this testing data. Good. This was amazing. So the next thing that's going to happen is we're going to make a project. Are you ready? So let's get to the project. See you in a moment. So are you ready for the project, right? So we just did a lesson. Now we need to apply this knowledge on our own. So I'm going to introduce a project for you. And when that's done, you should try it yourself. And then afterwards, in this video, there'll be a explanation or a possible solution how you and I would do it together, right? So are you ready? So how do you find the project files? Well, it's next to the lesson, right? You find the lesson, the project. And here we go. So each project is made in steps. So you go through all the steps. That also makes it easy. If you have questions about something, you just, in step 3, I don't understand what's happening there, right? Okay, so what are we going to do? Of course, we are going to use something we just learned in the lesson. Otherwise, it wouldn't make sense, right? You learn something new, you want to apply it immediately in order to make it stick. So we're going to make a project on k nearest neighbors classifier. So we are, first you alone, going to create a k nearest neighborhood classifier supporting 3 dimensions. And then investigate whether it's going to perform better, right? So we only used 2. It was humidity and pressure. So we're going to try to add one more to the model and see if it does better. Okay? So just to help you a bit along here, I just import everything you need. Actually, the first step is just to execute this cell here. I can do that for you. Or no, you can do that yourself. Okay, so you just execute this cell here. Okay? And then the next step is we read the data, right? So we use this read CSV, and there's a link to it, right? And it's the link to where the files are. You should have downloaded them in exact same structure from the repository that I gave you. And then you can have the user parse states true and index calls 0 as I used in the lesson, right? That's the second step, right? So now we want to investigate the data types, right? And you could do that by using D types. And a bit confused? Well, go here to this link here and see how it does, right? So you just put on a data frame D types here. So as I talked about, the examples are pretty good, right? So you have the data frame df, the data frame. In this case, it's called data frame, and it's initialized by this one here. And you could just say dataframe.dtypes with no parentheses afterwards, and it will give you a list. Okay? Perfect. So why do we do that? Well, the goal is to identify all columns with data type float 64 for the next step, right? So some of the columns do not have type float 64. They have type object, most likely. And you don't want to use any of those in your next step. So choose the 3 columns to create the dataset, right? So we have humidity and pressure together with another column to predict rain tomorrow. So like we did in the lesson, here we make a bit additional step, is we create a list of the columns, right? So we have humidity, pressure, and then your choice here should be one with D type float 64. For instance, cloud 3 p.m. and then rain tomorrow. And create a dataset consisting of these 4 columns. Remember, we did that in the lesson too. Do that. And then in step 5 here, deal with the remaining missing data, right? But we just make a simple choice here. We just use drop now, like we drop, not a number, like we did in the lesson. Okay. And then in step 6, train and test the dataset, right? So define the dataset X to be the 3 columns you chose, and Y to be the rain tomorrow. And you can use a list comprehension. Remember we did that with no and yes. Nice. And then we divide it into train test with train test split. See how it's done in the lesson. You can use random state 642 or any other number if you want to be able to reproduce the results, right? And then we create the classifier. We create this, and default is 5. You can play around with that. And then you fit the model with this, and then you predict, and then you measure the accuracy. Okay? Are you ready? And if you really notice something in the lesson, actually we imported it accuracy score, and in this one here we actually imported metrics. So that's why you have to put metrics.accuracy in it. So don't get confused about that. It is correct. It says metrics.accuracy here. Okay? And optionally, this is if you really want to learn something, right? Explore. This is where the fun begins, right? So go back to step 4 and find with different columns. Try to do that. It's gonna be fun. I promise you. Okay? So what now? Press pause in a moment. Jump into your Jupyter Notebook. Try to solve as much as you can. If you get stuck somewhere and you say, this doesn't work, it doesn't compute, it doesn't look right, then go continue the video until this step here and see how I'm doing it. And then you try again. You try, and then you continue without looking, okay? And in the end, you just go through my way of solving, or how you and I solve it together, and see if you did it differently. If you do it differently, it doesn't mean it's wrong. I mean, it's just different choices, okay? So try it yourself. See you in a moment. Bye-bye. All right. Did you try it yourself? Oh, did you? Okay, amazing. So now let's see if we can do it together, right? You'll help me, right? Because sometimes I mess things up, and I'm pretty sure you're going to help me out here. Okay, so in the Jupyter Notebook, let's import the libraries. That was step 1. Let's try to do that. Shift, enter. We did it. Amazing. Then read the data. So read the data from files weather.csv. So data, I just call it data like that. PD, read CSV, and we take files and weather, and see it auto completes if you use that, and parse dates true, index call 0. Okay, execute, and then we can actually see data here. Head is always a good idea just to look at it and say, nah, that's really beautiful, right? Okay, perfect. Then investigate the data types, right? So use D types. Let's do that. Data, D types. And again, what is it we're looking for? As I told you, we're looking for columns with have floats. So how does it work in data frames, right? It rates that you only have one data type in an entire row, or column, I meant. So you can use any of these. You can say wind gust direction, it's an object, and wind direction probably is an object. So if you look at wind direction, okay, this one here, you can see that's the direction, it's not a number. You could probably convert them to some kind of values, like a sinus value or something, but we're not going to do that. We're going to keep it simple and find some columns which are float. For instance, cloud, 3 p.m. So let's go down here. So use humidity, pressure, PM, and another column to predict that. And let's see 3 columns names and with rain tomorrow, right? So let's do that actually. Columns here, and we take I'm lazy here. You see, copy paste is off. Oops, copy paste is a sin. No, I don't know what it is. And we could take cloud 3 p.m. I'm lazy here. Oops, I did something wrong here. That's what I said. You needed to help me. Oh, it's because it doesn't like that I'm copying here. It doesn't like I'm copying from it. I thought it went pretty well before, but now I'm pressing wrongly. So now we have the columns, right? And then we are going to make the data set from that data set to be data columns here, right? Okay, so this is basically it, right? So now we have data set head here, and looks beautiful, right? Perfect. And deal with missing data. Okay, so let's do that. Use a dropna, so if it has not a number, right? So let's say data set clean like we did in the other one, and we set that to data set dropna here, and let's just like the other one, data set, oh, we should take length of it, length data set comma length data set clean. Oops. Here we go. So you see here, actually we delete way more columns than the other one. So it seems like cloud 3 p.m. is not as clean as the other one. But it's okay. I still think 2700 is good enough for our purposes right now. Good. And define dataset X to be the dataset consisting of the 3 columns. So let's say data set clean to be columns, the first 3, right? So we put in the right order, and then we take Y equals to data set clean, and we take columns, and actually 3 here. And then we need to transform, right? Remember that. NP array here, and then we'd set, how was it we did it? It said 0 if value equals no. Was that it? Else 1 for value in Y. Wasn't that it? I think so. Perfect. And then we want to divide it. Oh, that's a long thing here. And we take the train test split, and we take X, Y, and random state 42. Perfect. So now we divide it into training and testing and training and testing. And yeah, you did that too. Awesome. And now for the fun part, train and test the model. So create a classifier with K and neighborhood. So I think in the lecture we called it nay, so let's do that as well here. And you can play around with any neighbors, but we're not going to do that. And then we fit the model, fit with X train, Y train, and then we want to predict some data, Y pred, to be nay predict for X test, and then we need to calculate the accuracy score, Y test, Y pred, right? So again here what we did, we create the model, we fit the model with the training data, and then we do the prediction on the test data, and then we take the predicted data and make the accuracy of the test data here. 81, amazing. In the lesson we had 80 something, right? So actually adding the cloud measurement at 3 p.m. actually adds some accuracy to it. But there's a catch, of course. We also know that the dataset is smaller here, so it might be other factors that actually pay into account. So you cannot make the conclusion that it makes more accurate like that. Okay, so I would highly advise you to try to play around with it, and it's a good idea to actually make these measurements here to see how much data you lack, because sometimes you get some tiny data sets and it fits magically by magic. And don't do those mistakes and become all excited and say, whoa, I matched it. So again, it's not the goal to get 100% down here. It's not the goal. It is the goal to make something amazing. Okay? So if you like this tutorial, please like and subscribe, and I will post more in the future. In the next lesson, that should be somewhere around here, you will be able to do a linear classifier. It's going to be amazing. It's quite similar, easy to understand, like the K nearest neighbors, but it has different strengths, and we're going to explore that one together in the next lecture. It's going to be amazing. I promise you that. See you in a moment. Linear classifier. In this 15-part machine learning with Python journey, we are in the second lecture, lecture 01, right? So in the last lesson, we learned about K nearest neighbors classifier, which we classified rain, no rain with. We're going to do the same in this one, but using the linear classifier. The linear classifier is just as simple to understand, but it does it differently. So, are you excited? I am. If you're new to this course, there's a link in the description where you can find all the material, all the notebooks I'm using. So, don't worry about it. Click on that link, find the material, and let's get started. Let's jump to Jupyter Notebook. So, here we have it, a linear classifier. The goal of this lesson is to learn about supervised learning. So, we already started that lesson, and explore how to use it for classification. We'll use a perceptron classifier and use it for linear classification in this lesson here. Supervised learning again. So given a dataset of input-output pairs, learn a function to map inputs to outputs. That is, for instance, with images, that's often easy to understand. If you have a bunch of images with planes and some with birds, given the naming of these, this is a bird, this is a plane, this is a plane, this is a bird, right? Can you predict, when it comes a new picture in there, can you predict with your model whether it's a bird or a plane? So that's what classification is about. And it doesn't only have to be two classes, but in the beginning, that's easier. Good. There are different tasks of linear supervised learning, but we will start off with classification. Supervised learning task. Yeah, so what is classification? As I told you, I already explained that. So example is this data set here we explored in the last one. And given humidity, pressure, does it rain tomorrow or doesn't it rain tomorrow, right? So we have some data points here, and it says here if it rains or doesn't rain tomorrow. The task of supervised learning, a bit more mathematically, it is you want to find a function that actually takes the humidity and pressure and predicts what's going to happen, right? So this is the ideal scenario that we have, that given 93, the humidity and the pressure, it should rain and no rain and no rain and so forth. We want to make a function like that. But as you know, the weather predictions, I don't know how they are in your country, but in my country, they are hopeless. This function, you will never find a function that can do that. But you want to find an approximation of this function, and we'll denote it often h. So the goal is not to find a function that is matching 100%, but something that approximates it and makes a pretty good prediction. So in the last one, we use k-nearest classifier. In this one, we will use a linear classifier. So how does it do it? Well, again, when we work with only 2 dimensions, we have the humidity and pressure. Well, it's quite easy to visualize it. But you should imagine this works on higher dimensions as well. But for the purpose of understanding what it does, this is enough. So basically, it draws a line in the sand, you could say, and say if you find something over here, we classify it as red, and on this side, blue. So if a new point comes along here, what would you classify it as? Yes, blue, obviously. So that's how easy it is. So the magic of the algorithm is to draw this line here. This line here is the magic. Okay? So a bit math behind it, and if you don't really understand all these things, don't worry about it. But basically it's addition and multiplication. So given the humidity as x1 and the pressure as x2, what you're trying to figure out is a function h, which takes x1 and x2, right? This function here that is an approximation of f here that takes x1, x2, the 2 parameters, and it wants to classify it and wants to find the, how's it called, the values v0, 1, 2 for these here, and then it makes a function of that. And a bit more mathematically, you can actually use something called the dot product of vectors. Don't worry about it if you don't understand it. Don't worry. If you want to read about it, there's a link here. And the dot product of x and v, the vectors here, is the same as the h function here. So as you see here, this is the h function. So perceptron classifier. And again here, it is a linear algorithm that can be applied to binary classification, which is what we are making, right? And in a link here, you can read more about it if you want. I think actually it has nice pictures here, right? Again here with the linear classification here, you can see something here. You can read about it if you want. There's another picture here. And all in all, it's about machine learning, and when we come later into the neural networks, you will see a lot of these drawings here. So this is one of the building blocks in many neural networks. So it is a big step here. So how does it work? Well, you need some learning, right? We talk about machine learning. So how does it learn, right? So given data points x and y, update each weight according to this formula here, right? And should you understand and do all these things? No, but maybe it's nice for you to understand what's happening. So giving a learning rate, alpha learning rate, well, you get the new data point and you take the old data point and you subtract it from each other, and then you add it to the weights. And so this is basically what it does, right? It takes the actual value, the estimated from there, it takes the difference, and then it updates according to that. And it iterates like that every time you get a new point, and then you find the formula of the weights of your model. Okay, and as I told you in the last lesson, there will be some programming notes, and you see this a bit longer list, this time here. But we have a list of libraries used. It's going to be Pandas, NumPy, Matplotlib, sklearn, or scikit-learn. And there's some lectures if you want to dive into it. And what are we going to do? We're going to use CSV files, read CSV, list comprehension. It's really a nice tool to know. And we're going to use isNull, sum, dropna, train test split, perceptron, and accuracy score. Okay, So what is it we want to do? Well, we want again to use the same libraries. So let's do that. Import pandas as pd, import numpy as np, import sk, maybe what are we going to import from that one? I don't know. sklearn. What are we going to import? We're going to import model selection. What are we going to import? It's going to be from. Apologies. From model selection, we're going to import train test split. And what else we're going to import? We're going to import from sklearn metrics, import accuracy score, and then we're going to do the perceptron model. From sklearn linear model, import perceptron, and then we're gonna import matplotlib pyplot as plt, and we're gonna put it in matplotlib inline mode. Perfect. That was a lot of libraries. Ha! We made it. Okay, perfect. So let's get the data in here. So pd read CSV, and we take the files. Oops. Weather. And remember, in the last one, what I like to do is parse dates true and index call 0. And then we can just say data head here, and just to investigate the data. It's always a good idea, right? So this is the first step. Now we have the data, just like in the last lesson here. And let's try to investigate it. So what is it we want to do now? Well, again here, we want the data set to be limited only to fewer columns. But one thing I want to show you also is like is, null, and sum, how they can do. So is null here, and you want to read about it, you can always click here and say detecting missing value, right? That's interesting. And sum returns the sum of the values. You can also read about that. And actually can sum numbers of true statements. So let's just do that actually. So data set, how's it called? Is null? It was not called is null. It should be. Oh, now I understand it. It was not called dataset yet. Data is null. So what you see here is a lot of false and true statements here. And what you're really interested in is actually to figure out how many of them are actually null, right? So if you look at the one we used, last one was humidity and pressure 3 p.m., right? So you see there's only 13 missing and 19 missing, while we also use cloud 3 p.m. Remember that one? It is missing 561, right? And here are some that are missing a lot, right? So again, so this is a good way to investigate data, which are missing something, which are not. And this will help you when you kind of when you want to figure out what data to use and what to do with data. It's a lot of data missing, but you can't see. You could also look at it visually down here and see, whoa, but you don't want to do that. Okay, perfect. So what you want to do now is actually you want to create the data set. And in this case, we are just going to take data and we're going to take the same ones as last time. And again, I'm really bad at, oh, we have them here, humidity, 3 p.m. And so the notebook doesn't want to autocomplete unless, how's it called? Unless you are having it in the single brackets, not double brackets like this. So rain tomorrow. Here we have it, right? So this is our data set, right? And so far, so good. That's our data set. So again here, actually we can just immediately drop now here, right? So you remember that. And the reason why I show you this sum here is because we're going to use it in a project. And remember, again, how did you do with x and so on? There's x and y set. We're going to do the same here. And are you a bit confused right now? We're doing the same again, but often the things we're doing is the same, but we're using a different model, and we're going to see how that's going to be performed. And often the conclusion is, well, this performs worse or better, but remember, these are building blocks we're going to use later in the course, right? Data set. And what we want to do is actually take the first two here. I should have done like we did in the project last time, add it to a column, so we didn't have to do that like this, right? Okay, and remember the y, how we need to transform it with this one. So 0 if value equals no, else 1 for value in y. So now we have the data, and then we take x train, x test, y train, y test, and then we say train test split, and we take x, y, and random state. Let's take 0 here. And why is it we take random state here? It's because that we want to be able to reproduce it. We explained that in the last video as well. If you don't put this here, you will get random sets every time, but now you get the same train and test set. And basically, when you do real processing and so on, you don't want to do that, but while you're building your things, you want to be able to reproduce things, because if you find a bug or something goes wrong, it's really, really nice to be able to reproduce the exact numbers, because sometimes bugs are coming on specific data, and if you can reproduce the exact same environment or context, then it's going to be difficult to find the bug. Perfect. So actually, this is all the preparation we did, right? So again, these are normal steps. You find the data here, right? Remember the process of machine learning: find data, check the data quality, do something with the quality, and prepare it. Okay, and now we have the model. So let's make the model here, perceptron. And again, this one takes a random state again, because there's some randomness in it, and I want to do that in this case in order also to be able to reproduce it, right? So some things do not really have random states, but in this case I want to do it train. I want to do it in order to be able to reproduce it if something goes wrong, right? And then we had to predict it, right? So what we did now, we created the model, we fitted the model, and now we need to use the model with predict, and we do it on x test. And remember what we then did, then we took the test and we took a measurement, right? Accuracy score. And again, here sometimes I forget the order, and then you just like shift tab and you get it down here. It's true and predicted. So y test, y predicted, right? And then we get it here, 77%. It's worse, but it's a different model. And does it mean it's a bad model? No, not at all. But let's actually try to explore it. And again, remember what we did in the other one? It was like, let's just check how much is actually rain and how much is not rain. Because sometimes what happens is that the model will just say no rain all the time, because maybe it's more likely no rain, right? So that is actually y0, that is no rain, and divide that by the length of y. Because then we see if the model only predicted no rain, it would be 74%, but it is 77%, so it is not just only rain. But what we can do is we can actually make a figure of this. So let's try to do that. PLT subplots to visualize it, and And let's just put all the data here. Yeah, so let's take all the data here. I don't know if this is the best way to do it actually. No, now we did it. Okay, so y all, and we had the model predict x data, and then we do the axis scatter x. We should call it all instead of data here. 0, comma y equals x data. 1, comma color y all, comma alpha 0.25. Okay, I'll just explain what I'm doing here. Okay, so what I'm doing is visually showing how all the data is predicted down here, right? So again, you have the figure here and the subplots, and you take the data, you convert it to NumPy. And actually, I got a bit confused if it's really necessary to make this conversion. I don't think so, but I use it down here as NumPy. So in that case, it is necessary, at least if you do it like this. And then I take all the data, and then I predict all the data. And you say, wait a minute, can you do that? Yeah, because I want to color. Want to get the color, how it predicts. And what I want you to see here, it has a straight line here with the data. And that's how you can see how it is colored. Okay, so if you wanted to see actually the real data, so let's actually do that here. The real data is like this down here, right? This is how the real data should look like down here. So you see it's more scattered around here, but the linear classifier says we are gonna draw a line, and this is what it took as the optimal line here. In this case here, it was here on this training data, right? And you would say, okay, that might be true. So it's not like a straight line. It is a straight line. That's not what I meant. I mean, it's not totally 100% vertical. It is a bit inclined a little bit. But yeah, you see, there's a lot of data over here also, but it is impossible to make it. And yeah, that's amazing. Good. So the next thing we're going to do is actually, remember the last project, we actually tried to do a k-nearest model, k-nearest classifier on 3 columns. Now we're going to take way more columns and try to use a linear classifier to see how that performs on more data. Because here we only have 2 again. If you have more, it will be more dimensions. It's just hard to visualize. And then we'll just look at how it performs. Does it do better than this baseline here on 74%? No, 77%. That was a baseline. Okay, are you excited? I hope so, because that's really the fun part, is to try to explore data, do something on your own. This is just demonstrating how you get started, right? So let's continue. See you in a moment. So this is a project, right? So if you're new to this again, I will introduce a project for you. Then after that, you should try it on your own, and then I will give you a possible solution where we do it together, right? So the project here is, let's look in the Jupyter Notebook. It is perceptron, right? So try a perceptron model with more dimensions, right? So what we did in the lesson was we only did it on 2 dimensions, right? Humidity and pressure. So in this one, we're going to do it with more dimensions, and not only 3, we're going to do a lot. So the first step is import the library. So I imported all of them for you to enjoy. Perfect. And then we need to read the data. So this is the file's weather. And if you're a bit confused that we use the same data set again in this lesson here, or yeah, don't worry about it. This is the last time we're going to use the weather data, but it's just a good data set to start working with. And it's real data. I love to work on real data. And again here, you can use the parse states true and index called 0. It's actually not needed, but it's just a good idea to do it. Then we need to investigate the data. Remember in the lecture we had the ISNA and ISNULL. I actually think in the lecture we used ISNULL, but here we use ISNA, okay? It's okay. It's basically the same thing. And then we use a sum in order to see how many are not a number and how many are, sum that up. So we kind of get an idea of the missing data. And then we remove the dirty columns, right? So make a choice and remove columns with too many entries with not a number. Say, take all columns with more than 100 rows. Yeah, I think that should be opposite, right? So we want to skip all that have more than 100 rows, dirty rows, right? Also, you can remove rows and non-numeric values. Remember to keep rain tomorrow, right? There are some that are non-numeric. Remember, we did this thing with float, right? The D types, you can do that as well. And what you can do to remove rows is to use drop columns access 1. And if you're unfamiliar with that, I think in the documentation, you always see here, you go down here in documentation here, they make examples. So here you see they create a data frame here and then they drop B and C, and this is what you get afterwards. So it is examples. Then deal with remaining missing data. Make a simple choice. And what to do, right? We used dropna so many times, so let's do that again, unless you want to do something advanced. Good. Actually you can see here I added dropna here as well. It shouldn't be necessary because you did it up here. So define dataset X consists of all data except rain tomorrow. And then you have Y to be rain tomorrow. And divide X train and so on here with train test split. And you can use random state 52 in order to be able to reproduce it. Then train and test the model, right? Use perceptron, use it with random state 0 to be able to reproduce, and then fit the model with train, X train and Y train, then test it, predict it on X test, assign it to Y pred, and then you measure the accuracy of the score, and you can redo with different choices of columns, right? And then optional down here, you can plot it. And I like to visualize things. But it's sort of just to see, actually, this is actually a funny thing, because if you watched it in 2 dimensions, it was a straight line. But how does it do? How does it visualize with 2 columns if you have multiple? How does it look like? I'm actually curious, right? Because it's still a linear cut, but it's linear cut on multiple dimensions. You can only visualize with 2 dimensions, remember that. But how does it look like? Are you excited? I think you are. I am. I'm really excited. I'm gonna hurry down there. But just a moment. Before you hurry with me, try to do this project here on your own. Start from step 1, 2, 3, 4. If you get stuck, follow me along until you get unstuck, and then continue on your own again. And if you get stuck again, continue together with me again. So are you ready? I think so. Let's get started. Are you ready? Did you try it on your own? Please do so and get back here when you tried it on your own. Otherwise, let's dive into it. So this is our project, and I introduced that just a moment ago. So the first step was to import the libraries, just to execute this one. Can we do that? Wow, we did the first step together. I love it. Then read the data, and remember we have the PD read CSV, and we take files and take the weather data here, and then it advises to take parse dates true and index call to 0, and let's just assign this to something, right? Data and data head. And here we go, right? So now we have some data here. It looks beautiful. I love it. And let's continue to the next step. Investigate the data. Okay, so this is where it was a bit different from the lecture. I used ISNULL in the lecture, and here I use ISNA to take missing values, right? So it's basically, if values are null or missing, it is basically most of the time the same. Good. So how do you do that? So data isNA. What does that return, right? Return all this dirty thing here, false, 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 true, 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 right? And then you can use the sum here to sum it up here. And just to show you the difference, data is null sum. You can see here, this is the same values we're getting, right? I think so, they are identical. Okay, perfect. So what are we looking for here? We are looking for, well, we are looking for the columns with missing data. Good. So one choice we could do is just say those with too much missing data, these 4 here, let's delete them, let's drop them, and the rest we keep, right? And that's what is suggested down here. So let's try to do, make a choice, remove columns with too many entries with not a number, right? Say take all columns with more than, yeah, okay, so this is correctly explained. So take all the columns with that, right? So what do? We take data set equals to data and drop, and it takes columns here. And now we need to be able to take wind gust and wind speed and cloud and cloud 3 p.m. And what does it say here? You can also remove rows with non-numeric values. So what are these? Well, we can just add it here actually. Remember we did this data D types, and you can see which one are there. So wind direction, for instance, is also, it's non-numeric. Oh, I didn't copy it here. So let's, this one, wind gust here, that was the one we had. So wind direction here. And wind direction 3 p.m. And then we have rain today. It's not the one we want, so we can delete that one too. And then we should take axis 1. So axes are a bit confusing often with data frames, because they're just like as confusing as, how's it called, NumPy, because the axes are often what you think opposite. When you drop data on this axis is axis 1 and this axis is axis 0. So now we should only have beautiful numbers here, and we have rain tomorrow here, and we have all the data we want to keep. Perfect. So deal with remaining missing data. A simple choice is to simply remove rows with simple missing data. Use drop now. Okay, so let's do that. Data set equal data set drop now. Maybe we should call it clean here like we used to, so we can actually see the difference. So here we do it, and here we say length of data set comma. This is not required, I'm just doing it to explain why we're doing this. Data set clean, and you see here we lose a few rows here. It's not that bad actually. We still have 3,187 left from the original here, 3,337. Okay, so this is pretty good. If we remember in the last one project, I choose, maybe you did a wiser choice than I used cloud 3 p.m. and cloud 3 p.m. apparently is cloud 3 p.m. missing a lot of data, so you deleted a lot, right? So now we have the clean data set. So define data set. So create training and test data set. So defined data set X consisting of all data except rain tomorrow. So this is probably where I should show you a trick, because what are you going to do? Write it all? So if we'll take data set clean columns, what do we have here? We actually have all the column names here, and rain tomorrow is the last one, right? So actually if we do like this, -1, we actually get them all except the last one, right? This one is actually, the name of this one, risk millimeters. I think this is a good predictor. It's actually a prediction, right, in the data set. So let's just leave it there for now. Maybe we should remove that one, actually. That's a free choice afterwards. So this is actually how you can get all the column names, right? So let's actually try to say x equals to data set clean here, right? So now you have all that. And then we have y data set clean, and it is rain tomorrow. And we need to do this transformation, right? Remember this one, np array 0 if value equals no, else 1 for value in y, right? This is it. And then we need to train, split it, right? So let's do that. And we take x and y and random state 42. Again, we do that in order to be able to reproduce it if we get some errors, and we want to be able to reproduce our errors. Perfect. Train and test the model. Let's try to do that. Create a classifier with perceptron, clf perceptron, and it says to use a random state 0, right? You can use random state to reproduce. Then we do the fit, clf fit x train y train rain train rain train. That was fit the model with train and rain. It was x train and y rain. Now y train, y rain. Why does it rain? Yeah. And predict data on x test. So y pred equals clf predict x test and evaluate the accuracy. So let's do that. I think we took it as metrics here. Accuracy, it also says so. Y test, y pred. Wow, 80%, right? So actually you see here now we use more data points. It's 80.5, almost 81% accurate. That's pretty nice. It's better than my weather forecast. And we already know that if it only predicted, say, no rain, it would only be accurate at 74%. We tried that a couple of times. Plot the result. This is optional. You want to do that? Yeah, let's do that. So plot the results, right? So use matplotlib, pyplot, plt with subplots to create a figure axis. Let's do that. Figure axis plt subplots and predict the data points in x. Okay, y pred clf, that went well. clf wow, predict x. Make a scatter plot with data points in x with color the prediction made. You might use alpha to plot your arguments, right? So let's do that. X scatter, and then we put x as something. I don't really know the column names of this one here. You remember any of that? It doesn't matter. We'll take something. Comma 8 y equals x comma 10. It's just something. Color y pred, and then alpha 0.25. Okay, so here we have a mistake here because we have invalid keys. We need to transform x to a data frame, or we need to actually put the data frame's names here because it's a data frame. I was just confusing myself here, right? So let's do this humidity like we used to do, right? Humidity. I'll explain in a moment what I did wrong here. I mean, often when beginners program, they get all confused when they do something wrong. And it doesn't, don't worry about it. We all been there, done the same things. So I just confused that X was a NumPy array, but actually we didn't convert it. It's a data frame, right? Because here we don't convert this to a NumPy array. Y is a NumPy array here, all right? But X was kept as a data frame. So when you index data frames, you do it by column names here. So this makes it also a bit easier to show, right? So what I wanted to visualize here is actually, even though it's a linear separated, remember in the lesson, it was a clear line down here, but when you have multiple dimension, it actually becomes a bit scattered around here again, right? You see here, you have some predictions actually over here, now here, and here. It's because it's multi dimensions, and you can take different dimensions here to see how it works. Actually, I'm a bit interested in many things. Okay, I could continue. I can feel I wanted to do more here, but this is actually what you needed to do, and I hope you enjoyed it. If you have any questions, please let me know in the comments down below there. If you like this lesson here, please like and subscribe. This course is amazing, and in the next lecture, we're going to dive into how do you actually find the optimal line. Actually, putting a line might not be the best line you can put there. So this is where we come into something called support vector classification or support vector machines, and it will help us finding a better choice for a line and not just any line. So are you excited about that? Please remember, subscribe, like, and all that kind of stuff. Put some comments below there. I love to hear from you. So see you in the next lecture. Bye-bye. Okay, support vector machines. This is the journey of machine learning with Python, a 15-lesson course with you and I joining our forces to learn about machine learning with Python. So in this lesson here, we're gonna learn something about support vector machines. So we learned about so far some classification techniques like the k-nearest neighborhood and the linear classifier, but there was like a dilemma that we're gonna look at now, that how do you optimize the linear separator? So we're gonna look into that in this lecture. If you are new to this course, then look in the description down there. There is a link and you can download all the material, the Jupyter notebooks and everything down from the link there. Good, so let's jump to Jupyter Notebook and let's get started. So, support vector machines. So the goal of this lesson here is to learn about the problem of separation, to also explore the idea of maximize the distance, and to work with examples to demonstrate the issue, okay? And in the project, we're gonna do the same, but on some different data sets that we're working on here, okay? Good. Are you ready? Good. So the maximum margin separator, so boundary that maximizes the distance between any of the data points. And there's a link to Wikipedia here if you want to read more about it. We're not gonna read that together here, it's for you to enjoy alone. But let's demonstrate the problem. So imagine you have a data set of red points and a classification of blue points. So they are classified like this. This is a nice and easy data set, so it separates really well. So one potential line would be like this horizontally, and it classifies everything here, right? So on the training data set we have here, it looks fine. But imagine a new data point comes along here, and according to this line here, it should actually be red. But our intuition would also maybe say this is more likely to be blue because it's around the blue area here. So this line we used here on the training data set didn't really work well on predicting the future. But using the techniques we learned so far, we could end up with a line like this one on our training set, right? So what is a maximum margin separator? Well, it tries to draw a line that maximizes all the distances to the points. It has some mathematical engineering to do that. So when it comes to point here, actually you don't really realize it, but then the same point here came here actually, it would be on the right side of the line here. So these are obviously easy data sets to work with, so it looks beautiful, and it is when you visualize it like this. But on real data, it's often a bit more complex. Good. So support vector machines. Well, sklearn has this kind of thing here, and you can actually look at the docs here. Again, we're not going to do that together, but you just see here the support vector classification. The implementation is based on libsvm and so forth. I'm not going to read this. And we will use a linear kernel here, and there are many kernels you can use. They're like polynomial, RBF, sigmoid, and so forth. And if you don't know what a kernel is, I would understand that. It's a mathematical thing here. You can also read about that. I would not advise you, but if you are really interested into mathematics, what is a kernel? Well, read about it here, and it's used in machine learning. Do you need to understand what it is? I would say no, but you need to understand that you can change the kernels and it will change the behavior of your model. Okay, so programming nodes here, and as I said, they're often kind of the same thing here. We have pandas, numpy, matplotlib, sklearn, and you have some lectures there if you want to explore it a bit deeper. And we're going to use CSV, read CSV, lambda. This is new, right? You know what lambda functions are? Well, lambda functions are nameless functions. And if you don't know about them, I highly advise you to explore a bit. This is really not the best documentation on it, but you kind of get the idea of what it is. And you will below in our examples, because we're going to use it. And then list comprehension and apply. Apply is also new here. We're going to use it with the lambda function, actually. So you apply a function, a lambda function on it, on the data. So it's going to be exciting. New stuff. We love new stuff. Okay, so let's get started. So I import the libraries we need here, the NumPy, Pandas, sklearn, and Matplotlib. Okay, perfect. So let's start with our data. So in this case here, we're gonna read the CSV, and the files we're looking for here is called gender. Good. And let's just start by exploring this data here, what it is. So what do we have here? So we have some measurements of height and hair length. And just not to confuse you, these are in centimeters. So if you are in a country where you don't use centimeters, well, it's not like inches or anything, it's centimeters. So this is not extreme. These are normal measurements. So what we want to do is from hair length and height, try to predict the gender. And I know that maybe this is politically incorrect. So in these days of all these gender things, but let's just leave it at that. It's F and M, and there can be multiple more genders, but let's just keep it simple here. Okay, so perfect. So what we want to do first is just to get an idea, how does this data set look like? And this is where I want to transform the genders into a color instead to visualize it. So let's try to do that. The data, and we can just call it class, because it's a classification, right? And then we take data, and what is it we take? We take gender, and then we apply. And what is it we want to apply here? We apply a function on it. And you see the signature here. It is apply a function along the axis of the data frame, right? So let's try to do that. And here we use a lambda function, lambda x, and we say that we put red if x equals what? F, else blue. I just put n here. It should be blue. And let's look at data here now. So we added, so F becomes R and M becomes B. And let's leave it at that. And let's try to make a plot of that. So figure, to get an idea of the data, figure axis, PLT sub plots, and then we take axis scatter, and we scatter Actually, we do it differently in this one here. No, let's do it scattered like this. And then we take X here and we take data. We could do it differently here, but now I started here. Height on X. Is it height on X? Yeah, let's do that. And Y, we take data hair length. And then we take color to be data class. Isn't it bounded? So here we see it, right? So actually, just to minimize the data, we should maybe just limit our data a tiny bit here, shouldn't we? I think so. So yeah, I think so. I think we should just limit our data here. Data equals data ilog 25, because there's too much data here. There's too much noise, right? So let's see here, right? So what is it I want to demonstrate here is like these points are separated really, really nice and easy, right? At least now when we limit it to 25 first. There was a bit overlap down there, but let's just ignore that. So what could happen is if we wanted to use a separator from the last lecture, what could happen if it could look something like this, right? As already said here, right? So around 20 here, it could be a horizontal line. Just here would be a vertical line, and here it says horizontal line, and it separates them all, right? But we already know that if we added more data on this here, right, there will be some data points down here and so on. So this is our training data set, a simple training data set. So the separation line could be like that, but it could also be differently. So let's I just plotted some here. Let's do that. I just make an array from 150 to 190, I think. And then we make a plot here, x minus 145, and we put color yellow here. I just add a potential different line here. You could separate it like this, or I'm just demonstrating that it could be very different. And also it could be something like this here. I don't know where we're going here, but yeah, okay, so you see here it has another separation line. So this is just to demonstrate for you that depending on the algorithm, which line is correct. I mean, all these lines are separating, but which one is better? And this is where we're going to use our new model here, the support vector machine here, and try to separate it and try to ask it for advice. And it does that by all this awesome mathematics that we're not going to dive into, but it's just to say that, demonstrate here that this line is not obvious how it should be. We already have our data set here, so let's try to define x here to be data. I call it data, right? Yeah, data. And what we take here is height, and we take hair length, and then we take y equals data gender, and then we transform that, and p array. You remember this now, and it's like 0 if gender equals m, else 1 for gender in y, right? I think that does the work. Perfect. Good. And now we're not gonna do this test train thing, because now that's not what we want to demonstrate in this lecture. What we want to demonstrate is how it will choose a separation line. So let's try to do that. So CLF, SVM, SVC for the classification. And here, as I told you, there are different kernels you can use here. And the default one is RBF, and we're going to take the linear kernel as linear. And then we are going to fit on all the data. Yep. We're going to fit it on the data here, right? Because this is, we already put it down to only to be a subset of the data here. So perfect, let's do that. So now we have like this kernel linear here, which is fitted actually. So what to do with it? Let's try to do some prediction. So what I like to do something is visualize, and then this is just the way I find random rand, and we take 10,000.2, and then we take s test, we shift it a bit so it fits into our frame here. It's 50 upwards, right? And 120, no, 50 along the axis and 120 there. And then we shift this one 150 by 0 because it starts by 0, right? And what we're gonna do is gonna predict. So CLF predict. We're gonna predict X test, and then we're gonna visualize it. Fig axis, PLT subplots, and then we're gonna scatter X test, Y X test, and color Y pred. And here you actually have, oh, I'm kind of surprised, right? So the line is pretty low down here. Let's actually make the alpha value. I like that. Alpha 0.25. Okay, so here we see that actually the line is pretty low here. I actually would expect that a line of the separation of these points would be a bit more along the line of this one here, separating maximally. But apparently it makes some calculations, and based on those calculations it makes the decision. So this is actually, let's just try for the fun of it to add the points. Scatter. So the points were, I put it in data here, height, y equals x dot hair length, and then we have the color to be, what is the color? The color is y. Can we do that? Yeah, because those are numbers. Okay, so let's add those, and that went well. Actually, we need to transform the colors maybe. Y color, red if value equals 0, else blue for value in y color. Okay, this is because it uses the same colors here, right? So now actually I'm going to change. So this is actually how the points are lying here in our data set here. And you see actually, I would actually expect it to be more like this would separate it more. But apparently that's not the case. And I'm kind of surprised actually. Are you surprised? Well, this is sometimes how things surprise, but apparently it says that this is the best line to separate the maximum between the values, and that must be the case. I rest my case and accept it. It's like that. So see what we did here, right? We took and read some data, and we put it on hair length here and gender, and we minimized the data. It's an enormously tiny data set of 25 points that we add here with different hair lengths, and so it separates really well. Because it was a bit bigger, you saw it actually scattering all around. And then we actually did the prediction, and then we actually look at how it would predict data. Perfect. So we're going to join to the project, and the project we're going to classify dogs, different dog species. This is going to be amazing. See you in a moment. Are you ready for this project? I surely am. So let's look at it and try to explain it. So right now, I'm just going to explain it to you, and in the next one, we are going to solve it together. So let's look at that. So, support vector classification, right? We want to classify dogs. And to make it simple, we only have 3 types of dogs, and it's going to be a Doberman, a German Shepherd, and Rottweiler. So these are all, as far as I know, German species of dogs. So it's my neighboring country. They're beautiful, all of them, and I love them all. So the first step here is to import the libraries, and you should just execute this one, and then you're ready to go. Then you read the data, and the data set is called data02. Okay, that's a great name. And I guess then we need to explore the data, and we'll do that down here. So down here, the model works with name classes, but often it's more convenient to use numbers for classes, right? So what I'm saying here, this transforming we do right below here is not necessary, but it's nice. So create a dictionary to map class names to integer numbers, right? So you make a class identifier, and you map Doberman to 0, German Shepherd to 1, Rottweiler to 2. And then you create a column with class IDs, and then you use apply and lambda like we did here, like this here. We did something similar, right? Just this is a bit simpler actually, because we use this class IDs. Perfect. Then scatterplot the data, right? So explore it a bit, right? Create a fig axis from matplotlib pyplot. Make a scatterplot using class ID column as color, right? So this is also right. Now we made this transformation here. Now you can actually visualize it with colors. You wouldn't be able to do that if you use the names. I don't think matplotlib is that smart. And dogs use weight and height for dogs use weight and height for X and Y, respectively. Good. Fit the model. Use the SVC model from the with kernel linear and fit the model. Map out the classification, right? So hint, now create a random selection of data, like I did in the class, right? You use this random rand and shift the data according to this, like I do. Predict the random selection data, create a plot with the data with prediction. And then you can actually make optional, you can add a map with this map we made up here with the original data points, right? So make the same plot, add the data points from the original data set. You might need to make a color mapping, say colors blue, red, green, and use the class ID column with apply. Perfect. So let's try to do that. I mean, you try to do that before we do it together. Okay, are you ready? I think so. So see you in a moment, or as long as it takes for you to make this. Okay, see you. Bye-bye. Are you ready? Did you try it? Was something difficult? Let me know in the comments down below, and let's try to do it together, right? So, classification, 3 dogs types. First step, did you succeed with this one? If not, then it's like shift enter on, you need to highlight this one and shift enter. Then executes and it imports all the libraries you need. Perfect. Then read the data. Use pandas read CSV. So data equals to PD read CSV, and we have files and data. Is it the only one? Yeah, I think so. Perfect. And then we can actually take data head just to inspect the data. So you see here you have the weight and the height, and then you have the class. So the reason for this dataset of these dogs is, as you will see later, it's easy to classify them based on the height and weight. Perfect. So make class IDs, right? And again, we know it's not necessary, but it's really nice. So what we're gonna do is copy this one here and have the mapping, and then create a class, a column class ID, right? So data, class ID, capital ID, it has to be, it says so, so we do it, data, and what is it? What was it called? Class. It was actually called class, and apply to lambda. Oh, lambda x. Oh, it goes really well. Class IDs and x, right? So just an explanation of this one here, right? So lambda is applied on each row of the data. It takes class here. And for each class, it will take, if it's Doberman, then it will add Doberman and map it to 0, right? That's how it does it, right? So let's do that. And then we take data, head here. And now we see we have mapped these here. So let's just ensure that Rottweiler was 2 and German Shepherd was 1 and Doberman was 0. So this works beautifully. Scatter plot the data. Create a figure and axis from matplotlib pyplotlit matplotlib pyplotlit. I cannot say that. Matplotlib pyplot. There we go. SPLT. PLT subplots. Perfect. And then we want to scatter. AX scatter. We can do this in different ways. I mean, now let's do it like this. It's fine. Scatter x equals to data. And what was it called? It was called weight. And y equals data. Height. And now we need the color, right? And we need to use that as data class ID, right? That should be it. Perfect. Okay, so what we want to see here is this data is actually quite easy to classify. It's not 100%, but you see there's some overlap here. But other than that, actually, you would be able to basically draw a line here and draw a line here, right? How do you do that? Isn't it like this line here and a line here, approximately, right? Approximately, I don't know. I'm not very good at this. Perfect. So that's basically why we want this data. And you might wonder why it's all in lines here. It's because it is discrete numbers, right? So it's probably, we have the weight along this axis and the height is in. Okay, so the weight is on this axis and it's a comma separate, it's comma digit, and the height is in integers, so it is jumping like that. So that's why it looks like, it looks a bit different. It looks a bit funny, right? But that's, so it's not all like the other charts we had. It's not that much mixed together. Perfect. So that was it. And now we want to fit the model. Use the SVC model with kernel linear to fit the model. Do we know how to do that? Let's just call it model here. CVC kernel and linear. And then we take model, fit. And how's our data now? Did we didn't even divide the data yet. Ooh, can we do that? Is that legal? Is this legal? I don't know. Data. I think we should have added the step where we divide the data. But so far so good. We'll just do it a bit dirtier. And I'm happy you can forgive me for that. And height. So this is X usually, right? And then we take the Y here, it's data. It was capital, right? Class ID. So we fit the model here, right? So use the SVC model on kernel linear and fit the model, right? So normally you would have a step where you actually assign this to X and assign this to Y. But you can also do it directly here. It's okay. Can you forgive me for not making that step? No? Okay. Perfect. So map out the classification, right? So now we want to see how did this model do? Did it do like I predict up here, something with a line like around here and one line around here? Did it do that? I don't know. Let's see. So create a random selection of data. So X test. And we assign that to this one here. And then we move the data, X test. You can call it whatever. You don't have to call it X test like I do. Test. And then we multiply by this and shift it like that. And then we need to predict Y pred. And we do the model, predict X test. Okay? And create a plot. And let's just do that here. And then we create a plot here. Fig axis, PLT subplots, axis scatter, X test colon comma 0 first, Y equals X test colon comma 1 and color Y pred. And we can do the alpha. I actually think it looks nicer. Alpha 0.25. Okay, so here we have it. Actually, it's kind of funny to see actually it squeezes this one down below here. But other than that, it is pretty close. I don't know. So we should do the optional down here to add the data points from here. Let's try to do that. So make the same plot. Make the same plot. That's this. Make the same plot. And add the point from the original data set. So you can make a mapping here with this one here, for instance. Boom. Colors. And then you make X scatter. X and you say, how was it? Data. What was it? Weight, height? I don't remember. Height. Y equals data. Weight. Color equals. And this is where we need to with apply, right? So we could have done it data. We just do it in one run here. You can do it in multiple steps here, so don't worry. Class ID with apply lambda X colors X. Huh? Okay, we did something wrong. And what did we do wrong here? We probably put them opposite. Perfect. So I put them opposite there, so you make this. Whoa, what happened there, right? So you see here, there are some it doesn't predict, but it's impossible to predict it with linear separators, right? But other than that, it's pretty right. A line here and a line here. Interesting. I like that. Perfect. So far, if you find this step here a bit confusing, I would take a look at what we did earlier on this one here. It's basically the same thing we do here. We just apply it directly, and you can do that. I often advise to have a step on the way, right? So you can actually take here, you can say colors, Y colors, and add it here, Y colors here, right? So here you have it. And you have a syntax error here because you need a parenthesis here and you need to delete this one here, right? Perfect. So you see how it makes the code a bit more readable, like this. It should be a bit more readable like this, right? So this is one way to do it, and I hope you enjoyed it. So this is amazing. So if you like this lecture here, so please let me know in the comments here, and please remember to subscribe and like this channel. In the next lesson, we will learn about a linear regression. So what is the difference on what we're doing now? Right now, we've only been doing with classification. This is class. This is Doberman. This is a Rottweiler. This is a German Shepherd. What we want to do is guess numbers. Real numbers, not discrete numbers, real numbers. We need to be able to predict that. So we're going to do that on house prices. So we have some data on houses. How can we predict the house price of them? We'll do that in the next one. It's going to be amazing, I promise you. So are you ready? I hope so. Let me know below how you're feeling about this stuff here. So see you in the next one. Linear regression. Wow, this is going to be amazing. This is actually different from all the classifiers we've been working with, because now we're not going to classify. Now we're going to predict something. Yeah, that's right. Our machine learning models are getting more and more advanced. Well, are you ready? This is the 15 lecture or 15 lesson course on machine learning with Python. If you're new to this, look in the description below. There is a link and you can download all the material, all the notebooks we are working with here, so you can follow along and try to work with me. Also, there's a project in the end that we are going to do together. So are you ready? Let's get started. Let's jump to Jupyter Notebook and figure out what this linear regression is. Come on. Okay, so linear regression, this is the subject of this lesson here. The goal is to learn about linear regression or linear classifier, understand difference from discrete classifier, and understand it is supervised learning task. Get insight into how similar linear classifier is to discrete classifier. Okay, so what does that all mean? Does that confuse you? Yeah, it does, so don't worry, we'll get there. And then get some hand-on experience with linear regression. So, first of all, what is linear regression? Well, it is supervised learning. Remember, supervised learning, that is really, you still tell the algorithm what is the result you want when you see this. When you see this, predict this, right? When you see this, predict this. So you give a lot of data where you say, when you see this, predict this. See this, predict this. And then in the future, you see this, it has to figure out what to predict. So a linear classifier, and surprisingly, it looks a lot like what we've been looking at before, but there's a difference, right? Because it's linear and not discrete. It is given by a formula like this one here, like it's also a dot product, as we can see down here, but basically it's some weights, weight 1, 0, 1, and 2. We can actually get these weights below from the algorithm. I'll show you if I remember, otherwise please poke me and I'll show you. And we have these elements here, x1 and x2, which are what it's trying to classify. So if you're more into math, right, and you know about dot products, you know that you can have two vectors, vector w and vector x, given by this, and then the dot product is the formula up there. So hw, you'd often say, of x, the input here, is given by the dot product. And if you want to read about it, don't know what it is, well, read about it here. Don't expect to become a master just by reading this Wikipedia page. But if you don't understand it, don't worry about it. It's not needed. So what I also want to say is, yeah, of course, what if you have more metrics you're measuring on? Well, in a general case, you can have as many as you want, as many weights, as many inputs as you want to this function here. Okay. That's it. So what does that mean? Well, we'll get there. We'll see it in a moment. Don't worry about it if it doesn't make sense. Good. Measure accuracy. So there's something different from classification and linear regression. Because linear, when it was classification, right, it was like right and wrong. Like, does it rain or doesn't it rain? Is this dog a Doberman? Is it a Rottweiler? Is it a German Shepherd? It's right and wrong somehow, right? So when you classify, it's easy to say how many right did I get and how many wrong did I get, right? Right. And now we measure discrete values. That means we measure something. We say, in this one, we're going to work with house prices. So if we guess the house price or the unit house price is 100 and the real result is 101, is that wrong then? No, it's not really. It's really close. Instead of, if we guessed it to be 200, that would be worse, right? So we use something called R squared or R squared. That was difficult to say. And you want to read about this coefficient of determination, also called R square or pronounced R squared. It's basically when you have some kind of prediction along this line here, you have all the real values. What you measure is actually how much wrong did you guess, right? But not in a discrete manner. So the numbers you get out here is not to compared with the percentage of correctness in the accuracy you measured in the previous ones where you had classifiers. Okay, perfect. So a bit about programming, right? So we use pandas, numpy, matplotlib, sklearn or scikit-learn, and we have some lectures here if you want to dive in and learn a bit more about it. We use CSV files again, read CSV file, isNull, sum, correlation. This is a new one here, right? So let's try to click on that. What does it do? It computes pairwise correlation of columns excluding NA null values. Okay, what does that mean? Basically, it's a measure of how much data correlates. And we like data that correlates a lot, right? It means when something happens with this value, if it correlates a lot with another value, something happens there too, right? So they kind of go in sync somehow, you could say. And the less they correlate, they can also correlate opposite. But if it goes like crazy and this one moves and this maybe moves, maybe not, and you cannot predict anything from it, it doesn't correlate, okay? So correlation is, it goes in system and can also be this kind. But if it doesn't correlate, you cannot predict anything from this move, you don't know anything. So correlation is good. And then we have the train test split, and then we have the model we're going to use, the linear regression model here, and then we have the R square score to get the accuracy, right? Good. Are you ready? I hope so. Let's get started. So, as I promised you, we're going to import all the libraries, and then we're going to look at some data. And let's take the data, PD, read CSV. And what is the data called today? I have to look it up, files, and call something with house prices. There you go. And now let's just hit the data here and see how it looks like. So yeah, we have some transactions, we have house age, we have distance to station, and number of convenience stores, latitude, longitude, house unit price. So this is what we want to predict, right? We want to predict based on some of this data over here. We want to predict house unit price. So there's one thing that's interesting here, right? We have latitude and longitude. So I want to explore a bit here before we dive into it, and just to say, well, sometimes some data doesn't make sense, but it makes sense, but it doesn't make sense. So let's look at this one here. So this is a specific data set of house unit prices, right? So let's try to explore this one. Figure axis. So I'm going to make a plot now. PLT subplots and axis scatter x. What do we put on the x-axis? We put data. We put longitude, and then we put y. We put what is we want to predict. We want to predict the how's it called house unit price. And actually, we don't want to do anything else than that. What is it I want to show you here? Well, if you look at this, it's kind of, if you really want to see it, it looks like prices is correlated with the longitude, right? That means it looks like the longer you go in this direction here, the higher the price it looks like. You see that? over here. And that's often what happens, right? So this data is not full data set of the entire world. It's a data set, I think around, isn't it San Francisco or something? I don't know. It doesn't matter. But there are often areas where prices are higher, so you can get some kind of correlation, which is something that really doesn't make sense. It's not like if you went further this way, it's not like the prices would be up here, and if you went further, it would be up here, right? And if you went further this way here, you would have negative prices almost, right? It's not like that, but isolated, these prices seems to be correlated in this direction here. Really? Well, let's actually just explore that immediately. So let's say data core, that was the one I wanted to explore with you, and we can look at the doc here, compute pairwise correlation of columns, and this is basically what we want to do. Let's just look at the data. So what do we see here? So first of all, you see the diagonal here. It is 1, 1, 1, 1. Why is that? 1 means that you are perfectly correlated. That means a transaction versus transaction is perfectly correlated. House age and house age is perfectly correlated. What does that mean, right? So house age, if you make the correlation between house age and itself, that means if you have this value in house age, what is the predicted value in house age? It's the same, right? So it's 100% correlated. So that's why the diagonal is 1. But what we're looking at is, for instance, the house unit price. What does it correlate with, right? And if you look at this row down here, you actually see that the transaction date, it is very low. 0 means no correlation. 1 means perfect positive correlation, and -1 means perfect negative correlation. So we're interested in numbers that are close to 1, -1. 1 or -1, but not far away from 0. So it means that transaction itself doesn't really matter. It means house age does negatively correlate. That means that the older the house, the less the unit price. It makes sense, right? Old house, they decay. But it's only 0.2. Distance to train station, it also highly negatively correlates. That means the longer away the train station is, the lower the price. Makes sense. Number of convenience stores, right? It also correlates highly. So the closer you are to convenience stores, or how many you have close convenience stores, the higher the house price. And then this is the funny ones, right? So it's also it correlates almost as much with number of convenience stores as with latitude and longitude, right? And why does it make sense and why doesn't it make sense? It makes sense because we know as humans that there are some areas where the prices are higher than other areas. But the point is here that when you do these machine learning things, you need to think. You need to figure out what makes sense and what doesn't make sense. Okay? Good. So far, so good. Another step you also are familiar with now is we need to explore the data. Is there missing data? Is null. Some. And we see we actually have a perfect data set here. There are no missing data. And that's what we're looking for. Because if there was missing data, we need to do something. And another step you could have often is there any outliers? Is there some data that seems to be wrong? You could investigate that. We're not going to do that on this stage of the course. Just to let you know that there are more things you can do. Good. So, what do we want? Actually, we want to take the full data set, and I want to show you actually how you can also do it. Before we've been using writing a lot of columns and so on, but let's just do it the easy way here. So data, actually iLog here, and iLog takes rows, but can also take everything else actually. And for instance, if you do this one here, it takes all the data except the last column, right? And then you set y to be data iLog colon all the rows, but only the last column, right? So what do we have here, right? So in X, we have all the data except the last one. And in y, we have only the one we want to predict, house unit price, right? House unit price over here. Perfect. Good. So far, so good. So now we actually have prepared the data as we wish. And let's also just divide it into test and so on. So x train, x test, y train, y test equals it goes well, rain, train, rain, random state 0. Actually, I want to, because the data set is quite small, right? Let's just see here. Length y, doesn't matter which one. It's 400 data. So I actually want to limit the test size to 0.15. And why do I do that? You see the default values, they're often given here. Test size, okay, you have to go down there and look for it. Test size, yeah. So you see the default test size, it will, if it none, it will be set to 25%. But I want to make it a bit smaller because we have a small data set here, and it's a trade-off I'm taking now. Perfect. So now we have the train, and test, and so forth. And now we want to use our model. And which one was it? Remember, we're gonna use this linear regression model there. So let's do that. I'm just gonna use it by default. And again, many of them you can put all kinds of things in it. Fit, interpreted, normalize, copy X, jobs positive, and so on. You can do a lot of things. Some of them are more interesting than others, but in this one it's not so much. Remember the how's it called? The K closest neighbors classifier. There you can do a lot of things, right? Fit, X, train, Y, train. Perfect. Now we fitted the model and it wasn't happy. It said fix, not fit. Thank you for helping me here. It's because I'm talking and talking to you, I get distracted, right? Perfect. Awesome. Perfect. Let's predict Y, pred, and we do linear model here, predict, and we take X, train. Perfect, here. So now was the time, right? Because now we're doing something differently. Remember, in the other ones we use this accuracy, and here in this one we use this R square score, because just because you predict a tiny bit wrong, it doesn't mean it's all wrong. But let's look at the result here and let's be surprised. So how do you do that? R2 score, and it probably does the same. True predicted, right? You see here, you get the true values and the predicted values. So Y test, Y pred. And what do you get here? You get an error. And what do you say? Found input variable to be inconsistent number of samples. Test, I put X train in here, right? Thank you for helping. It's good. So what happened there? I put the train instead of test here. I'm supposed to use the test data set here, right? And then there were becoming too many values in the prediction here, so it didn't match the Y test. It has to be the same numbers. So again, you get an error. I get that all the time. Don't worry about it. Then you fix it, right? Figure out what it is. In the beginning, it can be a bit confusing what to look for, and you get this error output. Let's just try to get it again here. I think it's good. Good. So what do you see here? So how can I figure it out so fast, right? So found input variable with inconsistent number of samples, right? It was 63 and 351, right? So it says here that this one has 63 and this one has 300 something, right? So I immediately think, okay, I did the wrong thing here. And how can I know that so fast? I don't know. I've been doing this many times, and don't get confused about getting errors. So here we have a score. It's 68. Is that good? Is it bad? I have no idea. But what's funny is it's a measure. And then you can try to optimize according to it and try to look at the data and see if you're satisfied. This is just a measure, a one number measure where you can compare all the test data points to the predicted ones. Okay. So I actually also wanted to show you this, how is it called? Coefficients. Coefficients here, right? So what do we have here? 1, 2, 3, 4, 5, 6 coefficients here. And what are these? These are actually the coefficients we talked about up in our formula here, right? You had 0, 1, 2, 3, 4, up to 6 in this case here. And how many values do we actually have, right? We have 1, 2, 3, 4, 5, 6. And then this one, right? So 1, 2, 3, 4, 5, 6. And that's what we have here. 1, 2, 3, 4, 5, 6. So we have these coefficients here. And can you use it for anything? I don't know. Yes, you can. You can actually make plot with them. It was 2-dimensional. You can use these to plot the line that you're using, but we're not gonna do that here. It's just to show you. So the final thing I just want to show you is, like, again, because this is gonna prepare us to the project. Let's make a figure again, and I'll show you in a moment what I'm talking about. PLT subplots. And what do I want to plot here? I want to scatter something. I want to take X. Longitude. Y equals X. Latitude. And then we make the color based on, and data, house unit price. What I'm trying to do here. Okay, so let's look here. So obviously we are seeing some connections here, right? So this color here means it's higher prices, right? So the lighter color, higher prices, the darker color, the lower prices. So what we're going to do in the project is kind of like, can we categorize in these prices actually and predict the prices based on the location, and how well will that do? And we can do a measurement comparing to this 68 here. Actually, can we do something that does something that is on the same range, predicted as good, but only on latitude and longitude, right? Can we do that? That's the project. Isn't that exciting? I think so. So if anything, ask questions below. Now we're gonna dive into the project. I'm going to introduce the project to you. See you in a moment. Are you ready for this project? It's going to be a bit crazy because I like to do some things that maybe make sense, maybe don't. So we are trying to categorize house prices based on the location, based on longitude and latitude. How will we do that? We will use a K nearest neighbors classifier to do that. But wait a minute, we have discrete values. Well, that doesn't matter because we're going to make categories of price intervals. So actually we're going to make 15 price intervals and put them in categories from 0 to 15. And then we're going to use our model to try to predict the price. Wow, that sounds crazy, but follow along with me. It will make sense. Okay, so let's get started. So the first step in this process is to import the libraries. That's all you have to do is execute it. And you see here we use a K neighbors classifier and R2 score or R square score and accuracy score because we're gonna just do that for fun. Then we read the data. It's files, houses, prices. Perfect. And then now the step. This is the first time you do this, so if it's a bit confusing, don't worry if you don't figure it out, but let's try to do it. Try to do it and see me do it afterwards. So create 15 bins of house prices. Well, you use this cut function of pandas, I'll show you in a moment, on the house prices and make 15 bins and assign it to a column class. So if you want to look a bit on it, so it works like this. You kind of have the cut function here. And then you take the data frame or the column here, so that it's a series, and number of bins. And what it does is it takes data and categorizes it in bins intervals, right? So these are discrete into 3 equal size bins, right? 3 here, right? And here you can see a couple of examples on how it's done. If you don't figure it out, don't worry about it. We will do it together and it will be a pleasure. Then the second thing is, well, our k nearest neighbor model doesn't really like intervals. It likes codes, discrete values. So we're going to take the codes of the categories and assign it to class ID instead. So we take the class, the column class, and we take the .cat.codes and assign it to class ID. And then you get numbers like 0, 1, 2, 3, 4, 5, 6, 7, up, all the way up to 14 probably, with categories. Okay, good. Now we prepare the data. So we take X to be all of the data of the 6 first columns. I think there's 6 columns, right? And you can do that by ilog. And then you assign Y to be the class ID. And then you do the test train split. I should say train test split here with test size 15. And then you run the k neighbors classifier. You create one of them. Then you fit the model on here. And you might think, wow, this is a bit confusing. Why didn't I just do it up here? Well, in the last step, we need more values from it. So that's why we did it like this. And then you do the Y train. Then you do prediction on the test and do the YPred here, and then you calculate the accuracy score, and it'll be really low. And that, why is that? Well, if you look at data, right? So if some data is pretty close to, but comes in a wrong bucket or a wrong bin, it will be penalized by that. We will see that too. And then finally, we're going to do the prediction of the categories with the R square here. And this is a bit confusing. So it's basically copy pasting what it says here to make a data frame with the predicted values. And then we convert that into predicted values of the middle value. So we take the middle values of the categories and put that as a price. And then we compare that to the real score and see how it performs. That's exciting. Let's continue. See you in a moment. Or you should do something, and then we'll do it together if you need so. Maybe you don't. See you. Okay, are you ready for this? I hope so, because this is really exciting. So let's dive into it. How far did you come? Let me know in the comments. So let's start. So first step is to import the libraries. Did you manage that? I hope so. Then we read it. So data. PD, read, CSV. Which one is it? It's files, house prices. Oops, I'm typed wrong here, house prices. And let's just say data, head here just to see the data is fine. Okay, and let's prepare the data. So this is probably a bit confusing, right? So we have to create 15 bins of house prices. And we use cut on house prices column. So let's try to do that. And again, just look at this here if it was confusing, but let's just try to do this here. We call it class, and then we use PD cut, and we take data, and we take house unit price, and we take bins 15. If you're swearing right now, it's okay, because I also find sometimes, wow, was it that easy? Okay, so data head, but it can be confusing when you do it first times. Okay, so here we see we have a class now, a class column here, and for each price is put in a category. Okay, you see that, right? So 37.9 comes into this interval here, starting from 36.9 up on the way to 44. And again, 42 will go to the same category. 47 will go to the next one, as you see, from 44 to 51. And 54.8 will go into the next one, because that one ended at 51 and this one ends at 58, right? And 43 is in the first category. So unfortunately, or fortunately, I don't know, the k nearest neighbors classifier doesn't like classes. So we want to convert that to the codes. So class ID, we want to transform these class to the categories of codes. And how do you know this? Well, you just play around with stuff and figure it out, right? Or read the manual. Okay, so here you see this interval is now class ID with single S. Now we have double S here. It's annoying. Can you live with that? Okay, I'll just delete it here for you. Data. Drop. So this is what happens once in a while when you get too excited, right? Class ID in place true. Okay, it didn't like it. It wasn't called class ID. Okay, so access is 1. Okay, perfect. So what happened now? I just deleted that column here that I mistakenly added up there. Okay, perfect. So we just delete this again here. Perfect. But now you see sometimes people get excited and they talk too fast, write too fast, and you make mistakes. And I just clarified how to remove it again. Okay, perfect. So here you see here that this class has this class ID and so forth. So these are 4, 5, 6, and then 4 again here, just as expected. And then prepare the data. So here we just assign X to all the data. I think I introduced it a bit differently, but that was actually kind of a mistake because you need all the data down here. So can you forgive me? Data and Y, assign that to the data with class ID here. So that was the first step here to assign that. So isn't it cheating to have all the data in here? Well, in the next step, we only use a latitude and longitude, so it's not cheating. And why do we need all that? It's because we want to have the train and test data aligned with the categories as well. So it'll make sense in a moment. Train, now we do the split, X test, Y train, Y test, to train, test split, X, Y, test size 0.15, random state 42. Perfect. So now it is been divided. Okay, so now we need to train the model. We create a model. Let's do that. Model, k-neighbors classifier. It takes k as phi as default. That's fine. Fit the model on train, this one here, and Y train. Let's just copy this one here. So let's say model fit here and Y train, and then we need to predict Y pred model predict, and it will take this here. I actually think I got a space in front. Let's just see here. Yes, I got a space here. Just delete that. Predict, and then calculate the accuracy score. And it is the real values first. True, yes, and Y test Y pred. And 42, and it's just like, wow, that's not good. But it is actually, when you think about it, because what this does is if it predicts in a wrong category, you get penalized. So it only predicted 42% in right categories. But look at the data again. For instance, this 37.9 here, it goes into this class here, but you also see it's quite close to the boundary. So maybe our model predicted it to be in category 3, which ends at 36.9, which is one value away from it, right? In the end, right? So that is penalized fully in this way of doing it. So it doesn't really make sense. So what if we make something funny down here? So we want to make an R2 or R square score on it. But how can we do that? Because now we have categories, right? What we need to do is map these categories to the middle price of it and compare it to the real house unit price. Did that make sense, right? So we take the category class ID, we map that to the middle value here and compare it, with the predicted category, map it to the middle value here and compare it to the real unit price and see how well it does. How do we do that? Well, we take this one here. It creates a data frame with the predicted values and creates a column, call it predicted categories, right? And then we want to find the middle value. You do that by this here. So you have the predicted value to be the middle value of the categories, right? We use this apply again with the lambda function, and it takes the class of the categories and takes the it looks up the category interval and takes the middle value of it. It looks a bit more advanced than it actually is. Don't worry about it, it's not that complex. And then finally, we can use our function here with the real score on the first one. And how do we get the real score? And that's where it all comes to an end, because we needed the original prices, right? X test here with the house unit price here. And that's why we kept all the data with the predicted data here, pred. And then we see we actually get 69%. Or not percent, 69, score of 69. And if I remember correctly, in the lesson where we did way more data analysis with a more advanced model, maybe, I don't know. Yes, we use this linear regression. It predicted it to, it has a R-square score of 0.68. Does that mean this is better? No, the point is kind of like funny, right? So this is only predicting the price based on where you're located and nothing else. And this actually predicts it pretty good in this case study here. But this model we created here will not work on arbitrary data, not from this local environment. It will not be any good. That's kind of the key thing. We're doing this for fun because it kind of, it makes sense because there are local areas where people pay higher prices than other areas. And that's what we do here. So, makes sense? I hope you enjoyed this one because it's really been funny to make. And let me know below here if you thought it was too crazy or it was inspiring to see it. In the next one, we're actually gonna start with some of my favorite. It's gonna be reinforcement learning, and that's amazing because reinforcement learning is so mind-breaking. It is amazing how it works, and it's easy to program from scratch. And we're gonna do that actually because I love it, and you will understand it too. And it's gonna be simple and nice, and yeah. So unless anything, let me know in the comments. I'll be happy to help you. So see you in the future or the next lecture. See you. Bye-bye. Reinforcement learning, one of my favorite machine learning models. You know why? Because it's simple to understand and you can actually implement it from scratch because the concepts are so simple. It's going to be amazing. You're going to love it in the end of this journey here. This is part of the 15-part journey of machine learning with Python. If you're new to this, there's a link below there. You can get all the resources, all the notebooks, all the projects we are doing down below there. So click, check it out, and let's get started. So, reinforcement learning. Wow, don't you just love it? Well, what is the goal of this lesson? Obviously, it is to understand what is reinforcement learning and how does it work. Learn about the agent and the environment. I mean, first of all, yeah, you need to understand the model and what happens there, and that's the agent and the environment. And then how it iterates and gets rewards based on actions, right? And how it continuously learns new things. I mean, this is just amazing. And then we're going to create our own reinforcement learning model from scratch. And you're worried? Don't be, because it's so simple. You're going to be amazed. Perfect. So here we are. What is reinforcement learning? Simply explained. Well, given a set of rewards and punishments, or punishments they often called it previously, learn what actions to take in the future. So I often like to think of it like training a dog. And I think that's where the reward punishment came from. But often, I mean, I don't advocate punishing dogs, so you should reward it when it does something good and reward it, just ignore it when it does something bad. But the idea is that you are in some kind of environment and you have an agent, and this agent is exposed to a new environment, and based on the action, it will get a reward and a new state. So think of it like this. So when you have a dog and you want to train it, you speak different languages. You don't communicate in the same language. But the dog learns based on your rewards based on it. Imagine that the dog is doing something good, then you give it a reward. If it does something bad, maybe you just ignore it, or maybe you make a negative reward. That is the base idea about it, right? So you do something, you make an action, you are exposed to this environment, and you get a reward based on that. And if you do positive rewards, this is learning you want to keep and continue doing. If you get negative reward, you don't want to do it, basically said. So we have the agent here, right? So the agent, the environment gives the agent a state. So you're in a state. So imagine if you're a dog again. So a state could be you're lying in front of the door, or you're being outside. That's a state. Then you take an action. So for instance, let's say the state is the house owner comes home to the main door. So the dog can either bark, it can move away and jump up and lick the owner or whatever, right? So these are the possible actions that are possible. Then the environment is giving a state and a reward or punishment, right? So based on, let's say the dog barks, the dog owner doesn't really appreciate that, so you don't get any positive reward from that. Or the dog jumps up and licks the owner, real happy about it, but doesn't bark, and the owner likes that, so he rewards the dog. Okay, that's how it works. And just to give you an idea where it's been used, right? Like how robots are taught how to walk, right? So for instance, balance of a robot is pretty difficult, but learning, when it falls, it gets negative rewards. So it learns how to use all the mechanisms in the body to keep the balance, right? So it gets immediately rewards back, positive or negative, based on what it does. And that's the way it's learning. So we have something called Markov decision process. Don't worry too much about this. It's more like if you're like the mathematical aspects of it. So let's just try to explain and see if we can make sense of it, right? Model for decision making represent states, action, and their rewards. A set of states. So we have a set of states. That means all the possible states that you can be in, right? So for instance, for the dog, it can be inside in front of the door. It can be inside in the living room. It can be inside in the kitchen. It can be outside, and so on. Those are the states. And then a set of action. And the actions depends on the state, as you see here. It's denoted by the state. So for instance, in the kitchen, the dog can beg for food, it can lie down, it can walk out to another room or whatever, right? These are the actions the dogs can do in this specific state. So the actions are specific to the state. And then there's a transition model, right? So you have some kind of a model here where you can go to the new state based on the previous state, giving an giving the state and the action. And then you get a reward function that given that you were in this state here and took this action, you went to this state, what is the reward? Perfect. Q learning one model. So the method for learning is a Q function where you have a Q state and an action, right? So estimate the value of the performing action in the state, right? So this is the estimate. So you have like this Q table, and then you update the values, and when something goes good, you update it according to the actions you're doing. So let me say this differently, right? So you're in a state and you take one action. Based on that action, you will update that table. Or you can use that you're giving in a state, you have these possible actions. Which action is the most likely to give you some reward? And this is where the Q learning comes into the model, right? So we start with a Q table where we have that all the states and action are 0 because we know nothing in the beginning, nothing at all. So given any state and any action, we don't know what's going to happen. So it's all to 0. Then we update Q when we take an action, and we update it according to this formula here, which looks pretty scary. But we have some things here, right? So basically said, we say we update the Q table based on what we did previously. No, in the beginning it will be 0, and then we have some learning rate alpha, and we take the reward and we multiply that by some gamma, and we take the maximum of all the possible states and subtract the old state action from that, right? So we take the difference we take the reward, we take the maximum of the possibilities from the new state, and then we subtract the old value of the state. This can be rewritten like this. So it's 1 minus alpha times the current value of the state times the learning rate, the reward, that is what we gained from the action, and this is the maximum multiplied by the maximum of the new possible states. Perfect. And then we also do something else. Okay, so yeah, I know this sounds really, really scary, and I said it's really, really easy. And yeah, I know all this math here makes it kind of sound scary and easy. No, not easy, but scary at first. But don't worry, this formula here, this is the hardest part to understand. But think of it like you have a learning rate, and you take your previous experience and you update it according to the new experience with this learning rate alpha. That's basically what you think of. So maybe you don't understand the math, but it's basically taking what is, so next time you are in this stage, so you can update the values, you will see that in a moment. You will update the values, and then you will see, based on my experience, I know taking this action will be the best one. Just wait a moment. And then we have this epsilon greedy decision making, right? So explore and exploit. So imagine you're a dog again, and the dog always has one behavior. Say, for instance, when you have some visitors coming at your house, and the dog had two actions there previously, and it was like barking or jumping up on people and licking them in their face, just like it does with the owner. And the owner likes that, but the owner also thinks that, basically, this is not the behavior I want. But the dog only knows these two actions, only done these two actions. So what happens is, when it barks, it gets negative reward. When it jumps up on the people, maybe it's not negative, maybe it's a neutral reward. But if the dog only has these two options, it will never figure out that it's a better way. And that is maybe just ignore the people coming. So this is where you sometimes, with probability, epsilon takes a random move. And that random move could be, okay, the dog didn't do anything. And then the owner gets all excited and rewards the dog positively. So next time the dog knows, actually, okay, when visitor comes, actually my owner wants me to just lie down. Don't jump up, don't bark, because the best thing is just do that. And then you get a reward again. Amazing. Good. So does that make sense? I hope so. Good. Now for our field. So we're going to have a simple task here. So this is our universe. This is our states. This is our universe. So the idea is that you are put down in some random state in the beginning. And what happens is you can either move left or you can move right. If you move, for instance, left, and you move to the red point here, you lose. But if you move here and you move to the green one, you win. Similarly, if you start here and you move to the green one, you win, right? If you move outside the field, it's no good. This lose, this win. Outside the field, don't do that. Okay, so we need to model this universe. So this is our universe, and we have two actions. And in the end here, we don't have action going right. And in the end here, we don't have the action going left. Okay, make sense? Perfect. So what we do is we start at a random point. So when we play our game, we'll just put one time here, maybe one time here. Maybe we start here, but then we lose immediately, but we can't do anything about it. Or we start here, we win immediately. So we start in a random point. And then we need to figure out what to do. So we need to update this Q table I'm talking about. And then suddenly all these formulas and all this kind of stuff up here will kind of make sense to you. It should. So to do that, we're going to use something called object-oriented programming. And if you're new to that, I actually have a link to an awesome lecture describing all this kind of stuff here. Because object-oriented programming, it's not really difficult. It's just convenient for some problems. So I'm not going to go into what object-oriented programming is. I assume you know that. And if you don't know that, look at this lecture. And if you need some, it's a part of a full course, so you can actually take that course if you want. It's for free as well. I made it too, yeah? Okay, so the point is you start at a random point, then you move left or right. Avoid the red box, find the green box, right? So we need to teach our model how to do that. It's gonna be amazing. So in order to do that, we make this field here. And this is representing this field here. So initialize the field and set a random start state. Okay, that is what we do here. So we make a field representing this part here. Let's do that. And then we have some methods. One of them is done, return if in an end state or not. And then we have get possible actions, return possible actions in state, and then update the next state. Here you see we take the argument action, update state according to action, return state and reward. Perfect. And we're only going to use NumPy and random. Actually, NumPy has random in it, but yeah, I chose to use this randomness here. Okay, it's okay. You can choose it otherwise if you want. So let's start by importing that, and that's all we need. And we're basically only using simple functionality from NumPy, representing the Q table and getting them arguments, maximum arguments. I think there's nothing else we use. Let's see how it goes. Perfect. So the first thing is we need to implement this field here in an object-oriented class. So we're gonna define it down here, class field. That's it. We're creating our object. Def init function is the function called at initialization, and you need to have this self with it here. I'm not gonna explain anything about that. Good. And then we have this states, right? So we need somehow a list to represent, or that's one way to represent it, all the states here. And how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11, right? So I want to represent somehow the states, but I also want to represent good and bad states. So we have some neutral states, these here, gray ones, and we have a negative reward state and a positive reward state because we want to emphasize here. So how am I going to represent it is by what is the reward if you end up in this position. And we have some neutrals and some negatives. So the first one is negative. And then it is neutral, 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 neutral. And I think if I count it correctly, this should be it, right? So we have, let's count it here. Neutral, and then 1, 2, 3, 4, 5, 6 neutral or negative, and 6 neutral, and then positive and 3 neutrals. Okay, let's see. Negative, and then 1, 2, 3, 4, 5, 6, and then 1 positive and 3 neutrals. Okay, so this is our field. And then we start with a state, and that should just be a random state. And we do that random, rand range, I think we can use. Let's look at what rand range does. Rand range. Okay, so sometimes you misspell. Choose a random item from the range start to stop, and stop should not be inclusive. Perfect. So we do that by 0 point length of self states. That's how it is. So now we create a field and we create a random state. Let's actually just try that. So we do a field here to be a field, and then we take field state here, right? So you see here we create different states here. Every time we run it, it's most likely something different, right? Perfect. Awesome. So the next thing we want to do is check whether we are done or not. Okay, so def done self, and just for simplicity, let's just write it out here because self. So if self states self state, if this is equal or not equal 0, we have return true because then we're done, right? So in the case we are in -1 or 1, then we're done because either we failed or we won. All the other states are, you can continue, we're not done, right? So this is basically it. Else return false. And I know you can write this in one statement, but I like to explicitly write it like this because coding is also about readability. So let's actually try that, and we'd say field done here. We cannot do that apparently. Field object knows attribute done. This is because we need to execute this one up here. Okay, so I made a classical mistake. You need to execute and define it before you can do it, obviously. And you see false, true, right? So when you're in 0, it's true, right? And you can continue to do it a few times. I thought actually 8 was 1. 0, 1, 2, 3, 4, 5, 6. Oh, it's 7. Yeah, okay, makes sense. So should we try to get a 7? Here we have true, right? Okay, perfect. So this is basically done. This is done. And what was next? It was get possible actions, right? Return possible actions in a state. This is where you are in an environment. Get possible actions self. And one way to do it is to say, what are the possible actions? So let's just define the actions here, right? So action 0, let's put it like this, is left, and action 1 is right. Okay, so the idea is here, right? So if you are in a state, you can either go left and right, and some states like the beginning and the end, you can only go here, you can only go left, and here you can only go right. Okay, so actions could be, we make a list here in the beginning and we have both actions available. But if self state equals to 0, that means we are in the first state here. You cannot go left. So you take actions, remove 0, not 9, 0. And if self state equals length of self states minus 1, right? Then we are in the end here. If we are here, you cannot go right. Actions, remove 1. And then we can just return actions, right? So let's actually do that. Field get possible. Okay, we need to execute this one here, and then we can get auto completion here. Boom. So here we have it. If we are in 6, it's not done, and we have these actions. Let's try to get one with fewer actions. It takes some time. It's tedious. Okay, so 10, that's 11th position, right? We can only go left. Perfect. So this looks good. So you see how we're building this simple model here. Then we need to update next states of actions. Oh, def get, no, update next action. Was that what I called it? Next state. Okay, that makes more sense. And it has self and it has action, right? So what we want to do here is we need to think about, like, if we take a action which is illegal or illegal, right? So if action equals 0, that means we go left. We need first to check if self state equals 0, because in that case we just return self state. We don't change the state, and then we have minus 10 reward, because we say we don't want you to do that. Other than that, we take self state to be minus equal 1, right? We subtract 1 from it because we're going left. Perfect. And then we take if action equals 1, then we take if self state equals length of self states minus 1. Then we take return, we don't update the state, and then we return negative 10 because we don't want you to do that. And then self state plus equals, in other case we add 1 to it, and then in the end we want to get the reward here. Reward is equals to self states self state. So if we are ending up here, we want to have the reward to be minus 1. If we end up here, we want it to be 1. Otherwise, it's just 0. We don't care. And then return self state reward. Right? This is basically it. So actually, let's try it here. So we have a field here. So we are in number 5 here. So let's look at our table here, right? So 0, 1, 2, 3, 4, 5. So now we're really smart. We go right and right. Let's try to do that. Field, update, next state. We put it to 1. And let's just do this one here. boom. And then we have here, right? And then if we execute once more, actually, now in state 6 here, we are still not done. And we still have 2 possible actions, right? We go out, right? And basically because we can continue, we can actually continue out of the field. And in the end, we actually get out. Actually, I didn't get the -10 here to show you that this is actually what's happening. But as we don't update the state, we can actually execute it once more. And you see you get state 10. We continue to be in state 10, but we get a -10 in reward here, right? Perfect. So our field is working as described. It makes sense. Okay, so now to the learning. This is where all this formula comes in. And how do we do all that? Well, let's get to it and try it out. Don't you want to try that out? Good. So one way to do it is, again, let's make a field here. The reason why I want to make a field here is actually because we need to make this Q table here, and this Q table needs to be of a size of the field. So it's basically length of the field states, comma 2. And why is that, right? Let's just take a look at this thing here. So this is it, right? So the Q table is meant to, being in state 0, that's the first row here, you have 2 possible actions, right? Or we don't have 2 optional actions, but we don't know that. But then you have initialized it to 0, like we talked we should do, right? Remember? It said here, start with all 0, right? So we have a state for each state. So each row is a state, and each item in a row is a possible action, and they're also 0, right? So in the first state, we have 2 actions, potential actions, and further down here, but we don't know which ones are illegal and which are not. We will learn that, because if we go left in the first one, we will get a punishment of -10. Okay, perfect. So, okay, so let's do some more work here. So let's call the learning rate alpha and epsilon here, and the gamma to be here, and just to put them to some values. It doesn't really matter. You can play around with it afterwards. It doesn't really make a big difference here. I mean, what makes a difference here is especially epsilon here in the beginning. Theoretically, you only need to take random actions when you learn the state, but we're not going to do that here. And the gamma and alpha is about the learning rates, and we're not going to go into that in this one. You can play around with it. And alpha, the higher alpha, the more you learn from each stakes. And in the beginning, you want to learn a lot, and later, maybe you don't want to learn so much. Okay, so let's train our model. So we do that in some kind of range, and I think we do, what, 10,000 iterations. Then we create a field. So we create a new field every time, because we want to play in a new field, right? So while field, or while not field, I can continue typing wrong there. While field not done, right? This is what we are working on. Okay, perfect. So what are we going to do, right? So the first thing we want to understand is what are the actions that we can take, right? So we get the field and say, get possible actions. Perfect. And now the thing is, now we're having, should we do a random move or not, right? Remember, with probability epsilon, we want to take a random move, or we take the maximum, right? What we already learned. So let's do that. And right now you're thinking, well, it's all empty. It doesn't matter. It doesn't matter. Because in a few iterations, it will not be all empty, our Q table. So if random, how's it called? Uniform, sorry, uniform. And uniform is just taking a uniform integer from A to B, right? So it's just 0 to 1. And if that is smaller than epsilon, right, then we take action as a random choice of actions, right? So what it does, it just take a random choice in this one here with probability epsilon. And else, what do? We take action is equal to np arg max. What am I doing? So I want to find the argument in our Q table of the field state, right? So if let's say we're in this state here, then you take the argument of the max, right? So if it's argument 0 or argument 1, we want to know that we don't want the value if it's 0 or 6 or whatever. We don't care about the value, we care about the argument because it's either this action or this action, okay? Perfect. And then we just save the current state. So let's do that. So the current state is field. Continue doing that. I don't know why. Field state. Why do I want that? It's because in the next line here, we're gonna get the next state. Oh, next state and reward. And we take the field and we say update next state action, right? So we take the action, but we want to remember the current state because we need that when we update the Q table with this insane formula here. Okay, so I'm gonna use this variation here. Wow, can we remember all that? I don't know. We'll see. Instead of writing on this way here, because here you have to write it differently twice. So I'll take the second variation. So Q table current state action is equal to 1 minus alpha. Tell me if I do it wrong. Q table current state action, right? This is the first part. And then what is the next part? So 1 minus alpha Q state plus alpha reward gamma maximum. Okay. Plus alpha times reward plus gamma times, and now we want, what is it that we want here? We want the maximum value. So the maximum value of the Q table of the next state, right? Perfect. Let's try that. Okay, alpha is not defined. I always do that. Alpha. I don't know. What's typing today is not. Okay, perfect here. So what happened here, right? So we iterated 10,000 times. We created a field. And while we're not done, that means while we are in some kind of state, which is not red, not green, then we continue iterating. And what we are doing is we check the actions possible, and with some probability we take a random action, and with other probability we take the best action we know based on our previous experience. And also we have then we save the state, and then we update it, and we get a reward. So for instance, if we were at the end of the table here, and we went right, then we'll get a negative reward, and our state will not change, but we will save that in our table based on this formula. So let's look at the table now, actually. So let's actually have the table lifted up. Okay, here. So let's look at the table now. So imagine we started in this position here. Well, there's nothing to do because we don't do anything because the field is done. Remember, we check if field is done. Then in this one here, then it actually says if we go left, that's a minus choice. But if we go right, it's actually positive. It's not very positive, but that's because it takes a long time to realize where to go, right? So if you take the maximum, we'll go this way here, and then we come in this state here, and it says actually to go right again. Right again, right again, right again, right again, and 1 here, right? So you can see somehow the learning takes less and less and less, but the negative side here ensures that we are attracted to the positive side. And equally on the opposite side, right? So if we start here, for instance, this is this one here, we know we should go left. Similarly, we never in the end here go right because it's 0 and it says it's go left, and it knows that it is better to go this way. You might wonder, for instance, if we're in this state here, it actually has a small positive thing. Well, why can that be, right? But if we are here and we go here, we can actually still get to a positive place, right? It's just a longer distance to get there. And this is what the formula accounts for. Well, what is the smartest way? It's going left, left. It's not going right, then left, left, left. And this is the basis of it, and this is amazing actually. And in the project, we're going to do something which is a bit more complex. We're going to use the same thing here, just a bit more complex field. So it's like we're going to expand this one to be a bit bigger. So are you excited? So let's meet in the next one, and you will learn more about this. This is your turn to try it. See you in a moment. This is going to be an amazing project. I love this one. It's going to be amazing. Okay, so what is it? Let's jump to the Jupyter Notebook and introduce the project. And if you're new to this, you can get the notebooks prepared for the project. So you just follow along these steps in this manual here. So it should be straightforward for you to try it out yourself. And then afterwards, I'm going to try to solve it together with you. Okay, so let's jump. Okay. Project reinforcement learning. Exciting, huh? So bigger field, more learning, right? So the other one is like a one-dimensional world, right? You could go left or right. So let's expand that. So use reinforcement learning with Q-learning to find solution to this field. So here we have the field. It's bigger and it's two-dimensional, right? So now you can go left, you can go right, you can go up, you can go down. In one world, you could also go diagonal, but we're not going to do that. But you could actually add that as a potential side bonus to your project. Other than that, you can just say up, left, up. It should be the same as diagonal, but maybe there's some kind of, you want to make a field where it's actually possible. No, I'm just babbling. Okay, so you understand it, right? So the goal is to find the green field and avoid the red ones. And we have 2 red ones now. Wow. So the first step is import the libraries that we're going to use, NumPy and Random. Perfect. And then we're going to create a field. And what's funny here is actually the field is identical to the one we did in the lesson. On surface at least, right? But below it, it is actually a bit different, right? So what is the advantage of having the same kind of fields? It's like, well, actually the code that you used in the lesson, it is identical. The only difference is the things happening behind the field. So this is kind of one of the power of object-oriented programming. You can actually, then you can just take this field and exchange it with the field we used before, right? Make sense? Okay. So again, we have an init function done, get possible actions, get next actions, and it's described down here how you could do it. So init, right, initialize the list of represented states, and here it should be a list of lists. Before we had only one list, so this is one difference, right? Now we have a list of lists, and we have the positive end state should be 1, illegal state should be -1, and other states 0, and start in a random state, right? So also one difference here is the state is giving by 2 numbers now instead of 1 before, because it was just one-dimensional. Now you have a coordinate system, so this can be 0.0, then it can be 0.1, 0.2, and so forth down there. And done, check if current state is not negative. It's basically the same thing happening. And now possible actions, we make a list of actions 0, 1, 2, 3, because we have 0 left, 1 right, 2 up, 3 down. This is just a decision I made. You can have a different numbering if you want. And then check if the state is in a position where its possible action should be removed, right? Exactly what we did there in the lesson as well. Now we just have more states, it's a bit more complex. And finally return the remaining actions. And then update next state. And basically it's the same way of going around, but you have more checks to do, more negative penalties that can happen. Perfect. So if you jump off the board, -10, because you want to avoid that at all cost. And then we train the model, and this is basically the same. Create a qtable initialized with 0, and you need to insert the values here, and it's going to be a bit bigger than in the lesson, right? You have 1 dimension more in it. Then you have alpha, gamma, and epsilon. Again, we're not going to dive into these values. There's a comment below with this epsilon. You can actually have that. You would never take random actions. No, only take random action when you teach it. Then again, we do a loop of 10,000 iterations, and then it's basically described what to do here. It's exactly the same algorithm from the lesson. There's no difference at all. Simply identical. The only thing that's different is the qtable, right? And you can see here you actually have current x and current y dimensions instead, right? So okay, it's not 100% identical. You could make it like that, but we didn't. Okay, so solve the task. And again, this we didn't actually do in the lesson, but I thought it could be funny. So you kind of make a path and you create a field and count the steps, assign steps to 1, and then assign the start state to just another number, just to put it to something. And then we begin, we take action, and the next state, path, steps, and see the path, right? So this is kind of funny. It's just to check out how it would do. And in the end here, it's noticing that step 3 could just take random actions, and our example, step 4, we do not learn anything new. That is, we do not update our model based on actions here, because we just take the best actions possible. Okay, are you ready? I hope so. This is going to be amazingly fun. And don't worry if you don't get it immediately. Just it's quite similar to what we already done. But let's see you in a moment. Bye-bye. Are you excited? This is going to be amazing. This is one of my favorite projects. So let's get started. Reinforcement learning. So I introduced the project. So the first step is only to execute the libraries. And that succeeded. So far, so good. Now creating the field, right? And the field, as I explained, is having the same interface here. So we have the same methods here. But what's happening behind is a bit different. So let's just get started and see if we can figure it out together. And I know you'll help me. Class, field, actually like that. And then we say def, init, self. And this one is a bit different because now we need to represent the field, right? So let's try to do that. Self, we called it states. And we have a list of lists. And we want to represent each row as a list. So it's going to be here, and we have 11 along here and 3 rows here. And these two are -1, and this one is 1. So -1, and then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's count here. So 1, -1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's perfect. And then we take another row, another row here, and we insert it here, and then we insert another one here. And there's a difference because this row here has a 1 here because that's the end state, and this one here is all 0 here, right? So now we have the 1 here and the -1 and -1. So it is representing the -1, -1, and 1 here, and the rest is 0. Perfect, huh? This goes pretty well. I'm amazed. So now we need to make a state, all right? And you can represent that in many ways. I'm gonna represent it as a tuple here, right? So so you have the x-coordinate and the y-coordinate. And the x-coordinate will simply take the row, and the y-coordinate the column in the row. Okay, so perfect. So we take here, it's gonna be random, rand, range, and we take from 0 to length of self states here for the first one. And for the second one, we take random, rand, range, and we take 0, comma, length of self states, and we take the first entry here, right? So now we actually have a starting point, and let's, like we did in the other one, try to just make a field here and just see everything goes as we expect. So here we have it, and I continue doing that. That's funny. Okay, perfect. So here we started in state 1.9 here, right? Perfect. Awesome. So that actually clarifies that we are having the row and then the column there. Okay, perfect. Perfect. And one more here, def. And then the next one is done. I forgot self here. Perfect. And what we want to check is, again, are we in a position where we have a non-negative or non-zero value? Okay, so if self state states in self state 0, and then the second coordinate self state 1 here is not equal 0, then return true, else return false. Okay, so I executed that, and let's just try here. Field done, and we see here false. That is correct. And try once more. Actually, it's less likely to get a true now because the field is bigger. And let's see if we can get one here. I don't know. Let's last try here. No, we don't. Okay, perfect. It doesn't matter. We believe it is working, and if not, I'll owe you one. Def get possible, how is it called, actions, and we need the self here obviously. And the idea is kind of create the actions here, the possible actions, and just like in the lesson, remove them if not needed, right? So 0, 1, 2, 3, and let's just, for the fun of it, write them here. Action action 0 implies left, and let's just copy it here. And 1, 2, 3, and left, it was right, up, down, right? So we remember it. So what do we do first? Let's just take them in this order. You can do it in different order if you want. So if self state 0 equals to 0, that means we are in the top row. That means we are in the top of this mountain here. We cannot go up, right? In that case, we cannot go up. So action remove up is 2. And if self state 0, again, if that is equal to the length of self states, right, -1, action remove 3. We cannot go down in this case. And if self state, the second coordinate, is equal to 0, that means we are in the outside here. We cannot go left. Action remove left, which is 0. And if self state 1 equals length of self states 0 minus 1, then we cannot, where are we? We are in this end here, and remove 1. And then we return action. It should actually have been actions, shouldn't it? I think it should be actions. I know it doesn't really matter, but I think it's more nice to have it as actions. So let's see here, field actions. No, it was not called that. It was called get possible actions. And then we see here, we are, where are we? Something is not possible here. So we are in the low here. So it's down. It's not possible. So 3 is not possible. Let's just try one more. Here, everything is possible because we are in the first row and we are in the middle somewhere, right? So it seems to have some effect, at least what we're doing. And here we are in 2, 2, so it's a low one again, so we cannot go down. Yeah, perfect. Good. Now to def update, how's it called, next state, self action. And now we're doing the same thing here, right? So for convenience, let's just put x and y here to be self state here, so we don't have to think about that. Okay, so what are we doing, right? So if action equals 0, that means we're going left. So we need to check that we are in a state where we are allowed to go left, or we have to check we are not in a state we are not allowed to go left, right? So that would mean that if self state, no, x equals 0, right? Actually, that's y, right? I just confused myself. Okay, so if y, because y is representing this direction here, right? That's often what's confusing. Also with NumPy arrays, it's confusing. But if we are in end there, then we should return self state and -10, right? And if action equals 1, that means if y equals length of self states 0 -1, return self state -10. Oh yeah, I forgot to update it here. If it is then self state equals x comma y -1, and here it is self state equals x comma y +1, right? And if action equals 2, if x, that means 2 is up, so x is 0, then return self state -10, right? Else self state equals x minus, no, plus, oh, I forgot, up is -1, -1 and y. And then if action equals 3, then if x equals length of self states -1, then return self state comma -10, else self state equals x +1 y. And then we do, what was it we're doing here? Then we need the reward. Reward is equal to self state 0, oops, self state 1. Let's just make an, and then return self state reward. Woo! Invalid syntax. Where was that? Line 46 here. Perfect. Good. So now we have a field here, and let's see, we are in 2.2, and let's just try to add along here, right? So what we're going to do is field get possible action. We're in 2x2, so let's just try to go down. Update. Wasn't it called update? Didn't I execute that one? Okay, field. Okay, we need to update this one here, and then we have update next state here. So we're 1.4, so let's just try to go up, which was 2, right? And then we print out this here. So here we have it. we are in 0, and if we go one more here, it is still in the same position because we are doing a legal move. And I did the same mistake again. I forgot to get the result of that, but you see here, then you get -10. Okay, so it works as we are expecting, right? So wow, that was a lot of code, right? But we managed together. So awesome. Ooh-ha, that was good. And now for the fun part. Let's train our model. Okay, so now we need to initialize our model. So let's try to do that. Again, we just make a field here, and then we make a Q table, and we take NP zeros, and now we have to be the length of field states here, and the length of field states 0, and how many actions do we have? We have 4 actions, right? So this is it, right? So now our Q table is a bit more involved. So for each possible state, and now we have a lot of states, we have 4 actions possible, right? So here is one state, another state, and so forth here. And it's 3 rows, right? And for each row we have 11 states. Perfect. So it looks pretty good. So let's just delete this one and continue our journey here. Okay, so we have these, what does it say here? We have alpha, gamma, delta, epsilon. So let's just make that alpha, gamma, what was it called? Epsilon. We have those. And then we make a for loop, for in range 10,000. That should be enough. And then create a field, create a new field, create field. Perfect. And while not field done. Perfect. I forgot the colon there. And then we do get possible actions, field, get possible actions. Perfect. If, with probability epsilon, if random uniform 0.1 is less than epsilon, then what we do? We take a random choice, action, random choice, actions, and else action equal to nb arg max q table field state, right? And then we need to have the current state, current x, current y. It is equal to, oh, I did this again. I don't know. It's happening all the time today. Field state. Okay. And then we need the new state. Next x, next y, comma, reward. Remember that we want the x and y coordinate. Actually, never mind. X and y coordinate, and then we make field update next state action. And then we need this one here. I'm just gonna copy it because it's too much typing for me. And we're gonna cross our fingers that everything went well, right? Perfect. Awesome. Invalid syntax here. So there's a multiply here. So it didn't keep them up there and makes sense. Okay. I did that again and you didn't tell me? Perfect. So now we have it, right? And now we should actually have a Q table here. And let's look at that. It looks like that. That's a lot of numbers, right? It's difficult to make if this is correct or not. So that's why we actually, in order to check that it's correct, we want to go down here and solve a task. So let's try to do that. So start to see the path, make a variable path equals to np zeros, and that will be 311, right? So what we have here is a way to represent something, right? So we just put it to zeros and then we add numbers accordingly to that. Okay, so what we're going to do here is we're going to create a field and steps, and we take one step here immediately, and then path we're gonna update from field state 0 and field state 1, and we're going to put that to np not a number, right? And then we begin, then while field, I continue doing this, done or not done, while not field done. Okay, and then we take action and we take np arg max, and we take q table and field state, and then we take next x, next y, oops, and we take field update next state, and we take action here. Okay, actually we get the reward as well there. We don't care about that one, so we just remove that reward. And then we are gonna take path next x, next y, steps, and then we take steps plus equal 1. So you can see how the path is going, right? Boom. And here we have it, right? So we started actually on this point here, and you can see how it moved here until it hit the goal here, right? So it started here, boom, 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 boom. So what it's doing, it is looking up in this state here, and you can take a look at this amazing table here and see how it goes, and just say that it takes the one with the highest value, the action, and it moves accordingly. So it seems actually it's working. At least it ends up in this position here where it should go, and it didn't go other way. It took the minimum path, shortest path most likely, and that's how it should work. And again, just down here, just to notice that in step 3 we could just take random actions and not, I mean, here we take random action once in a while and then we take the best action. But when you train the model, it's okay to take random actions. So that means basically put epsilon to 1. Okay. Perfect. And in step 4 here, normally when you use a model, you will also update the state according to the formula here. We don't do that down here, but you could also do that. So you could learn along the way. So you would actually use exact the same model written down here in step 3 when you explore the world, because sometimes you learn new things, just like the dog, remember? Sometimes you have to try new things. Maybe there's coming something along which you didn't know. Okay? So I hope you liked this journey so far. It's been amazing. So now we looked at reinforcement learning. That was like the second big thing. First we had supervised learning, now reinforcement learning. And then the next one, we're going to do unsupervised learning, right? So unsupervised learning, it is when you don't know anything about what it is, right? You need the algorithm to figure everything out. That seems so amazing, right? It is good for some things and less good for other things. And we're going to dive into that in the next lecture. So are you excited? I hope so. Please remember to hit the like and subscribe and all that kind of stuff. I would love to hear from you. Is this going as you planned? Is it too difficult? Is it too easy? Let me know and I will be happy to help you. So see you in the future. Bye-bye. Unsupervised learning, the third main category of machine learnings. So we covered supervised learning, and in the last one we covered reinforcement learning. I love that one. Check that video out if you didn't do that so far. And in this one, we're gonna dive into unsupervised learning. So if you're new to this series here, this is a 15-part tutorial that will give you everything you need to know in order to get started with machine learning with Python. It is a free online course. Go look in the description, you'll get there, and all the notebooks and everything there it's free available, so go download it and check it out. Okay, so are you ready to get started? Unsupervised learning, what is that? Well, that's what we're going to dive into. But basically said, it is you know nothing about the data. How can an algorithm figure something out which is useful for you? So let's try to do that. See you in the notebook in a moment. So let's dive into it. So here we have our notebook here with unsupervised learning. The goal of the lesson is understand how unsupervised learning is different from supervised learning. I think you already get a pretty good idea. And how to how it can organize data without knowledge, right? So unsupervised learning is often used to how can we make some organization of this mess of data, right? You have a huge load of data. How can we categorize it in a smart way so it's useful? And then we're going to understand how k-means clustering works and train a k-means clustering model. You ready? I hope so. I am. What is unsupervised learning? Given an input data without any additional feedback, learn patterns. It is the third large group of machine learning. Wow. Amazing. I told you already. So clustering. Organize a set of objects into groups in such a way that similar objects tend to be in the same group. So what does that mean, right? Let's look at k-clustering. An algorithm clustering data based on repeatedly assigning points to clusters and updating those clusters' centers. Okay, so imagine you have this data set here. And what it does, it takes two random points, these here, the red ones here and the blue ones here, and then it assigns all to be red, all those data points which are close to be red, and the blue one, it assigns the closest one to be blue. Apparently this one competed and got this one here. Okay, so what does it do? Then it calculates based on that what is the mean value of all the red points, and it moves it a bit. And the same it does for the blue one here. And there's way more blue points down here, so it moves all the way down here. And then it tries again, and then you see suddenly all these are red and all these are blue. And you see this is the idea behind k-means clustering. It's basically taking random points, updating accordingly to the data, and then it learns that those points close to it must be similar, and then it will exclude points that might be more similar to other points in that way. We will make an example data that will demonstrate this pretty well, so don't worry about it. Let's get started. Good. Programming notes. What do we need for this one? We need pandas, numpy, matplotlib, sklearn or scikit-learn, and k-means, the model we want to use in this one here. So let's import all the libraries here. And the first thing I do here is actually I left this code here because it's not really interesting. It is just to generate some data which demonstrate the k-means model pretty well for us. So basically it just takes some random numbers, in this case 400, and then we take the first 100 and shift them by 5 by 5, and shift these here, this next 100 10 by 10, and then the next one 10 by 5, and then the last one 5 by 10. So let's just try to visualize it so you get an idea what it is. So fig axis, plt sub plots, and then we take axis scatter, x equals to data. Oops, it's like this, right? The first we need all the data, and y equals to data colon here, and we don't need any colors. So what we get here is all the data points here. So you see it's kind of grouped in 4 groups, as you see here. That's kind of the point of the data here, right? So it's kind of, you have one centroid here, one centroid here, one centroid here, one centroid here. So we want to try out our k-means model to see if we can figure it out for us. There's a bit problem with this k-mean models. It's pretty amazing actually. So when it has data like this, it will figure it out immediately. But so we need to trick the algorithm a bit just to make it happen. Okay, so let's try to do that. So let's call it k. Yeah, I like to call it just model, right? Model. K-means here, and we need to fill out a lot of arguments for this one here. So let's look at the manual here. And the number of clusters, obviously we need that one. It needs to be 4, right? How many clusters do we need here? We need 4. And what else do we need? Init function, right? So it has something called k-means ++. And the problem with that one is it is way too good to guess just from the first guess. So we need to do something a bit more random. So what it does is the k++ does a really good choice of choosing the points here, so they are actually centroids are pretty accurate from the start. So what we want to do here is actually just to use a random here, where it just chooses random points, and I think it has this random state as well, just for reproducibility if you want to do the exact same as me. So you can use random state 42. And then we have max iterations, and we want to start with 1 iteration because we only want to iterate once, right? Is there anything else we need here? It has what is an init? Number of times the k-means algorithm will be run with different centroid seeds. Okay, so let's do that to 1 also. And init 1, right? So this is the model. We create the model. Now let's fit the model. Fit with our data. Good. And then we want to have the prediction here. Model predict data. So we predict the data here. So here we create the model, we fit the model, we predict the model, and then let's make a axis here. PLT subplots here. Good. And we take axis scatter, and we scatter all the points again here. Data colon comma 0, y equals data colon comma 1, and color equals to y pred, right? And this is actually the data, how it will be colored. So you see here, this is color, but we also want to see actually where the centroid points are, right? We kind of get an idea that 1 point is here, 1 point is here, 1 point is here, and maybe 1 point is here, right? But we want to visualize them, and how do you do that? Yeah, you need to know where they are at, and I forget it as well. So the model, it has something called cluster centers, and we take them 0, y, model, cluster centers, and colon 1. And then we take color red. So here we actually have it, right? And you see it didn't change because we have the same random state up here. If you didn't have the random state, it would probably change to new points. And we only iterated once, right? So this is the first iteration of some initial state here. So they are just random. And again, if I didn't choose this one here to be random, the choice would be amazingly good from the beginning. It's amazing. But for here, we want to see that, see how it works, right? So this is the first iteration, and when we make another iteration, you would see that actually it updates the points. it updated the points, right? You see, actually, it moved a bit, right? You see, now we actually have more points here, and less points here, and less points here, and more point here. And then we can actually go to the third one here. And you see, now it moves a bit more. And the fourth one here. And you see, it moves more. And the fifth one. You see, it moves more, right? And let's not go crazy. Let's go crazy, I mean, 10. So after 10 iterations, maybe a bit less, but after 10 iterations, it has actually found the points in the middle, right? And all it does is in each iteration, it tries to calculate what is the mean value of all the points we're having and moving according to that. So that's how it is, right? So starting from the first iteration here, it was like this. And in the 10th iteration, it's like this, right? And it's only doing that. So it's quite a simple model to understand, actually. I don't know if you thought about it, but there's one question here, right? So let's actually just copy this down here. What if we are working with random data we don't know anything about, but we made one assumption because we knew something about the data here. We knew the data was kind of grouped in 4 groups. Let's try to see what happens if we have 8 groups here, right? It ended up something like this after 10 iterations. And it might be, if we do 100 iterations, it ends up a bit different. Actually, it did not. But never mind. The point is this better? Is this grouping here better with all these 8 points than this one here with 4 points here? What is the best? How many clusters should we make? How do you know that? So luckily there are some amazing people that have done a lot of research on that, and they figure out 2 ways to figure out the most ideal number of clusters. And it's called the elbow and the silhouette method, I think. And we're going to explore that, and we're actually going to explore it on the exact same data set here, because our intuition says 4 points is the ideal, but what if it's actually 8 points? What if that's more ideal? I mean, we see here it doesn't really look ideal to cluster it like that. Our intuitions should be true, but let's see what the science says, right? So are you ready for the project? I hope so. It's gonna be amazing. So see you in a moment. This is a project, and this is going to be amazing. So let me introduce you to the project here, and afterwards you should try to solve it, and then we're going to try to solve it together. Okay, so the project is choosing the right K, right? Or the right K. I mean, and there are 2 widely used methods to get the good value for K, and the one is called the elbow method, and you might wonder why it's called elbow, and it will be clear in a moment, and or when you finish the project, it will be clear. And then there's silhouette coefficient. And we're going to try both of them, and hopefully they will conclude the same thing. And we're going to try it on the data that we introduced in the lecture, because we have a good intuition about that. So the elbow method, it is make a chart of the K different values. And if the line chart resembles an arm, yeah, I have to put it like this, but the arm should be like that. Then the elbow, that's the elbow, is a good indication of the best fit of that point. When you see the chart, it will make sense to you, okay? So what do? Well, we import the library, and then we generate the data, the same set of data we used in the lecture. And then we do it for different K values. So create an empty list and assign it to SSA, sum of squared error. Iterate over K from 1 to 10, both inclusive. Create a model K-means with cluster K. Fit the model with data and append model inertia to the list of SSE. Perfect. Create a plot. Step 4. Create a figure of the axis. Matplotlib. We've done that all the time. And make a plot over the range 1 to 11 and SSE. Right? And then you'll see the elbow and wonder if it is at 4 or something else. Good. Then the silhouette coefficient, a measure of cluster cohesion and separation. It quantifies how well data points fits into a assigned cluster based on two factors: how close the data points is to other points in the cluster, and how far away data points is from points in other clusters. So first we imported is just a library you can use. Perfect. And then you calculate the silhouette coefficients, create an empty list with assigning it to silhouette coefficient, iterate k from 2 to 10, both inclusive, because 1 doesn't make sense because then there's no neighbor, so k for 1 doesn't make sense in this model here. Then create the k-means model with clusters k and fit the data, and calculate the silhouette score of data with model labels and append it to silhouette coefficient. Then plot the result and make a plot of the range 2 to 11 of the silhouette coefficients. And you will be surprised. Okay, are you ready to try this out? I am. I'm waiting impatiently for you to finish it up, and then we can do it together. Looking forward? Okay, see you in a moment. Are you ready? Did you try it out yourself? I hope so. Now we're gonna try it together. If you didn't try it out, please do. It's good practice. Don't worry about it if you don't get it right in the first place. I mean, we've been doing this for many years, so it's a bit easier and looks pretty easy when I do it. And it can be a bit frustrating to see that it looks easy and you think, wow, why didn't I think of that? So don't worry about it. This is about learning, and failure is a learning. So you should just celebrate, clap yourself on the shoulder if you do something wrong, because this is where you learn. If you do everything right, correct the first time, then you often don't think about things. Okay, are you ready? I hope so. The elbow method. Okay, so I already introduced what we're supposed to do, so let's just get straight into it. So the first one is this one. Did you manage that one? I hope so. Then step 2 is generate the data. Did you manage that one? I hope so, because you only had to execute them, and you can see that by the numbers here that you need to execute them. Different k. Okay, so what do we need? Create an empty list and assign it to SSE. Okay, SSE. Boom. Perfect. Iterate over k from 1 to 10, both inclusive. So for k in range 1, 11. Perfect. And create a k-means model. So model k-means and cluster k. Oh, just k, not double. Perfect. And then we have model fit with data. And then score. How was the score? Fit the model, append. Okay, append model in. So there's no score here. Sorry about that. SSE here. Append model inertia to the list. Okay, perfect. And we're done. Perfect. So what it does, it tries all the different k values, and then it kind of takes this inertia and add it to the list. And now the interesting part is to see how this works for a figure. So we make a figure axis to be PLT subplots axis, and we just plot it here, and then we take range, that was range 1.11 and SSE here. Boom. And here you see it, right? So what I told you about this elbow, right? It is, you see it like an arm. I cannot make it here. Arm like that lying down, right? And you see the elbow is this one here, obviously. And it is as 4. So it actually says that clustering with 4 clusters is the ideal according to this model here. So far so good. Our intuition said the same, that this data set was using in 4 clusters. So let's try the next one here. I already introduced it, so just import this one. And then create an empty list. Okay, that was a long name I chose there. Too long for me to write. Good. And then iterate over k for k in range 211. Create a k-means model k-means and clusters k. Fit the model fit data, calculate the silhouette score data, silhouette score, and or on data and model labels, and append it to append it to silhouette coefficients there. I just confused myself. Append score. Perfect. So now that's done. Then we need to plot the result. It's the same thing here. Figure, axis, PLT, sub plots, and axis, plot, range, 2, 11. And then we have silhouette coefficients. Boom. And here you see it, right? So you see the top here is at 4 here. So it also concludes that 4 is the best value of the coefficients. So far so good. Isn't that amazing? I hope so. And this actually ends this project. I hope you enjoyed this one. It's been amazing, and unsupervised learning is often a mind-breaking thing actually, that you can actually do it, and it's so simple and so easy to understand. So if you liked it so far, please like and subscribe to my channel. I would enjoy that, and get some feedback from you. Is this too easy? It's well explained. Should it be explained a bit better? In the next one, we're gonna look into neural networks. And if you just heard a bit about machine learning, neural networks is the thing, right? That is, you need to master that. So the things we've done so far are quite easy, but actually some of them are actually building blocks to neural networks. You need to have this basics on place before we started on neural networks, and it's going to be amazing. I promise you that one. So see you in the future. I'm looking forward to hearing from you. Leave a comment. See you there. Bye-bye. This is the moment I think you've been waiting for, right? Neural networks, or sometimes called artificial neural networks. What is that? If you've read a bit about machine learning, you just probably know that this is the big thing. This is what you need to learn, right? Because the models we tried so far are pretty easy to learn and use. Not said that this is going to be difficult, but you can make a lot of advanced stuff with neural networks. But don't worry, we're going to start slow so you get an understanding of it. If you're new to this series here, well, this is a 15-part series about machine learning with Python. So if you want to check it out, there's a link down there in the description. You can get all the notebooks and everything, the projects we're making. It's going to be amazing. So I hope you will join our journey together, because it is amazing. So let's jump to Jupyter Notebooks and get started with neural networks. So as it says here, well, the official name is probably artificial neural networks, or not probably, it is artificial neural networks, but most people just call it neural networks. So what is it we're going to cover in this lesson here? It is, we're going to understand what neural networks are, and how can you model other machine learning techniques like the ones we already did with this one. And there's something called activation functions here need to consider now. And what about a simple OR function? How can you do that? And different ways to calculate weights. It's often a bit hidden when you look at it the first time. You don't really think about this problem here, but it combines with something called batch sizes and epochs. So let's get started. So what is artificial neural networks? Well, it is trying to simulate biological neural networks that are in brains. And I am not an expert on that subject, so I should not talk about that, but that's kind of the idea behind it. And they're often just called neural networks, as I said. So our first network here, right? You remember our activation function, our hypothesis function that was written something like that. If you didn't follow along, you should check out some of the first videos in the course. It will explain about all this and the math and all that kind of stuff. How can you model that with neural networks? Well, neural networks are kind of like nodes, which are pointed with directions, right? So this node might have some weight on it. these weights are going to be important in understanding neural networks. So nodes here, there will be some entry nodes or input nodes, and in this case we have two input nodes, x1 and x2, x1 and x2, and they will have weight going further, right? So this node has weight w1 and this node has w2, which is related to these functions here. Then the activation function here, or the result of this node here, will be w0, w1, x1, w2, x2, right? So this is exactly modeling our hypothesis function from previously here. Now something called activation functions. So there are a few ones here, and we're not going to cover all of them, but in this one we're going to use the sigmoid here. But there's a step function here, which is 1 if x is greater than 0, else 0, right? We've been using that kind of activation function in a neural network to classify things here previously. There's also the rectified linear unit, which is the max of 0 and x. And then there's sigmoid that we're going to use in this one, and it is 1 over 1 plus exponential of minus x. Okay, so if you want to read a bit more about activation functions, there's a link here, and there's a bunch of them here. I'm not going to go into any of them there. It's for you to enjoy. Yeah? Good. So the first one you want to model is maybe an OR function. You remember OR? OR is 1 if, or here it's 0 if x1 and x1 is 0, else 1, right? So if one of them is 1 or both, one or both is 1, then it's 1. If both are 0, it's 0, right? That's how it says. So how can we model that, right? So here's our neural network. So it takes x1 here and x2 here as input nodes. And then it actually has the weights of 1 here. And then the activation function says -1 plus x1 plus x2, right? So it's not stated here, but it uses a step function here, right? So if it's above 0, we have 1, and below 0, it is 0, right? So first imagine that x1 and x2 are 0. Then we have 0 times 1 is 0, 0 times 1 is 0. So that means x1, x2 are 0, minus 1 is minus 1, minus 1 of the activation function is 0, right? Then imagine x1 is 1, then 1, 1, again becomes 1, and then 0 from here, so it's 1. So it's -1 plus 1, it is 1, and that means actually that we have 1 here, right? And similarly, you can check it for x1 equals 1 and x1, x2, I cannot say it, x2 1 and x1 0, and x1 and x2 1 will also give 1. Good. So just a note here, neural networks are in general can have any number of nodes here, any number of nodes, exit nodes as well, and it can actually be many layers, but we're going to cover that in the next lecture, the next lesson here, and where we're going to talk about deep neural networks. But then in the first place, we only think about these two layers, input layer and an output layer. So, but still, just remember, even though we make some simple things here, we can have any number of input layers and any number of output layers. So you probably wonder, so the big thing here is actually calculating these weights here. So how you configure a neural network is you have some input nodes, then you have some weights that the network needs to calculate, and then you have some activation functions with them. And the big thing is to calculate these weights. I mean, here we constructed it ourselves, but we don't want to put the weights here. We want the algorithm to figure it out. And this becomes a bit more advanced here. And there's something called the gradient descent, which is like the, maybe you could say, one ideal way to do it. And I'm not going to go into what gradients are. You can read about it on Wikipedia here if you want. There's a nice page explaining, and a nice video actually here also explaining somehow how it works, right? You can see the points are moving closer and closer. I'm not going to go into that here. Good. But how to think of gradient is thinking of about if you have some weights and you calculate some new points on it, what is the direction the weights are going? What is the gradient? What is the weight? Which way are they going? Remember those points we just saw in the video of on Wikipedia? What is the direction of the weights, right? So you have some initial weights, and if you do some new calculations, new data points, what is the direction? What is the tendency you're going, right? So how is the gradient descent algorithm works? Well, it's trying to minimize the loss, right? So again, if you had some network, let's just take this one here, and you see, you do the calculations on some points, and you calculate, the loss, how many points were wrong. That's a loss, you can say. You want to minimize that. So that's the point of the algorithm, minimize loss with training neural networks. So how does this work? We start by choosing random weights. So we just, if this was our network, we would add a random weight to each one of them. And then we would repeat the following: the gradient based on all data points direction that will lead to decreasing loss, right? So you basically take all the input data and you have the output, and you see, if I use these weights here, what is the gradient if I calculate it for all the points and try to minimize the loss? And you get some weights, the gradients here, and then you can update the weights based on that. So there's a problem with that algorithm. It's amazing, but the problem is it's very expensive to calculate. So what we often do is like, okay, we need something that works before we end existence on planet Earth. So you need something that's a bit faster. So one of the steps towards that is stochastic gradient descent. So what it does, instead of doing the calculations on all the data points, it only takes it on one data point. So basically, in each iteration it takes one data point and calculates the gradient descent and updates the values based on that. And then it iterates again and again and again and again. And it actually shows out that a compromise even further is often used, which is called a mini-batch instead, mini-batch gradient descent. And what it does, it puts things in small batches. So instead of process all the data, it takes some small portion of the data, and it takes one point and calculates it based on that. And that actually turns out to be pretty nice. Now back to something we know. So perceptron. I had a hard time to say that. Okay, so these are these linear separable decision boundaries. Remember that? That's what this node can do. We can use that in our model, and we'll do that below there. One funny thing about it, it doesn't use XOR function. If you don't know what that is yet, don't worry, we'll cover that later in our lectures. But linear separation cannot make the model the XOR function. It's actually going to be funny to look at that later. Good. So let's get into it. So what we need here is NumPy, Matplotlib, TensorFlow. TensorFlow is a new one here. It's an end-to-end open source machine learning platform. If you want to read a bit more about it, you can see it here. End-to-end open source machine learning platform. And yeah, I'm not going to go into depth there. We're going to use that, and how to make a network. You make sequential, you have an input, and then you have something dense there. So let's get started. Are you ready? I hope so. So the first thing you should do is install TensorFlow. I'm not going to do that here because it's going to make a lot of output here, but you need to execute this one here because by default TensorFlow is not installed in your Anaconda, or at least it didn't used to. So if it is now, maybe it is, I don't know. I cannot predict the future. Good. Then we need to import a lot of libraries here. So as you see here, we have the NumPy, TensorFlow itself, and TensorFlow Keras layers. And Keras layers, input, dense, and sequential we're going to use, and then Matplotlib to visualize, and so forth. So as in the last lesson, we're going to create some data here to make it a bit more, just to see how it works. So I just visualize the data immediately. So you have two groups of data. We added labels on this data because now we are not in unsupervised learning, we are in supervised learning again. And we want to use our neural network. So we have some data points here and some data points here. So this is a quite easy network, but we want to start easy, right? Not network, data set. So we have data points here and data points here, and we want to create some model that optimizes this. So the first thing we do is, as usual, we have the X and Y data. So the X data is the two first columns and the Y data is the last column, right? That's how it's decided. And then we have the xtrain, xtest, and so forth here. Actually, this one is not needed. It's the default value, but let's just leave it there. Good. Then batch size is explained, right? We talked about batch sizes, meaning batch, right? So batch size is a set of samples you do in each iteration. So when you do a batch, it's a specific number of data points that you use. So you also need to think of how many times should I run over all the data, and that's where the epoch comes into the number system, right? So epoch is an arbitrary cutoff, generally defined as one pass over the entire data set. So apparently that's not always the case, but it's something similar to that. Okay, good. So are you ready? Let's try to make our first model here. So model. So what we want to do is we want to model a linear separator like we did already. And doing it with neural network will actually seem a bit more complex than just using the simple thing, but it will teach us how the thinking is behind it. So the first thing you use is a sequential where you build the model inside. So when you have a sequential, you actually just add layers to it like this. And the first layer we're going to add is this dense layer. Oh, not the first. This is the layer we're going to add to it. So dense, I didn't really mention it up here. This is the regular density connected neural network. Just a regular densely connected neural network layer, and that's it. So good, perfect. And what you want to tell this dense layer here is, well, I thought you could get the description of it. Apparently not. So you want the that's a bit awkward. I thought I imported the dense here. I can take dense up here. Good. And dense implements the operations. Okay, so output, we need activation, which is the activation function we're going to use. And what else does it have? Okay, the problem is it doesn't really tell us here, right? So you need to know below what it does. Perfect. Good. So one of the things you need to tell it is what is the output dimension you want, and that's 1. And then you will need to have the input dimension. It doesn't really know it here because it's not really. So it has 2 dimensions input layer, right? So that's what it has. And then we have to set the activation function, and we're going to use this sigmoid in this example here, and that's it. And when you created the model, so this model is only consisting of something similar to this one here, right? This is our model, so it will take 2 sets of data. So don't just ignore these values here. These are the one we're going to calculate. And then we have a different activation function. We're going to use the sigmoid activation function, which is often pretty good at these things. And how do you know that? Well, you just practice and you get some experience. So the next thing is you need to compile your model. And this is also, we're not going to dive into all these things here, but you need to have some loss function. And we're going to take the binary cross and throw, that was spelled wrong, cross and throw P. And you're going to take the optimizer. I mean, this is beyond the scope of this, but these you need to define as well. Oops. Metrics. Accuracy. Perfect. So that's basically creating the model. This is the definition of the model, and you can add any number of layers like here. You start with sequential, then you add layers, and then you compile the model, and then it's ready, right? So model, and now it's something that looks more similar than we used to. We fit, we take X train, Y train, and then we have these epochs that we need. And epochs, let's take, I don't know, 1000? I have no idea. Let's try that, and batch. Batch size is actually set default, I think, to 32, usually, I think. batch size. So batch size none. If or none, batch size will default to 32. But let's just put it here specifically. 32 is often said as a good choice. And you see that's pretty small actually. And verbose, I don't want to have all the output here. So let's fit the model there. And you see it takes a bit time there. And then we actually have the model, and then we want to have the accuracy. So model evaluate. And what do we evaluate? X test with Y test. Okay, perfect. So the accuracy is 100 here. So yeah, 100%. So that's pretty good. But the data set is also quite easy, right? So it's not like surprising that it's like that. Okay, perfect. So let's just check that everything is as it should be. I mean, it says it's 100% accurate. Let's see if it is. So model predict x test. Perfect. And then actually this is a funny thing, and I'll get back to that. Figure axis in a moment. Figure axis PLT subplots, and then we have AX scatter X test. Actually, I just changed my mind. Let's add all the points here, because let's just visualize everything. It doesn't matter if you predict all the point or only the test point. We evaluated it on the test point. It is correct. So let's just visualize all the points here. And the prediction is with the color here, right? So YPRED. And you'll be surprised here first. So let's see why you'll be surprised. Because you see there's actually coloring here. Why is there coloring down here, right? Why is that? Why it's not? It's because we forget that actually our prediction function, activation function, is this sigmoid here. And sigmoid is far up here. Is this one here. And why not just use this one here, up here? Well, because this sigmoid here is actually pretty good at doing these things, and you get a discrete value and not how it's called yeah, good. So how can you change the result, right? So you can actually do that np where, I think it's called, and then say np where it is YPRED equal less than 0.5, and you say that to 0 and 1. So what this and where does, it is it says condition for x and y depending on condition, right? So if this condition here is less than 0.5, put 0, otherwise 1, right? And then you see here now the colors are distinct. Good. And you can also, if we want to make this full map, I like to do that actually. Rand 10,002, I think that's what I usually use. And then we need to change it a bit. And how much do we change it? 14. It depends on the scale here, right? So you have from -2 to 12, so that's around 14 plus, and then you plus 2 by 2, right? Okay, and then we need to y full. You have to take our model and predict x full, right? So we make a full map of this one here, and then we have figure axis PLT sub plots and axis scatter, and we take x equals to x full, the first coordinate, and then y to be x full, and we do that to the second coordinate, and then we have color to be y full, right? And then just for the fun of it, put this alpha here. Perfect here, right? So here again you see the coloring on it here, right? So this is how actually the model is choosing It actually went up to 16 here. That was not the point. I added too much actually. I should actually add -2, right? That's actually what I'm looking for. I was just making it wrong, right? So I added 2, it should be -2 because it goes down to -2. Okay, so here we have it, right? So you see here, this is how it models it in a gradient color. And we can do the same thing here with y full np where, and we take y full less than 0.501, right? And then you get the border here. So this is how I actually divided it. You might think, why not divide it here? Well, we didn't use this other techniques, so it's gonna be fine like that. Okay, isn't that exciting? So big question is, this was kind of like artificial data that we generated. Let's try to use it on some real data and create a simple model to try it out. And what we're gonna do is we're gonna do a project on some real life diabetes results and try to predict if people have diabetes or not based on some metrics. Okay, excited? I hope so. It's gonna be exciting. So I'm gonna introduce the project in one moment. See you there. Are you ready for this project? It's gonna be amazing. Your first neural network on real data. Huh? How's that going for you? So, project neural network. Woo. Diabetes classification. Given a dataset of various metrics, can we predict if a patient has diabetes? Can we? So again, never expect 100% accuracy, especially things like that. There are so many variables like the weather data. You should, if you have 100% accuracy, you overfitted it. Okay. So the first step is to import the libraries, and I hope you manage that. And then we have to read the data, and it's called in files diabetes. Use this one, and I often like to take hit on it afterwards. And then check the data quality. We're gonna check how many are, we tried this before, right? We're gonna check how many is not a number, because you need to figure it out if some data points are missing. And then you check the data types, because maybe some of the data columns there are not numeric or floats. Then we create the data sets. So assign X to the all but the last column, and then Y to the last column. So the last column is probably if the patient has diabetes. And then we create training test set. We also done this before. So we divide it into these sets here using this train test split. And then to the exciting stuff, calculate the average accuracy for 10 runs. So there's actually one thing that you should think about is when you do these things and there's a lot of randomness in it. So sometimes you do calculations and it fits perfectly. So there are many techniques to avoid that, but one of them is, let's try to recalculate the thing with different changes. Set the random seed here, as you see here, and so you can reproduce it. And try to do all these checks here and choices here and see if it fits consistently. So if your model is good. Also remember, if you have a complex model, often they get overfitted, and you'll learn techniques later also how to deal with this. But in the first step here, we just recalculate it for 10 runs. And the purpose of that is to check that it's not just a coincidence we do really well or really bad. So we loop 10 times. We make so first we make an empty list of accuracies, and then we loop 10 times, and then we put a random seed. So in this one here, you need to put the random seed down in the TensorFlow in order to be able to recreate. Then we have the sequential model, right? And then we make the dense layer with input dim 8 because we have 8 and the activation function sigmoid. And then we compile with loss and all these things here. And then we fit the model with epochs. I actually use batch size 100. I don't know why. You can try with 32 afterwards. And then calculate the accuracy with evaluate on test and test Y. And return the second variable as the accuracy, right? Append it to the accuracy, possibly multiplied by 100 if you want it in percentage. Calculate the average value. Perfect. Predict values. Then afterwards, predict all the values in the model on X and make it into class IDs and where, so on, assuming a YPred is predictions. So then we predicted all the values, visualize correct versus incorrect predictions, right? So there will be some which are incorrect, and then we actually calculate the difference here, the real values with the predicted values, and incorrect predictions will be 1 and correct will be 0. Make a scatter plot with the two variables and the correctness and calculation as colors. And there's no help here because this is optional. Okay, are you ready for that? I hope so, because it's going to be exciting to work on this diabetes data and get some experience with this quite simple model. So see you in the moment. So before I see you in a moment, I should also explain you should try this on your own, step by step. If you get stuck, I will help you in the next one. And then when you get unstuck, don't follow me along, try it yourself again. Okay, so see you in a moment. Are you ready for this? I hope you tried it out. Was it difficult? Let me know in the comments down there below, and let's get started. So I introduced the project already, so let's just start executing the first step here and see if we can manage that together. Will you help me? Shift enter. Whoa, I think it's a TensorFlow. Okay, good. Use pandas to read CSV. Data, PD, read CSV. And we take files, diabetes, and let's just take data head here. Good. And let's inspect the data here. Okay, so this data is pretty nice, right? So number of pregnancies, plasma. So it all looks pretty good here, but let's see that in the next one here. And then we have some class variables. 1 is probably diabetes and 0 is not. Okay, so check data for quality, right? So this is data is not sum, and we're pretty loggy here, so all the data points are there. So this is a classical beginners training data set, so you can find it many places available because it's pretty nice to play with, and you will also find people that have fitted it way better than we're gonna make here, because we're gonna make a pretty simple model, so don't worry about that. That's not the purpose of it, right? It's to learn. And so that was one thing, right? Check that there's no non-numbers, so all the numbers are there. The next thing you want to check is probably data D types. And why is that? You want to check that you have numeric values, right? So it's either int or float, because sometimes, even though it looks like numbers here, it can be strings or dates or something, and you don't want to feed that into your model. Good, perfect. Awesome. So create the data sets. So let's do that. Create the data sets. So how can you do that? I think you can do that. X data and iLog. There are many ways to do this. -1. Y data iLog -1, right? So what do I do here? I take all the columns, all the rows, I mean, and then I take all the columns but the last one, and then I take the last column here, right? So here we have it, right? So you can just see here, we have data here, the age, and you can see here, Y is a series, so that's how it works. Good. Let's just clip this one out here. Good, perfect. And then we do this train thing here. Train X, Y. I want to be able to reproduce it, right? So random state 42. You're wondering about why I use 42. Please let me know down in the comments, why is he using 42 all the time? Is he nuts? Okay, perfect. You know the story about 42? No? So check it out. If you Google 42, I actually think you'll figure it out immediately. It's kind of a thing for geeks like you and I. So you should know it. Okay. Create an empty list and assign it to accuracy. Accuracies. That's difficult to spell for me. Loop over I1 to 10 for I in range 10. And then set a random seed. TF random set seed I. It's just to be able to reproduce it. Create a model. Model sequential. Good. Add dense model. Add dense layer. and we should have input dim to be 8, and we have activation to be sigmoid. And actually default value is 1 for the dense model here. I don't know if it, yeah, I have a problem to get this dense model here, but default output is 1, so you don't have to set it like we did in the lecture. Then fit the model, or now compile the model, compile, and we need all this here. I think I got a space too much in the beginning here, yeah. And again, we're not going to go into these things so far. And then we fit the model, fit. And what do we fit it with? Fit the model. We fit it with X train, Y train. And then we do all these here. Perfect. Model and evaluate. And we take the accuracy is the second return argument is accuracy. So model, evaluate, and we take X test, Y test here. Good, and then we take accuracies and append it with accuracy, and let's just multiply by 100. Perfect, and yeah, let's just run that. Okay, that was not happy. And what does it say? It says missing 1 required units. Okay, actually it didn't take it as a default. I apologize for the victims. It's the first one here. Perfect. Actually I should update that. Where is it? Input. Add a dense layer with 1 exit node. Okay, so it actually says there in the text, it says 1 exit node. That's the first one. So that's the first argument here. I was just too fast there. I actually thought it took it as default 1, but no. I'm learning along with you, so happy for that. And you can see here it running. It should be running 10 times. 1, 2, 3, 4, 5, 6, 7. So it takes a few seconds there. And then afterwards we need to calculate the average accuracy. So how do you do that? You take the sum of accuracies. It's not done yet. It is done now. Accuracies. The sum of them and divided by the length of accuracies, right? And then you have 75. Is that good or bad? I don't know. It's probably not the best out there, but it's a starting point. It means that we guess right in 75% of the, on average, 75, right? And you can actually see the numbers, accuracies down here. So sometimes a bit lower, a bit higher. So this is the result of the model. And you can play around with epochs and batch sizes, maybe 32 instead. And epochs, I mean, the higher it goes, the more it goes over it, the slower it becomes, obviously also. So you can play around with that. Good. And predict all the values with model on X. Okay. Y pred model predict X. Okay. Make it into a class IDs with num. Okay. Y pred np where y pred less than 0.5 comma 0.1. Perfect. So now we have all the prediction. And so yeah, you can see that it's just a list of these things here, and it should be the same as this one here or closer. It's not the same. I'll reveal that to you because there are some mistakes. 25% mistake. So the next one here we need to do is actually visualize the correct versus incorrect predictions. So let's do that. So what do they differ? So we're actually just mapping the ones that are correct and incorrect. So let's do that. Actually, I don't want to type in all these things here. Okay, and then we make a figure, axis, PLT, plots, and then we take axis, scatter, and now we have to remember that actually the X here is a data frame. And let's take the body mass index, and for Y, I don't know what to take, the H, and then we take the color to be the differ, and then alpha 2.25. Okay, so what is it we see here? So first of all, this is not the prediction of whether you have a BMI or diabetes or not. These are the ones that we predicted correctly and incorrectly. So you can see where our algorithm does really well. It seems to be down in this area we do really well. So this is where people have low BMI and the age is young, right? So the old, it could actually probably be like this right here. So our model is pretty good at predicting that when you have low BMI, it's pretty accurate, and also when you're young. So it seems like the age is also a high influence on it, right? While you get older, it's more difficult. Older and BMI goes up, it's difficult for our model to predict. I mean, this is just visually, so it's probably a bit premature to conclude anything here, but this is just a way you can see how is a model actually doing, and are there areas we're doing well and are there areas we are not so good at, right? So this is teaching you to visualization is a really great way to get an idea of what's happening in the model. Okay, so I hope you enjoyed this one here because it's really fun. I highly advise you to try to play around with the parameters. You can Google also about this diabetes datasets. You will find it many places and get great ideas on what to do next. But if you're curious, then continue this journey with me because we're going to build more advanced things. So in the next video, we're going to go into deep neural networks. Deep ones, the DNN, right? The big thing, right? So that's going to be exciting. And what is that? Well, deep neural networks is when you add multiple layers in them, multiple layers. I hope you enjoyed it so far. Please let me know, comment down below, subscribe, and and like this video. I would appreciate that. So see you in the next video. Bye-bye. Are you ready? Deep neural networks. You've been waiting for this one, I know. DNN. We covered a lot so far, and today we're gonna kind of combine a lot of the work we've been doing into these deep neural networks. If you're new to this series here, this is a 15-part tutorial or 15-part course on machine learning with Python. If you want to get started and follow along, there's a link down below there. You'll describe everything for you. You can get all the notebooks and everything we're using in this course. So join with us and let's get started. So deep neural networks, right? The DNN, the thing we have been waiting for. So what is the goal? Well, first of all, it is to understand what is deep neural networks. I mean, we already talked about neural networks in the last part of this series here. So what is it and what makes it different and why it's so powerful? Well, we'll explore that. How algorithms calculate weights for the DNN, right? We already talked about it for neural networks, but it becomes a bit more complex now. And actually, I will show you some tools how to get an understanding what is this DNN and what problems they can solve. Remember, just a small teaser here, remember the XOR function? We're going to explore that one because that's one of the things that neural networks cannot solve for you. Okay. Perfectly. So let's get started. What is deep neural networks? DNN. The adjective, the deep in the deep neural network refers to that we have multiple layers. Remember in the other networks we had like input layer and an output layer. Here we have hidden layers as they're called. And there's no real definition on how many layers you should have to call it a hidden or a deep neural network, but I think the common thing is to say 2 or more. So you have 2 or more hidden layers, then it's called a deep neural networks. Also, if you want to read more about it, there's a link to Wikipedia. I think actually that's a quite good source. Some people like Wikipedia's descriptions and some don't. They can be a bit difficult to understand sometimes when you start out from scratch. Good. So how do we calculate the weights? Because deep neural networks, or DNN, work the same way as neural networks. So we have these nodes here, the input nodes here, and there'll be weights along the way as well as with a activation function. But we need to calculate weights now for multiple layers here, right? So we need weights for all these edges here, and all these edges there, and all these edges there. And again, there can be multiple layers, and the more nodes you have in between here, you can have 10, 20, 100, thousands of nodes here. You need weights for each node to the other. And how do you calculate that? So remember what we did in the first one, right? It was quite not difficult, but you needed to kind of make a lot of calculations. So it's going to be the same here. So how does the algorithm work here, right? So you use a concept called back propagation. So how does it work, right? This is for training to find the weights of the hidden layers, which might not be trivial. So what do you do? So again, like the other one, you start with some random edge values. You just add some random values to these edges, and that's it. That's the first choice. Then you do like the other one, you repeat, you calculate error of the output layer. So you say, okay, so you have this loss function often called, and that's kind of the error, and you calculate the value of that. Then for each layer, starting with the output layer, you propagate error back one layer and update weights, right? So you take what is the error between these layers, and then you update backwards. So that's basically what it does. And again, we have the same problem all the time. It is overfitting. You fit too close to training data, and it doesn't generalize well. So in this one here, we are going to introduce one concept which is commonly used in deep neural networks because they're so complex, and suddenly you'd have no idea what's happening inside the neural network. So what we're going to do is something called dropout technique. So what is it? So imagine actually we have this network here, and we train and we train and we train it. And there might be, you get too dependent on some nodes. What does that mean? That means that the weights are really, really high to this node, and other nodes are really not helping that much. So what you do is actually you drop out nodes. What does it mean? So you remove some random nodes, right? You remove this node and you remove this node, and then you run again and update the weights, and then you add them again afterwards, and then you remove some other set of nodes. So that's what the dropout means. You remove some nodes, and there's some values of how much to drop out. I mean, it can be 20 to 50%. I mean, you can play around with it. And again, for small networks like I'm illustrating here, it might not make sense to have this dropout, because if you drop out one node out of two, then you only have one node left, right? So it's more like when you have like big networks where they're large and complex, then this dropout makes sense. So actually the examples we're using here, maybe the dropout is not ideal, but we will use it just to demonstrate it. Dropout at each layer of the network has shown good results, right? So it's again one thing that maybe surprised me a bit about machine learning. So it's not, I mean, it's a lot of trial and error. You just try what works and doesn't work. And in the end, it's not like you cannot prove scientifically that this is the optimal way to do it. You can try a lot of things and get some experience. That's also what people pay for, experience. And if you're really interested in this dropout thing here, there's actually a link to the original paper that describes it. So if you're a bit scientific and you really want to dive into it, read it. If you don't understand it, don't worry about it. You just need to understand what it does and why it is a good idea to have dropout in huge, large, deep neural networks. So one thing I find funny, or not funny, it is funny. It is to play around with this playground here, TensorFlow.org. So the funny thing is, if you have no hidden, remember we talked about this XOR function, and it's still confusing. Don't worry, in a moment it will not be confusing anymore. You cannot, without hidden layers, make the XOR function. What does that mean? We'll get there. Let's click on this one. And I advise you highly to play around with this thing here. So what is this? This is a playground. So again, like we have played with our things here, we have some output data where we have two classes of data classification, right? First, we're going to try a simple classification problem like this one, where we have all the class nodes on this side and the other class on this side here. So they are together, right? So it's going to be an easy network. So if we remove all the hidden layers in our network, so we only have two input layers and the output layer here, well, this will go really well because this is a linear distinction between the two values. So this is pretty easy for it, and we need no hidden layers. Okay. So there's no need to make a more complex network for these things, and we have models for this. We tried to do this already with linear regression, so it's all okay. So this is the XOR. What do I mean by XOR, right? So look at this. This is a really interesting network because we have the class blue here and here, and the orange here and here. So this is called the XOR function because basically it's a 0 to 0 is 0, 0 to 1 is 1, 1 to 0 is 1, 1 to 1 is 0. So it has class 0 here and here, and class 1 here and here. And this is a complex one. You cannot, with this here, you cannot solve it. As you see here, nothing happens over here. This is, the colors are not changing here when you run it here. This is the run it, you have the epochs here, and you have activation functions. We're not going to dive into these things here. This is classification problem, right? And learning rate and activation function. Let's leave it there. You can play around with that yourself. But the key thing is when you run it here, when you train the network, nothing happens. While when you had this classification problem here, where it's simple, it immediately, when you run it here, you immediately find that it classifies everything on this side here to blue and everything on this side to orange. And this actually classifies it perfectly. It has 0 loss. Okay, so let's go back to our function here. So what can we do? Well, one thing we can do is add hidden layers. So let's start by trying to hit 3 hidden layers. Let's try 4 instead. It's gonna be fun. So what we see here, it actually takes a bit of time here, but boom, it does solve it. And this is actually quite interesting to look at because actually see the weights on these networks indicated by the thickness of the lines here. So you can see actually the blue ones here are taking over, and then this orange layer, and then the blue and a lot of orange down here, and so on. So you can see the colors, but it does succeed with loss of 0. Okay, so this is fine. That means we can make this XOR function here with 4 hidden layers with 2 nodes on each layer. Let's try it with 3 instead. And we'll see that actually, hopefully it should be able to solve it. It seems like here, let's try to refresh it and try it again. I think usually it can solve it. Maybe I'm wrong. It seems like it's difficult for it to solve it now, right? And you see, again here you get overly dependent on specific layers here and less dependent on other nodes here. So it seems like, okay, I actually thought it was able to solve it. Let's try it once more. I'm probably wrong. It seems like I'm wrong. So you cannot solve this one with 3 hidden layers with 2 neurons each, or nodes. And another thing to notice is if you want to investigate each of the nodes, you can just hover your mouse above here and you can see how it is, how it does it, right? So again, this gives you an understanding of how this works. Okay, perfect. So if we have 3 hidden layers, maybe we add 4 nodes here. So let's try that and refresh that and see how it works. So see, if we add additional nodes here in the beginning, we can actually solve the problem of it. Again, perfectly. So with 3 hidden layers and 4 nodes here and 2 nodes here and 2 nodes here is possible. I'm not gonna go into more. Let's just try to remove 1 layer here and see how it goes now. And actually this goes fine too. So actually, and actually see this node here doesn't really add anything. So it should actually be possible to, no, it's actually not possible because you need the last node here. My mistake again. And let's see how this is so funny to explore around with. Okay, you see it's more evenly weighted now. So this is one way to solve it, and now I advise you to go in here and play around with it. It's really, really fun. And there are other models here. And actually, if you want to go into regression models instead, you can do that as well. You see they changed over here. So it's different things that we're trying to solve here. And you kind of get an idea of how it works. And you can change the activation function. You can change the learning rate as you want, the number of hidden layers, the number of they call them neurons here. I usually call them nodes. Maybe I'm out of fashion. So it's fun. Try it out. It's a lot of fun. And the link is here in this ebook here or notebook here. And remember, you can download them all from the GitHub. There's a link down in the description. So let's get started and try to play around with this. So in this one here, we have some programming notes here. We're going to use the pandas, NumPy, Matplotlib, sklearn, and TensorFlow. And if you didn't install TensorFlow, that was in the last one, you can see how to install it on your Anaconda notebook. And you can see some lectures here on the material if you want. Other things we're going to use is read CSV, train since test split. We're going to use a sequential, dense, and dropout. Perfect. And if you want to read more about them there. Perfect. Let's get started. So what did we do? We imported it all, and then we're gonna have the data here. And we're gonna take the PD, read CSV, and let me remember it's called XOR, right? XOR CSV. And I think actually that's what we need to do. Let's just investigate the data here. Yeah, this is perfect, right? So you have some X coordinate and Y coordinate, and then you have a class ID. Let's try to visualize this immediately just to see if this is what we expect it is. So PLT subplots and AX scatter. We take X to be, oh, sorry about this. This is me being a bit confused here in the morning. X to be X and Y to be data Y. And then we have color to be data. It's called class ID. Okay, perfect. So here we have it, right? So this looks pretty good, right? This is exactly what we expect. It's uniformly distributed points, and it is XOR function. You see there are probably going to be a bit difficulties here on the edges, but other than that, it should be possible to do it. So far, so good. So I like that we do some training and testing data so we can do some classification. And how is that? We use this test split. So let's say train is called train. And train X test, Y train, Y test, and then we call train test split. We have data, and what is it? We take X, we take Y, and then we do data, and we take class ID, right? And then we take. Should we do anything here? Let's for the sake of it, let's take random state. Random state equals to 42. Perfect. So now we have splitted up the data, and we're actually ready to go. So let's get started. So what do we want to do here? Well, we want to explore kind of the idea what we did last time. And so remember, one of the things we did is to rerun the networks, because how this works is it is initializing the things by random values. So sometimes when you don't run so big, you want to rerun it a couple of times just to make sure it's not the random freakish random values that makes it bad or good. So I make this list of accuracies of it, and then we're gonna for I in range, and I'm only gonna do 5 iterations there because we're not gonna wait forever, but you can do multiple iterations to make it more better. And then we actually just make our model here. So the model, again, remember, is sequentials. And then for the first, we're just going to add a dense model. And we have a one output node here, an input dimension. It doesn't remember this. Input dimension 2, and activation. We're going to use relo. Good. And that's basically the first model that we're going to use here. So again, model, we're going to compile it. And again, we're going to use a loss function here. We're not binary cross entropy. And we optimize here. And metrics, the list of accuracy. Perfect. And then take model fit, and we take x train, y train, and epochs. We take 100, and batch size, it is the default 32, but we just add it here for if you want to change it, because it's one of those parameters you can play around with. So verbose is just so it doesn't print that much. And then we want the accuracy here. From the model, we do evaluate, and we do the x test, y test. And then we add the accuracies, append accuracy. Let's just multiply by 100 to get it in percentages. Doesn't make sense, I don't know. Accuracies, and divided by the length of accuracies. So the funny thing here is that this doesn't compile because we probably misspelled something here. Compile, invalid keyword argument in compile, optimize optimizer, it's called. There you go. Thank you for helping. Good. So the funny thing here, this will be really, really bad. And why will it be really bad? Well, because you cannot fit it, remember? So this is only one node. It takes 2 input and 1 output, and it doesn't work. So what you get here is 50-something% accuracy. Is this expected? Yeah, I think so, because you can capture a bit more than half maybe, but better than that, it's difficult. So this is expected. This is what we already explored. So let's try to add some more, right? So one thing we can do is add similar layers here. And let's do that actually. And we end with this sigmoid. And we take the relo here, and we take, let's take, was it 6? I don't remember the values. We take something here. And then we actually try this one instead. I think this is overdone. It should probably fit pretty good. And again, you see here, it's almost close to 100%. Here it's actually 100. So this is why we take the averages. So averages is 99% here. So this is pretty good, right? Pretty good. And if you play around with this, maybe it's high epochs here, then you'll get 100. You can play around with it. And I think you can lower the number of nodes also. Actually, I shouldn't have these activations here, input. I don't know if it got confused about that. It shouldn't have these. I think it's going to be the same actually, but apparently it ignores it when it is defined here. It should ignore it. Okay, so why do I get new results here? It's because we do randomness in here, right? So if you want to be able to reproduce these, you should take TensorFlow, random, set seed, and let's just set it to I. You need to set it to something different every time, otherwise it will not be the same. So the advantage of doing this here, it is you will get the same results each and every time, right? So if I rerun this one, I'll get the same. So it's 99.1. Okay, perfect. And what about this dropout? How does that work, right? Well, basically you just add a dropout here. I would be surprised actually if it does better now, because we have such a little network. We just take 20% dropout. So let's try that and see. It's probably going to do worse because the network is so tiny, right? So don't expect this to do better. Look, it goes here. One is already 90 here, and 73, right? So this is way worse. But why is it that? Because if you drop out some of the nodes, you basically remove the main part of the nodes, and it's going to be affecting it too much. Good. Perfect. So this here, I advise you try to play around with it. I would take out these here in the beginning because these networks are so small. Now we're going to try something with another data set. So let's call it dirty so I don't call it data, so we can distinguish. No, I'm going to override the values anyway. So never mind. I like to call it data. Data PD read CSV, and we have files XOR, and you saw there was one dirty, and then we call, let's just look at the data here, and you see this is the same kind of data, but when we visualize it, so fig axis PLT subplots, we do axis scatter x data x y data y color data data class ID. Perfect there. So here you see what's the difference here. The difference is this is a bit more complex network because we have it's dirty, right? So it's not clear lines. If you played around with this one up here, I'm pretty sure you can get 100%. So it's not a problem to fit this network perfectly. But this one here is more realistic. And this is, again, if you get 100%, or in this one here, you are ensured that you overfitted it. Because that's not supposed to be, because there's supposed to be some randomness in it, and you cannot predict everything. Again, good. So let's try actually. So now I actually did it pretty nice. I can just copy this one to get the same things down here. So now I have the network here, and actually I think we're not gonna do repeated things. But if you want to do the same as me, random set seed, let's just set a seed here to 42 so you can reproduce the exact same thing I'm doing here. Otherwise you'll get different results. So model sequential. And what are we going to do? Well, let's play a bit around with it. Model, so we add dense, and we're gonna add way more here, 20 nodes for instance, and the input dimension is 2 still, and activation is, we use this ReLU. Good. And model add dense, let's do 20, activation ReLU, and model add dense 1, activation sigmoid. Okay, perfect. And actually we just need to do the same thing here. We need to compile the model and get the accuracy here. Oh, actually we don't need to print add it there. Let's just see here. Let's just accuracy here. Perfect. So what's happening here? We are just running through one time here. We actually get 92%. I'm actually kind of surprised. This is actually okay. Let's try to have some dropout in this one just to compare with the other one. So 92%, is this good? I mean, it's difficult to say because you and I, we know we're not going to fit it 100% because there's so many outliers here. And let's take and add dropout to our model and see how it goes. Let's run it again and see how it goes. Actually, it's quite the same, right? 92 point something. So it's pretty nice. Okay, so I'm not gonna do more about this one here. We are gonna go to the project in a moment here, but I highly advise you to play around with this, try something different and see how it goes. And let me know in the comments how high score you can get. And this one here, is it good to get insanely high score? I wouldn't say so. What is the limit? I don't know. You need to make some estimates on that before. We know this is an XOR function. Ideally, it's just dirty. So let's leave it at that. Okay, perfect. So in the project, we're gonna look at banknotes. What? Yeah. So you do some measurements on banknotes to check if they're fraud or not. And we're gonna look at measurements, the metrics of that, and see if we can make a model that can predict if a banknote is fraud. Wow, is that exciting? I think so. So see you in a moment. Exciting. This project, we're gonna do deep neural networks, and we're gonna do it on banknotes. Okay, let's dive into it. So identify false banknotes. That's the goal, right? How do we do that? Well, follow along here. So we import libraries, like always, and then we read our files, banknotes here. And you might be curious, what's in this one? Well, you can always snoop around here and look at the files here and look at the banknotes here, and you see, okay, it's just a bunch of data. So it has done some measurements: variance, skewness, kurtosis, entropy, and then the class, if it's false or not, right? So based on these measurements that you can do, somehow, I cannot, you can probably, I cannot, you get kind of, we want to be able to predict if it's false or not. So investigate the data, right? So this is what we're going to do here. I just make a peek preview there, and then you have to use unique. I think here it should not say link. Where did that link come from here? Okay, perfect. Unique here, and then if you want to read about it, what does it do? Well, it finds all the what does it do? It finds unique. We need to check if it has unique values, right? Perfect. And then you need to say check for missing data and investigate that. Then we need to divide data into features, vectors, and labels. So this is basically makes the X and makes the Y. We've done that many times. And then we split X and Y with this here. I'm actually a bit evil here. I didn't write an X train X test, so you have to write it yourself. And we use test size on 0.4. And then we create and compile the model. We use a dense 8 and a dense 1 output node with sigmoid and activation and compile, and then you do that. And fit for accuracy, accuracy. I wish I could talk better. And we do that with epochs 20 and verbose 2 for some reason. And then afterwards, we're going to add another hidden layer to see if we can do better. And I don't say which hidden layer, just add a hidden layer. Be creative and play around with it. That's what I find which is funny about this. Okay, so are you ready with this? I hope so. So get started. Try to do as long as you can. Hopefully you do it all. Afterwards, check out. Maybe I would do it a bit different. So let's see how we can do it together afterwards. So see you in a moment. Bye-bye. Did you try it out yourself? If you didn't, please pause the video, try to solve, try to do this. This is how you learn. And don't worry about if you're failing or not being able to figure it out. It's not failing, it's learning. This is where you learn the most. Trust me, I've been programming for my entire life. And the times where I didn't figure it out immediately, those are the times I learned the most. So it's not like figuring out the first try. It's not going to make you a good programmer because you need challenges. Okay, so let's get started. I already introduced it, so let's import the libraries. We do that by Shift-Enter. Are you comfortable about that? If you followed along, I know you are, but if this is the first video, don't worry about it. Good. Then we want to read the data. So let's call the data here, pd read CSV, and it's files, banknotes, and as always, just take a head here so we can see, investigate the data here, right? So this looks pretty like it should, I guess. So next step, investigate the data. We want to check how many classes that's here, how many classes are there. So what you want, you could use unique, right? So let's try to do that. So data, we actually only want to do it on a class probably. So unique. Oh, unique. Oh, it's just because it's a bit slow sometimes. So here you see you only have classes 1 and 0. And this is exactly here. So it's just to make sure that you are not, there might be another number or class 3, class 4. So just to be sure that we understand the data correct, right? And the next thing is check for missing data. So one way to do that is data, it is ISNA and sum of that, because you can sum over true statements. So if all return false, you will get 0 here, which is exactly what you have. So this is a perfect data set. So in real life, it's most of the time not perfect. So please be aware of that. So when you work, it is a good habit to do this. I know we've been doing this in this series here, and it seems like most of the time there's not missing data, except with weather data. Remember that one we started with? There was a lot of missing data. Good. And we actually explored a bit what you can do. The simple thing is just to skip it. Divide data into features, feature vectors, and labels. So I actually don't think we used this terminology before, but features is like the data we're gonna fit on, and the labels are the things we want to figure out with our model. Good. So x is equal to data, ilog, and we take everything, and then we take everything except the last one, and y is data ilog, and we take the last one here, right? There are multiple ways to do this. If you did it in a different way, where you made a list of, I don't know, maybe you did that, it's fine, don't worry about it. So let's just investigate it here. Head here, it looks like this is all the data we need here, and we can just add another one here and say y head here, and we see this is a series with the classes here, right? So this is exactly what we want. So far so good. And this one here, if you did it differently, don't worry about it. This is one way to do it, and it can be a bit confusing at first. What does all this mean here? So this first ilog is integer location in the rows, and the colon here is basically taking every single row, and then we go to the columns and we take the list of columns, all except the last row, last column. And then on this one we do the same, except we only, instead of take everything up to the last one, we take the last one. It's negative indexing. Good. Perfect. Create training and test datasets. Oh, I was so mean here. I should have written this out. Train x test. Oh, test. It goes really well here. Y train, y test, and then we have this train test split, and we take x and y, and then we take test size 0.4, and let's take something called random state 42. And the reason I didn't add this one here, but again, if you want to follow along exactly with me, if you have some problems, it's a good idea to put this random state here. If you don't, you will get some other results, right? I explained that in a previous lecture. So if you want to dive into understanding this, please go back and start all over if you didn't. Perfect. Create and compile the model. So let's try that. So model. Actually, also just to make I don't know if I actually included that. I probably didn't. I didn't. So I cannot do that. So here you will get different results. Don't worry about that. Here, sequentials. So what is it that we want to do? We want to add a model in the dense here, and we take 8 here. We take input dimension to be 4 because we have 4 rows, and activation to be this ReLU here. Perfect. And then we take model, add dense with 1, and activation, it is equal to sigmoid. Perfect. And then we want to model compile, and yeah, let's just copy all this stuff here. I think that's all we need to do here, right? Perfectly. Then we need to fit it here. So let's try to fit it here. Of course, we have to write model fit. And what do we need to fit? Fit train, y train, and then epochs 20. We could also put batch sizes and all that kind of stuff. And model evaluate and x test, y test, and just a bit less verbose. And you see here, why did I do that? It was just to print out a bit more. You can change this to 0 if you don't want that much output. But then you can actually see how the model follows along here, right? You can see the accuracy, how it changes. It's actually pretty good, 98. So the accuracy ends at a 98, actually 0.5 on the test data. On the actual data, it was 98.3. So this is pretty good. And if you want, of course, you can play around with the model up here, but we're not going to do that. Here, we're going to add another layer in our model and try it out. So how to do that is just copying this down here. And yeah, let's add the extra layer here. How many should we put in there? 4. Yeah, let's actually add 4 here, and ReLU here, and then we compile the model, and then we actually try the accuracy here. And you see here we actually get 100%. Pretty good, right? I don't know if this is realistic. I think actually on this data set it is realistic to have 100% because detecting this should not be a big problem as far as I know. There's been a lot of, I guess there have been used a lot of resources to figure out which metrics to measure here, and it has high accuracy. So I think actually it's might be, maybe you know more about it than I do, but I think actually it might be realistic to have 100% down there. So I wouldn't be worried about it. It's also a very small model. It's not overly complex, so I wouldn't be worried about that. Wow, wasn't that great, huh? So if you like this thing, and if you like this, especially this lesson here, please let me know below in the comments. Please let me know if you found it a bit difficult. If there's something about deep neural networks you don't understand, please feel free to ask. I'll try to reply it. So in the next one, we're going to look into convolutional neural networks. And what is that? Well, when you want neural networks to work on images, for instance, you need to do some tricks down the sleeve. And you'll know why in the next one, because it's gonna be too many input nodes if you don't prepare the data for it. And it kind of makes sense when you see it. So if you can't wait, please remember to like this one, subscribe, and all that kind of things, because the next one is gonna be amazing. We're gonna work with images. Like the first thing we do is digit recognition. So if hidden handwritten letters is one of these classic data sets that are out there that everybody works on. So you need to do that as well to get some experience. So see you there. It's gonna be amazing. Bye-bye. Convolutional neural networks. This is exciting, right? So in the last lesson, we covered deep neural networks, and it was amazing what that could accomplish. So what is the next step, you might think? Well, what if you're working with images, pictures, and you want to extract information out of them? What is the challenge then? How do you do that? Well, this is where convolutional neural networks come into the picture, or CNN, and you don't want to miss out on that. So, welcome to this lecture. So, if you're new to this series, don't worry about it. There's a link down below in the description where you can find all the information. There'll be 15 lectures, all prepared with notebooks you can download from my GitHub. And yeah, follow along and learn with us together. So we will jump into our Jupyter Notebook right now and get started. So see you there. So convolutional neural networks, CNN. The goal of the lesson is obviously to understand this CNN thing and the strength of CNN. What is it they can do for us? And how to detect handwriting. So you already see down there. I mean, we're going to use that as our first pilot project, or what you call it. And the next one we're going to do in the project today is going to be really, really amazing. So what we want to do is figure out how do you actually extract features from pictures and learn convolution, pooling, and flatten. What is that? And how to create a CNN, or convolutional neural network. Perfect. So are you ready for the next one here? I think so. Computer vision, what is that? Computational method for analyzing, understanding digital images, right? So that's basically, for instance, down here, there's a handwritten detection. It is how do you actually extract information of these handwritten letters and figure out that that's a 0 and this one is a 1 and 2 and 3 and so forth. How do you do that? Well, machine learning to the rescue, and CNN in particular. Good. So that's basically one of the goals of computer vision. It is how do you actually extract information from the pictures that you're looking for. So one naive approach would be something like this, right? Just create a big neural network that for each pixel would have an input node and take it as an input. Whoa, you think. In these cases, maybe that is actually possible, because how many pixels are there? 28 by 28. But you also realize that's still going to be an enormous neural network. And will it be accurate? Maybe, maybe not. But there's maybe one thing you want to think about. So this is how that would work, right? It would have an enormous, probably way bigger than this one, number of input nodes, and then you have the hidden layers along here, and then the output nodes here. There should probably be 10 here, because one for each possible digit there. But when you think about images, actually there's something you might think, well, you're actually not interested in each pixel by itself. You're more like, when you look at it, you're looking at a bigger level. You don't analyze what's inside this pixel here when you realize this is a 2. If there was a small gray tone here, a tiny gray tone here, you wouldn't care. So what you're really looking for is more like the features in the images, not the details, right? So this is where image convolution come into the picture. It's applying a filter that adds each pixel value of an image of its neighbors, weighted according to a kernel matrix. Okay, that sounds so crazy you can't understand it. But basically said is, for each region of pixels, for instance here, you would look at the neighbors and calculate a value based on this pixel and the neighbors. What this does is actually makes it's a filter that makes the image. You probably know that from your iPhone or your smartphone, right? You sit there and you put filters on and it changes. Some makes it more blurry and some makes it more sharp and so on. So let's just try a image convolution here. So how do we do that? So in this first part here, we're only going to explore that. So this is what we're going to do here. For instance, if you looked at the image, sometimes you're not really interested in the overall thing, you're maybe mostly interested in the edge detection. And what is that? Don't worry, we'll see it in a moment. So for this, we're going to use this Python image library. Don't worry so much about it. This is really not about it. This part is just to visualize it. So let's just try to run this code to make it. So we have a picture of a Doberman here, and you convert that. This is not about this, so let's just execute this code. But the funny part is here, we use this kernel here, and it has size 3 by 3. And this kernel subtracts the values multiplied by 1. So it subtracts the values of the 3 top pixels and from the side pixel, and then it multiplied by 8 by 8 center pixel, subtracts, and the bottom 3 subtracts here. So it's like, actually it's a 3 by 3 matrix. This is the size, but it's just given as one vector here. So don't worry about that. But let's see the result, right? So if you look at the original image first, let's do that actually. You see this is a Doberman, a beautiful, beautiful picture of a Doberman. But if your computer is supposed to process something, so figure out that this is a Doberman, what is it interested in? Is it interested in that it has brown tones here, it's grass in the background? Is it interested in that? No, actually not. So applying this simple filter here will result in this image here. And you see here, actually, this is just a very, very simple filter. And you see, actually, you can actually still see it's a dog. And actually, you could actually probably also, if you know dogs, realize this is a Doberman. Amazing, right? So what this does is actually removes a lot of unnecessary information and keeps parts that are necessary in order to detect what's in the image. So this is the idea with image convolution. It is extracting only necessary information and put out away all the information you don't care about. And just think about it. This simple little matrix here, represented as a vector, I know, can actually convert this image to this image. And you still have a lot of information, enough information in it to figure out it's a dog, it's a Doberman. Wow, that's amazing, right? So that's the idea about image convolution. We're going to introduce a few more concepts here. One of them is called pooling. It is reducing the size of the input by sampling from regions in the input. Basically reducing the size of the image, right? So as you see here, if you have a big image like this one, maybe actually if you have a smaller one, you will still realize it's a dog, right? You can reduce the size. So that's basically what pooling is about. And max pooling is just one technique, which is like it takes the maximum value of each region. So like for instance, you took a region like this, you just take the maximum value from that region and then you downsize by that. And that has shown to be an effective way to do it. And does it work on everything? No, probably not, but it works for what we're going to do here. So what is it convolutional network is? Well, it's a neural network that uses convolution for analyzing images. So let's look at the idea here. Idea of CNN, input image. This is actually this scale here, that's our image. It could be the Doberman. Then you do some convolution, and you can actually do multiple convolutions to get the features out of the image that you want, right? So you apply convolution, possible several to get features of the image, right? So you get this feature image out here. And then you do pooling, right? It's actually reduces the input, right? And you could also do multiple times. And what it does, you can see each these here is representing a pixel, and here you have like kind of less pixel there, bigger, so it's a less information, right? So it reduces the amount of information, right? If you pull too much, obviously it will be too little information left, but the balance is to find the right balance of convolution, get the features. Then when you get the features, you get the pooling, you reduce the size, and then you flatten it. Flatten means you just put it into a one-dimensional array here to all the input, to the input, how's it called? The input nodes of our classical neural network, possibly a deep neural network, right? So you get the idea. You take the image, you make some convolution where you get some features, you reduce the size, you flatten it. Perfect. Wow, this is going to be amazing. I know it. So programming notes, we're going to use TensorFlow. That's actually all we're going to use today. I'm surprised. If you didn't install TensorFlow so far, go back, I think 2 lessons, and I will show you how to install it in your Jupyter Notebook. It is not installed by default, at least not the version I'm using. Maybe in the future they have it. And what are we going to use? We're going to use a lot of things here. We're going to use categorical. And basically what it does, it is converts these values. In this case, we're going to have digits like 0 to 10. Or 0 to 9 actually, and it converts it so it's not a digit, it's a vector. I actually think they have an example here. Yeah, exactly here. So here you see you have 0, 1, 2, 3, and we will have numbers up until 9, and it converts it to a vector, right? So this is the first vector representing 0, this is representing 1, representing 2, representing 3, right? So it represents that vectors. And why do we do that? Well, you need it in order to use the models. That's sometimes how it is. You need to put the data as it wants the data, right? And then we have a sequential, we create the model, then we have dense, dropout, like we know. Then we have this conv2, which is a new one, which is basically making the convolutions of our network. And then we have max pooling that I talked about there. It's going to do the max pooling. And then we have the flatten that we also talked about. It's going to do the flattening. Oh, you're smart. I know you knew that. Good. So let's get started. So you probably wondered about one thing, and that was actually this data set here. This is a classical data set, and it's called the MNIST database. And actually, maybe this should have been in a link, but you can actually read about it. It's a classical data set that has a lot of handwriting here. It was I don't think it's a challenge anymore because it's been solved so many times. But back in the days when machine learning was in an infinite state, it was struggling. It was one of the big goals to detect handwriting. But everybody on their journey needs to do that. So how do you get the data? You get it like that. And if it's not downloaded, it will download it to you by pressing this one. So this is actually getting the data, right? Maybe it actually does it in the load data. I don't remember if this one is downloading it the first time you do it or this one is doing it. But it divides data into train data and test data like this. So that's how it does it. So let's see if it does anything. No. So yeah, it will download the data if you don't have the data, and I don't remember how big the data set is. It's probably taking up some space, but if you want to work with machine learning, you need to have some space on your laptop or computer. Perfect, so far. So now we have train data, and let's just, oh, where did I go? Here, xtrain, shape. You can see here you have 60,000 28 by 28 images, and you should have the same amount of labels, shape, and let's just take everything now. Y test shape. Okay, perfect here. So you see here you have 60,000 of 28 by 28 images. You have the labels, which is also 60,000, and then you have 10,000 test images, which are also 28 by 28, and then you have 10,000 labels for the test images. So it is in all perfect shape here. And let's just, for the fun of it, let's just see an image that it is like it is. And I don't know, let's just make it, if you want to try something else, you just put an index for fun here, and then we take the image here. And the image here is from the Python image library above there. And you need to take it from an array here. Oh, that was index. So you take the image out of the index. You need to take it from an array because they're represented like an array here. And let's just print, oh, how is it? Y train index, because you want to see if it is the correct index. And then you have display image here. Okay, perfect. So what you see here for this image, for the third one, it is a 1. It prints 1 here, and this is a 1 by the label. You can try something else here, right? So you get a 4 here and 4 here, and you see that. So that's how the images are. These are 28 by 28 pixels. So there you go. Perfect. Awesome. So the first thing you want to do is the values in these images. Let's actually just try to take a look at that. I know it's 28 by 28. The values are numbers, integers from 0 to 255. Okay? So what you want to do is you want to normalize it into interval from 0 to 1. How do you do that? Well, let's try to do that here. Xtrain. You can actually do it simultaneously here. I don't want to do that actually. So you'd say Xtrain divided by 255.0. Why do I put 0.0? Because you want it as a float. Xtest to Xtest divided by 255.0. Some people like to put spaces here. Originally, I don't think you should do that, but most people actually do that nowadays in these notebooks. So let's just follow along. Okay, so this is the test, and this is test now the images. So we scale them down to a value between 0 and 1. That's what it does. Okay, and now the labels. Remember we talked about this categorical. We need to do that as well. So let's do that on the labels. Train to categorical, Y train, and we do Y test to categorical, Y test. Good. So now we transform them into that. Okay. So actually, if you remember the shape here, then you take Y train, shape. You see here now we have vectors of 10 instead of just a single value. Remember, it was representing from a vector representing the number, right? So it's a 0 vector with 1 on the place of what it is representing. So this is the first step, and then we need to reshape actually these, if we take the train here, we need to, it's also a bit annoying, but that's how it does it. We need to have an additional dimension on this one. So we need to reshape that. Xtrain and Xtrain, dot reshape, and then we need the entire train shape 0. Doesn't go well. And then we need to do this of 1, 2, and then we add this dimension here. And we need to do this again for X test, reshape, X test, and just copy this. Copy this. Did I do it correct above? Yeah, good. So, what did I do? Oh, I forgot the shape here, right? Shape. Thank you for correcting that. It's, we can get so excited and you get so fast and then you do these mistakes. But thank you, you can help me along here. Good. So now we prepared the data as it should be, and yeah, you can just see a train shape now, that now we have this additional dimension here that the model needs. Okay, so are you ready? So model, now we need to use a model, sequential, and this is not me who found this model here. I'm just taking one model here, and you can play around with it afterwards if you find a better idea. So the idea here is you take you basically take 32 internal nodes, and you make this for 3x3 matrix, and activation, we use a relu, and input shape is, it's here 28 by 28 by 1. Right, we have this one extra dimension here, and I think we lost a parenthesis here. Boom. How did I know that? It's because it didn't align there. Model, add, and what do we add? We add a max pooling, 2D, and a pool size you add there, 2 by 2, perfect. And model, add, flatten. And what do you flatten? You just flatten. Okay, perfect. Model, add, dense, and you take the 128 apparently, and activation, relu. Okay, and then take model, add. I'm gonna be a bit extreme here. 50% dropout is a bigger one. Model, add, dense, and we take 10 now because we have 10 ones now, right? Activation, we use a soft max here. Good. That's basically our model. So what do we do? Model compile. And what do we do? Right, optimizer. Oh, and loss categorical cross entropy, and metrics. We have this list accuracy, and then take model fit x. Oh, we didn't have capital X anymore. X train, Y train, epochs 10, and model evaluate. Okay, perfect. And we take X test obviously, and Y test here. Perfect. So this is gonna take a few seconds here, but again, I didn't create this model here myself here. I was just, somebody had done a lot of work, and if you're interested in it, you can actually check on the Wikipedia page and see actually there are a lot of interesting approaches. I actually think they have links to a lot of things. So this is a table of some of the machine learning method used on the dataset and their error rates by type of classifier, right? So linear classifier, you can see that the error rate is 7.6. So this is done only by linear classifier. And then k-nearest, actually that's pretty amazing, right? 0.5% error with k-nearest. We used that one. That's pretty amazing. I'm kind of surprised, right? And remember support vector, and that's also 0.5 here. Deep neural network, it's 1.6. And again, convolutional, like we're doing here, and there are different limitation, right? 6 layer, 13 layer. So you can actually look at these here, how they're done. And there should be some links to them somewhere, I guess. Also figure it out, and you see convolutional, it has a pretty awesome score. Almost perfect, right? And of course, you are not getting perfect because with handwriting, even sometimes when I'm writing with my hand, sometimes it's not perfect. It becomes not readable for myself. I sometimes write something and it's just like, wow, how can I read that? I'm so embarrassed about myself. Okay, so we're getting close to this one here. And again, you saw the results on Wikipedia, and they it seems like the state of the art is trying to do a 6-layer or 13-layer to get these kind of scores. So with 6 layers, you can do that properly on your machine and try to play around with that. See if you can figure out a way to do that exactly, and so forth here. So now we're almost in the end here, and I'm pretty excited about it. And you see already here, I mean, we could probably end it a bit before, because actually the accuracy is pretty high and it's not really improving that much anymore. It's tiny improvements, right? So isn't that exciting? So what it did, it said, okay, so in the training set, it reached around 99%. And in the test set, as you see, it is not as good as the training set. It's very close. So there you go, 98.7%. So that's a loss of 1.3%. And we're looking at Wikipedia, 1.3. That's actually, I mean, these are state of the arts, right? So that's pretty good. But an interesting thing could actually use k-nearest neighbors, right? And a support vector machine. That's also pretty amazing. So amazing. I hope you enjoyed this, because in the project we're going to do something similar, but we're going to try to classify birds and planes instead. Yeah, you heard right. Birds and planes. They both fly in the air. And it's going to be a still picture, so you cannot see if the wings are going like that or are still. So it's going to be amazing. You will enjoy that, I promise you. So see you there in a moment. So are you ready for this? So this project is going to be amazing. We're going to look at birds and planes and so much more, actually. So what is it we're going to do in this project? Well, we're going to look at this dataset called CIFAR 10 dataset. And why is it called that? It's because it has 10 different categories of images. So it's a large image dataset of 32 by 32 color images of 10 classes, right? And there are 50,000 training and 10,000 test images. So there are airplanes and birds, as I said, and also cars, cats, deer, dog, frog, horse, ship, and truck. So are you excited? I think so. This is gonna be so amazing. So the first thing you need to do is just to import the libraries, then download it, execute this cell down here, and then we'll load the data. Then we need to normalize the data. So here you want to have the class names of the labels, and it's basically to take the names, which you have here, and usernames conversion, right? So you have a class name, you have an integer, and then you train a label, the index here, right? So you can show an image like that, because the data doesn't have these names here, but you want to be able to see the names, right? So it's taking the integers to a index. Okay, and then we create the model here, and again here I just give a model. It's not me who invented this model. I'm not an expert in these things, but it has the things we've been working with. It has convolutional networks and max pooling, convolution again, max pooling, conversion, and flatten, and then it has 2 dense layers, and then we just try to compile it with this stuff here, and perfectly. And then we train the model. So we train it with these parameters here, or use it on fit, and then we test the model to try it. All right, and finally, optionally, you can try to improve on the model. There's probably also a lot of things you can look at on the internet and get some great ideas on how to improve this one. So don't feel shy about that. It is how you learn, you explore. And yeah, are you ready? I think so. Let's get started. Or you should get started and then follow along when you get stuck. See you in a moment. Are you ready to try it along with me? Well, did you try it yourself? Please let me know in the comments. What was your score? Please let me know. It's going to be amazing. Remember, it's not a competition to have 100% accuracy, but it is fun. Okay, so let's get started here. So let's execute the first 2 cells here. This one, importing the libraries, and then this one here to download it. And if you don't have it downloaded already, it will probably show that it's downloading down below here, but I already did that, so it's fine. And then we need to normalize the images just like we did in the class or lesson. So let's do that. Train images, it is equal to train images divided by 255 0, and test images equals to test images divided by 255.0. So that's basically what you want to do. Then you map the images into the interval from 0 to 1. And then we get the class names, and basically what you need to do is actually to copy this one here down here. Then you have like all the class names so you can look them up. And how do you do that? Well, you actually can, yeah, let's make an example here. Index 0, let's just take the first one, and then you basically you can get the class name here, and actually you can show the image here of this one, and you see train image is not defined. I call it train images. Perfect. Class name is not class names. It goes pretty well. And just for the purpose of it, let's just change it here. Class names, train images. Perfect. So now you see it here, and this is a frog. So you can see that from the class names, this should be a frog, and from and you can try another image here and see that this is a truck, right? So basically it's just to explore the data set, and yeah, this is how you can use it, right? So if you didn't have this class names here, you wouldn't be able to get the name of it, right? This is what it does here. Perfect. Awesome. So create the model, and this is funny. Model, sequential. See, didn't I import the sequential model? No, I didn't. So apologies for this model. Sequential. It's called models. Sequentials. Oops. So I have a model there, add, and then in the layers we have conv 2D here, and we have 32, and then we add this piece to the equation here, and then we take model, add layers, and then we have the max pooling max pooling 2D. And what do we add here? 2 by 2. Good. And then we take model, add layers, and we take conv 2D and 64. And this one here. Rilla. Shouldn't be Relu. I don't know why it's Rilla here. Relu. I can see I have mistyped here. I'll just perfect here. And then model, add layers, max pooling 2D. And it's 2 by 2. Perfect. Model, add layers. What do we have? Another conv 2D. And we have 64 again. 64 again. And then we have 3 by 3. Oh. 3 by 3 here. And then we have model, add layers, flatten. And this one here, I'll just flatten, and then we have model, add dense 64, and we have input dim for activation relu, and then we have model add dense 10 the output node. Okay, awesome. And then we need to, model add dense 10, and then we need model compile, and we need to compile it with all this piece here. Okay, so it's gonna be a bit exciting to see if everything is fine. Okay, we also didn't have dense here. It's just me being a bit sloppy here. Layers. I mean, in the other ones I had it included up there. And what does it say here? It says input. Okay, I have a P there, and there you go. Perfect. So you see, when you type this many things here, it happens that you mistype. Don't worry about it. It happens for me apparently. Good. So model fit, and then we have train images, train labels, epochs, and then we have validation data set here. Perfect. And 10 epochs is probably going to take some time here. So well, let's see how it goes. And other than that, we're probably going to fast forward on this one here, so you don't hear me sit here waiting with me. See you in a moment when it fast forwards. Perfect. So now it's done, right? Perfect, amazingly. So what's the next thing? So let's try to try to make some predictions. So let's try to do that. Index equals to 0. Yeah, first of all, I forgot the first step here, right? To try to assign that. So let's do that first. So ypred is equal to model predict, and it has test images. Yeah, perfect. So we have predicted, and then let's try to see some results here. And we had this one here. Remember what we did up there? Yeah. And class names ypred index argmax. Okay, this is probably a bit tricky to figure out. So it predicted this one to be a cat. I would say it's a cat too. It's a bit difficult to see actually, but yeah. Automobile. So this one is wrong, right? And this one is ship. That looks like a ship, yeah. And this one is an airplane. Yeah, that actually is an airplane. Okay, so you see how it's not 100% accurate. It says, what was the accuracy score? It was like 78 here. So that's one that actually has a validation accuracy here at 70%, right? So remember, it had, I didn't actually emphasize that, but in our, where did we do it here? We actually put validation data as our test images and test labels inside the model layer. We've not done that before, and I forgot to mention that. So what it does, it actually, as you see, it calculates the accuracy on the train data, and then it actually does it on the validation data again, right? So it has a wow, that goes well, accuracy score on that as well, right? Perfect. So yeah, we get our accuracy score on our validation here actually to be 70%. So that is not that good, but we can actually add it here as well. Let's just, so how do you do model evaluate, and we have the so it is test images and test labels, and let's just verbose 0. So you see here, it ends up at 70% as it's said here. And the last step here, try to play around with it, with the model, try to improve the score. And the reason why I don't want to do that is you saw how long it took to execute here, so I'm not going to play around with it here. This is some model here. Doesn't seem like this is a perfect model, but it also remember, this is not an easy problem to solve. I mean, there are a lot of images, and you saw the quality of the images also. Apparently, it is good enough to have a 70% precision on it. So there you go. I hope you enjoyed this one. In the next lesson, we're actually going to do quite similar to the same, but we're going to use a different framework, the PyTorch. And some people, they devote their life to say this is way better. It's basically also made for Python. So some say, well, it is more aligned with how you code in Python than this TensorFlow is. So that is actually, we're going to do some of the same things here, and with PyTorch instead. It's going to be exciting. If you like this one here, and please let me know what kind of scores you got. It's going to be exciting. I mean, here we got 70% on the validation test set, and let me know below there how much you got when you played around with it. It's going to be exciting. And please remember, if you enjoyed this, like, subscribe to my channel, and see you in the next one where we are going to explore PyTorch. It's going to be amazing. See you there. PyTorch. In this lesson of machine learning with Python, we're going to explore PyTorch. Actually, we're going to do quite similar work to what we did with TensorFlow in the last lesson, because in that way you kind of can compare the two frameworks, because basically they do kind of the same thing, but some people divide their life to PyTorch, others say TensorFlow. I'm not the judge of that. That should be your judgment. So let me know in the comments below if you find it easier to work with PyTorch than it is with TensorFlow. And of course, this is only one dimension. It's also about what information is available about it, how easy is it for you to start with it. So let me know down there. If you're new to this series, this is a 15-part journey with machine learning for Python. If you want to get all the notebooks that I'm using here and the projects, please look below. There's a link and you will get started immediately. So without anything, let's dive into the Jupyter Notebook and let's get started. PyTorch. So let's see what the goal of the lesson is. What is it? Actually, was a bit about this one, PyTorch versus TensorFlow. Well, it's not that simple to say that, but let's get a high-level understanding of that and how to get started with that and work with image classification like we did in the last lesson, and it's going to be amazing. So one great thing about PyTorch is actually they provide a free book that you can just read and download. Apparently it takes a few seconds here. Yeah, here. Deep Learning with PyTorch, and it's from their official page here. So if you want to get started with it, it has amazing deep dive book, and I think it's actually worth reading, and I read some of it, and it's amazing. Perfect. So if you want to really get serious about PyTorch, that's a great resource. I'll just say some of the examples are not perfect in it. You need to modify them a bit in order to get them to work. But other than that, it is fine. But it's fine, yeah. So this is a bit more controversial. I said versus in the subject up there, but let's just say TensorFlow or PyTorch and TensorFlow. Well, they are the most popular deep learning frameworks out there. So whether you use PyTorch or TensorFlow, it really doesn't matter. If you are getting good at one of them, I think you're good to go. PyTorch was released by Facebook AI Research Lab in 2016 and TensorFlow in 2015 by Google Brain Team. I think if you look at the history online, it seems like this PyTorch was not as good in the beginning, and the development speed of of TensorFlow was faster, so it was providing better frameworks, but it seems like PyTorch is basically on the same level now. So I think in general it's a matter of taste, what you like the best. They're both good choices for deep learning, so don't worry too much if you don't feel that PyTorch is for you or you don't feel like TensorFlow is for you. Basically choose what you want. So the first thing is obviously you have to install it, and we'll do that down below here, or show you the command you have to press in order to do that. So don't worry about that. It's not this, it's not part of the Anaconda, at least not when I made these recordings. Maybe it is in the future, so then it is. But it doesn't hurt to install it on top. It will not do anything crazy. So PyTorch comes with a long list of prepared datasets. You can actually see them all here. They have quite some sets there, and that's one of the things that is amazing with these things, right? So if you want to start playing with machine learning, it's a great choice to have a framework which provides training datasets for you so you can become better. So we're going to explore the same two again, right? This handwritten dataset, I love that one because it's so funny, because this is just one of the things, first things you want to do with machine learning is these simple things, and then this dataset here with all the images here. And actually here you have some scores. We didn't really explore this web page, this wiki page in the last one, and you can see kind of the error rates. I think we ended with 70%, so that's an error rate around 30%. So it's pretty far to go from us, right? But again, these are probably also taking. You saw how long it took to calculate our CNN network, so I was not optimizing for that. Okay, so the great thing about this here is you use this Torch Vision to have the datasets, and if I didn't click so hard, it wouldn't happen. Never mind. So we have this Torch Vision with these datasets, and you set a data path, that is where it will download it to, and then it will ask if it is trained data or not. So it's like the test data or the trained data, and yes. So one of the things that you first notice is that, okay, so you get all the data, but it's kind of in the raw format, so you need to transform and normalize it. And it's actually quite funny because you can do that immediately when you import images, but you need to kind of investigate it first, right? So it has these, the first step is to make it to Tensor, which is like the format that it's using. So it turns NumPy and these Python images to Tensor, and then we need to normalize it. We do that by mean and standard deviation. I'll show you down below there, don't worry about it. And then we can apply the transform normalize, which takes the mean and the standard deviation with it. Okay. So in this one here, we're going to explore the MNIST dataset with the handwritten digit recognition dataset. And we're going to use this network here, which I didn't create myself. It's just taking some network. And it's a bit more advanced than the other one. And so it might take longer. I don't know, actually. I'm kind of curious about this too myself, because will it be too long to make this network? Because so the input layer here is 784. You might wonder why. And remember the old one, we actually made some big compromises on that, the other network. We had a way smaller input layer. And then we have the hidden layers of 128, 64, and an output layer of 10, which is categorizing, which we have. So when we have defined the model, so here's the working process. First we transform and normalize. When we define this model here, then we have we will use the optimizer here, and then it is code like this. I just copied the code in here because I don't really think it's benefiting to sit here and realize what this code is doing. I mean, you can read the code here. You have the optimizer here, then you have the loss function you define, and then how many epochs. So you define all these things here outside in Python, while in TensorFlow, you just add them as arguments. And yeah, is one way to do it. And then we have the optimizer and batch size, output, and you mean the loss function, loss backwards, and optimize steps, and so on. And then you get the values here. And this is how you do it. And then you test the model. And I also don't think there's anything special in this. So again, I just copied code in here. We're just going to copy paste it and we use it. Okay, good. The libraries there. This is a long list, right? So we have Torch. This is PyTorch. This is machine learning framework. And then we have Torch Vision. That's test data, for instance, and then we use Matplotlib to visualize something, and we have a lecture here if you want to explore a bit more about it. We have the datasets. We have 2Tensor normalized that I talked about when we read the datasets, and then we need Compose to have a multiple of these, and then we have data loader in order to prepare the data, sequential, linear, ReLU, log softmask, GD is like the gradient descent. We actually talked about that earlier, remember, in a previous lecture. And then we have the negative log likelihood loss function we're going to use. Okay. So if this is the first time you run it, you need to install Torch and Torch Vision. You can do that by only installing Torch Vision because it will automatically install Torch. So all you need to do is run this cell here. I'm not going to do it because it's going to write a lot of things, but you need to run this cell here and it will install Torch Vision and Torch for you. Good. And then we execute this one here. And then we are gonna download the images. So it's gonna put data in downloads and it's gonna put all this data here. And it's gonna first have the MNIST, and then it has validation data or test data, right? And you actually get it to see how it works here. So it is downloading, and then there should be a folder here with the data here, right? So this is the downloads I added, and here we have it here. Perfect. Awesome. Amazing. So now we have the data sets here in this MNIST. So let's just try to explore one of them. Image label of MNIST. Let's just take whatever, and then we have a label here, and it's labeled 0. And what is labeled 0? Well, we have MNIST, and we have classes. That's a classes, and then we just put label there, and it is a 0. So it's going to be interesting to see if this is really it. Now can we watch this one here? PLT. I know I'm a bit sloppy with these thing here. Image show here, and then we take the image, and then we take CMap to be gray. And why do I do that? Because it's grayscale image, otherwise it will be colorful. And you see this is a 0. Amazing, right? So the key thing here is that this is actually a grayscale image, and it's a we want to convert it into these tensors as I talked about up here. Remember, we needed to make these transformation. So the first one is transform to tensor. So let's actually try to do that. So basically, this is kind of what is a bit, if you ask me, a bit funny, because you actually need to copy it again. Okay, so let's just leave out the validation because we actually don't need that. And then we actually say we don't need to download it again because we have it already. And then we need transform. And then we need transforms to tensor. Perfect. So you add this to the list here, and yeah, let's execute that. And then we have these to be tensors instead. And we're not going to explore that, but what we're going to get now is we're going to take all the images out because we need to calculate this. Remember, we need to calculate the normalization, and we need to find the mean. I double click on that again. We need to find the mean and the standard deviation. And how do we do that? We use functions to do that for us, but we need all the images by that. And then we need list comprehension to do that. So image t for image t comma underscore in minist. I actually shouldn't have done this. I should have called it something different, but I overwrote the previous variable. It doesn't matter. Now I did it. And that's that one. And we need to use torch, stack, and dim 3 here. Perfect. So now we have all the images in here, and we flatten them, or we took out the labels. And what we can do now, so torch stack is just as it says here, concatenate a sequence of tensors along a new dimension, right? So that's what it does. Perfect. And now we can actually take a view here, 1.-1, and take the mean value of dimension 1, because it's one-dimensional images, and we get this value here. And then we take image view 1, -1, and we take the standard deviation of dimension 1. Okay, perfect. What did it say? It's because I didn't put an S here, right? Perfect. So now we have these things here, and now we can read the data sets again. And let's do that. So we take this one here. Now we have to add a bit here to this one. And now we need to make this transform compose that I talked about. Transforms compose. And it takes a list, and we just add this one. And transforms normalize, and normalize takes first this one, and then it takes this one here, and right, and I think we're losing a parenthesis or something here, isn't it? Yes. So, and we need to get the validation data as well normalized. And remember here, I do the normalization calculation on the training data only, and not on the validation data. So, false, well. Perfect. So now I have the transformed and normalized it to these data sets here. Okay, so far so good. And what is next? Well, we need to create this one here. Wow. Can I really remember all that? No. So I just put it down here, so we can see it together, right? And what do I need? So actually the input size, let's just put it in a variable here, to 784. And why is that? You might ask. Well, what is 28 times 28? Isn't that the image size? The image size is 28 by 28. Didn't we have that somewhere? We actually didn't put that out anywhere, but we remember that is the case. So that's the input size. And then we have the hidden size. And it's 128. And why do I put it in a list? It's actually just for convenience, so I don't have to type it multiple times. And then output size is 10. Okay, perfect. And then we make a model here, and we add that to be NN sequential. And then we actually added argument by argument to it. So we have this linear layer here, and it takes input size and it takes hidden sizes, because you need to. So here's one difference, right? So in what's called in TensorFlow, it figures it out itself, right? Here you need to put all the what's called output sizes between the layers as well. So this is a difference, and honestly, I don't know what is better. I mean, then you feel kind of the framework should be able to figure this one out itself, I would say, but it doesn't. So in my opinion, you have to do a bit more work in this one here. That's okay. And then we have the softmax here, and it was actually the log softmax, and it takes dimension 1 here. Okay, perfect. So this is actually our model. So far so good. And it says requiring one positional argument, out features. Oh yeah, I actually forgot that here. And output size. Perfect. So this is it, right? So let's just explore here. We have this input size of 784. Then we have the second layer here, which is 128, and output 64, input 64, output size 10, and then we have this log softmax, which reduces it to 1 here. And this is our model. And let's just move this one up again. Then we should have optimized the model there. And here again, I'm just gonna, not again, here I'm gonna copy it. Let's hope everything is correct. And loss function, name target is not defined. Okay, so let's think, what line was that? It was 15, it was loss output target. It actually labels, so there's a misspelling there. Perfect. So let's just correct that up here so it is correct for you. Labels. Perfect. Awesome here. And now it's gonna run, right? So for each iteration, we made 10 iterations. That's a lot. We are going to see how it works here. And maybe I should have done less iterations, but now that's what we did. And let's see how it goes. And then afterwards, we will compare it to the results of the validation data. So it's a different network also, we have to remember that, but this network is quite larger than the one we had in the other one. So I would expect it to do better, but we'll see when we run this test here, where we actually calculate the accuracy. Okay, so 6 here. So soon it's done, and then we can run this cell down here below to get the accuracy. And it's actually quite funny how the loss function, it went down there and went up again here, and then it goes down again here. So in a moment here, it's very exciting and actually quite fast here when you think about how big the network is. I'm kind of surprised. I was like, wow, 10? Did I really put 10 iterations? And actually, it ends on 9, obviously, because it was up to 10, so now it's done. So are you ready to get the accuracy? And again, we have val loader. Oh, actually, I forgot. Did I forget? Yeah, so we need the values. So I have this train loader here. We need similar here to have some validation, right? And this is for val here. Perfect. So accuracy 96%. That's amazing, right? So the other one, it was 70% accuracy, and here we have 96%. That is amazing, right? That's pretty amazing. So the network was quite larger, and I must say it went pretty fast. That's pretty good. I don't say the other one was a masterpiece of a network, but this one surely beats this surely beats it, both with speed and accuracy. Oh, actually, I forget. I mean, we were comparing it to the... I'm actually wrong. So first of all, I was a bit wrong there because I confused it with the test we did on the other data sets. This CIFAR here. Where is it? Here. And that was the one we had accuracy of 70%. This one we had 90. I think we had pretty similar result to this one here, and actually that was way faster. Actually, I think the result was a bit bigger, so maybe this network isn't particularly good. I remember the other one to be way smaller and way more accurate. So there's some things to think about there. Maybe you should try to make the other network we did in the other one in this one here, and try it out to see if you get similar results. And of course, you don't get the exact same result because of the randomness involved in it. So, are you ready? In the project, we're gonna try to figure out if it's a plane or a bird. So let's get ready for that one. See you in a moment. Bye-bye. Are you ready for this project? It's going to be amazing because now we're going to try to use PyTorch on our dataset of CIFAR. So let's try to do that. So if you didn't do it when we played around, you still need to install PyTorch and Torch Vision, or Torch and Torch Vision. You do that by executing install this pipe, how it's called, !pip install Torch Vision. It will install both of them. If you did already, you don't need to do that. Then you need to import the libraries here, and then we need to download the dataset. It will be done here. The first dataset and the validation dataset. Then we're going to explore it. We're going to look at the type of CIFAR and the length of CIFAR, assign an image to a label and a label of CIFAR at index 10 or 1000, and get the class name of the label by doing like this here. Okay, like we did in the lesson. It's just to explore it a bit. Then you visualize it, and you can use Matplotlib to visualize the image. Just use this one as I did in the lecture. It's going to be fine. And here you don't need to do this CMap because this is color image, so you don't need to do that. Transform the images, remember, then we did this transform with the 2Tensor in order to do that, and we need to do that before we can normalize it, because we need to get the mean value and the standard deviation in order to do that. And then we need to you have all the images transformed in this one here, Tensor CIFAR 10, and then you need to stack them again, and you use a list comprehension like you did in the lecture, and then you calculate mean and standard deviation, and you'll see that these will be three-dimensional values, and you need to copy those as well. Then we need to normalize the data, just like we did there, and in order to both do 2Tensor and normalize, we need to use this composer like we did in the lecture. And yes, we have two tuples. Now it takes two tuples, not single values like we had in the lesson. It's tuples of 3. And you will see that. And then you have to do that on this dataset and on the validation dataset. Then we're going to limit it because, again, remember last project we did, it took really long to run it. So I limited this to only have birds and planes. It's 0 and 2. And then we use list comprehension in order to limit the dataset to only have these things there. You will see in a moment. You just follow along there. And then we create the model. It's going to be a very simple model. I mean, in the lesson here, we had a quite complex model to identify handwritten digits, and it didn't really perform amazingly well comparing to the simple one we had with the TensorFlow. And by the way, did you try out to take the one from TensorFlow and transform it into here and see how it went? Please let me know in the comments. It will be really nice to hear that. So we have a more simple one here. So we take linear, ton, and linear, and log softmax here. And it's going to be interesting to see how that performs. Then we train the model. So we have here, we do the train loader here. We do this trick here, not trick, but we need to put it in batches. And then we have the learning rate, and then we optimize here, choose the optimize in the loss function, and then we train the data here. And then we test the data here. It's basically just copy paste this down here and run it. And then the fun part here, right? So I'm not going to show you these things here, but try to improve on the model, because I took a really simple model here, and there's a great potential to improve it. And some simple things you can do: adjust the learning rate, run more epochs, a number of hidden nodes, and change the activation function, add another layer, and so on. Advanced thing, let your imagination guide you. Wow. And you can see some of the results here for inspiration. Probably you can see there are links to the resources here. So these results here, let them guide you. And finally, add more classes, right? So we only focused on airplanes and birds. Try to add more, one or more, and play around with that. This is how you learn, right? So amazing. Are you ready? So let's get started, or you should get started and go as far as you can, and then I'll help you, or we'll do it together. Please help me, because I sometimes type wrong, you know that, and it's really nice that you can help me with that. So see you in a moment or some minutes. See you. Bye. Are you ready? Did you manage? What was it difficult? Let me know in the comments below, and it's always nice to hear from you guys. So let's start by this one here, right? I already installed it, so I'm not going to execute this one, but if you need to install it, it's Shift Enter to install it, to execute that cell, and you need to mark it like I'm doing here. This is also just execute, Shift Enter, and then it's installed, and then we need to download the datasets here. And you see here, bam, 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 it needs to download it. And actually, this is a bit bigger than the other one, so you can see it takes a bit longer to download it. I'm kind of surprised how slow it is, actually. But never mind. And then it has extracting it. Perfect. Files already downloaded and verified. Perfect. So now we need to explore the dataset. So we have this CIFAR 10 here. So let's see the type of it. Type CIFAR 10. Perfect. So you see it is a Torch Vision dataset CIFAR 10. So it is a internal size, internal type CIFAR, but you have a length on it. It's 50,000, and as far as I remember, it is 10,000 the other one. So you have 50,000 images and 10,000 test images. And then what does it say? Assign image and label to CIFAR 10,000. So image, label, and you take CIFAR 10,000 here. And now we need a few extra cells here. There you go. And then it says to get the class name, use this one here. So let's see the class name here. It's a truck. It's a truck. So that's actually all we needed to do here. I didn't need that many extra cells here. But let's visualize the image. You can use this one here, as it says, and we just add image in there. And you see this actually looks like a truck, as you can see. This looks like a truck, if you ask me. So it seems like their labels could be accurate. Transform, right? And now we need to add this transform to reading the images. And this is basically this line here where you need to add the transform download false, and then we add this one here. Good. And transforms, okay, thank you. No, which one is transform? This one is transforms, right? Boom, that's how it is. I apologize for this. I just corrected immediately, so you will not have the same mistake here. So you will not have the same mistake. Perfect. So now we actually we converted the Python images to PyTorch, right? Perfect. Now we need to normalize it, and in order to do that, remember we needed to. So here it assumes it's called Tensor Cipher 10. I didn't do that. I called it Cipher 10 here. So I'm just going to be a bit different, or maybe we just added here and I overwritten the other one. It's kind of silly, but now it's there. Now you have all the images transformed in Tensor Cipher 10. So it doesn't say you have to do that over here, but that's okay. Then you can concatenate them like this. So remember, it had images, and then it had torch stack, and what it took was this comprehension, image t for image t underscore in Tensor Cipher. I think that's basically all, and then we have dimension 3 here, right? And that should actually do the trick. So it actually takes a few seconds in order to do that. Perfect. And then we have all the images, and it was called view on the 3 minus 1 and mean dimension 1. Then we have this one here, and then we have images view 3 minus 1 standard deviation dimension 1. Okay, perfect. So now we have the values we're going to use down below here, and look, the difference is here that now we actually have a value for each layer in our frames or images, right? Before we had a grayscale image, so there's only one layer. Now we have red, blue, green, or which I always forget. We have 3 layers of the colors, right? So we have a value for each layer. So normalize the data. So this again, we need to do something similar to this one here. We copy it down here, but now we need this transform here, and remember we need transforms compose transforms normalize, and now we need these layers here, the mean value, and standard deviation here. And I hope everything went well here. And as you can see, I made the same mistakes here. It should be transforms. Okay, perfect. So I apologize for that. It should be corrected for you now, so it's fine. And then we need to do this for the validation as well. Perfect. Val false. Perfect. So now we're ready. Limit the dataset, right? So this is kind of funny here, because what we need to do now is actually to extract all the information from it. And so we only need the airplane and birds, and what it advises here is to take this one here and map it. So what does this do, right? It takes that the labels that are labeled 0 will be labeled to 0, and the labels that are labeled 2, which is a bird, will be labeled to 1. So we have labels 0 and 1 in our data set. Doesn't make sense? Just wait a moment. Good. So we actually have the list comprehension here. I think this is actually all we need. So we have cipher 10 here equals to this piece here, right? So what does this one do here, right? So it takes images and labels from cipher 10 if label in 02. So this is a requirement that is either airplane or bird. And then we map it to this one here, image, label, map. This is this map. So if it was a 2, it will be mapped to 1. And if it's a 0, it will be a 0 still. And then it says to do this as well for, well, perfect. So now it's doing it, and it takes a few seconds because it's quite a large set. So it should be done in a moment. Perfect. Create the model. So now for the fun part, right? So let's create a model there. So the model is 3072 to 512, and then it takes this TON activation and then a linear with 2 nodes. So it takes from 512 to 2 nodes, and then it uses log softmax. Okay, perfect. So let's try to do that. So model, sequential, and it takes this as a list like this. Okay, and then linear 3072. And why it's 3072? You know that? Let me know in the comments. 512 here, and then, and what do we do here? Perfect. Oh, comma, and then linear, and it takes 512 to 2, and then it takes nn log soft max of dimension 1. Perfect. I think that was basically it. So we are happy here. Then we train the model, and how to do that? It is basically, we do this loading thing here, the data loader, and then we have the learning rate. So this is a bit copy pasting, and then we do the optimizer and loss function here. Let's see if we can do it all correct, and then run the training here. Boom. And I do 10 iterations again. I'm a bit worried about that. Cipher 2 is not defined. So actually, so what I did wrong here, Cipher 2, so it should be called not Cipher 10 and 10 here, because it's Cipher 2 now, right? It makes sense, right? Yeah, so that's why it's called Cipher 2 down there. It's because there are only 2 different categories now. But yeah, should we rerun it up here? It took, we'll do that. We'll do it. Oh, it's a quite fast, this one, because it actually remembers it. That's pretty nice. Okay. Oh, could we do that? Yeah, I think we could do that because these were reassigned. No, we couldn't do that. That was success, because now what I did, I removed all the labels with 2 now. Oh no. Okay, so I have to run these here again here, and then I have to run this one again here. Okay, I apologize for the confusion here, but that's just to keep it a bit more consistent so you understand what's happening. And we all do mistakes, so don't worry about it. And we had the model here, nothing changed there. And then we have this one here. Boom, and now it runs. Okay, so it was the first one, second one. Okay, it goes a bit faster. I'm happy about that. We see the loss function going up and down like crazy here. And perfect. And test the model. So let's try that. Perfect. So accuracy 80%. So remember, actually, this. Okay, we cannot compare it with the others. With the other we did, because there was 70%, but that was on all 10 data sets. We only did it for 2 here, so it's not a fair comparison. But this model here is also quite simple, as you see here. It's really simple, so don't expect too much from it. And that's it. So optional, I highly advise you to play around with these things here, because it's really funny, right? To maybe more epochs, number of hit nodes, add some, remove some, adjust the learning rate, and change the activation function, add another layer, and yeah, look at Wikipedia for inspiration. And also, I would advise you to try all 10 classes of data. Try, maybe start with 3, 4, and continue from there. It's going to be amazing. Perfect. I hope you enjoyed this one, because it's been amazing to make. It's really funny to play around with these things. Also, let me know if you like PyTorch better than TensorFlow. I think it's a matter of taste. I think there's a bit more code involved when you do these PyTorch, but some people say it's more in line with how you should think Python, and I can see their point. But on the other hand, why make things more complex when it's not needed? And in the next one, it's gonna be amazing, because actually we are gonna learn about recurrent neural networks. And what's that? Well, so far we are not really using history very well. So in a recurrent network, you can actually re-inject the same again and again in the network, and it works really well with time series data. That is data that has some sequence of time in it. It's going to be amazing. You will be surprised how amazingly funny it is to play with. So remember, like, subscribe, and all that kind of stuff to my channel here. I really appreciate it. I will make more stuff available if you start supporting this. Thank you, and see you in the next one. Recurrent neural networks. Wow, that sounds cool. What is that? Don't worry about it. We will cover that along with some introduction to it with some examples. And then we're going to do a project where we're actually going to use weather data to try and predict the temperature in the future. So don't expect some perfect results, because as far as I know, there's been no weather prediction that was 100% accurate so far, at least over the time. Maybe once in a while it is, but not all the time. So if you're new to this series, this is the Machine Learning with Python course. It's a 15-part series with tutorials on each concept and projects doing on each concept, and we are here in the recurrent neural network, or RNN. So let's jump to the Jupyter Notebook. If you don't know where that is, there's a link down below in the description. You can download all the resources available, all the course material. It's going to be amazing. So see you in Jupyter Notebook. Recurrent neural network, RNN. Okay, the goal of this lesson is to understand what is this recurrent neural network, or RNN, I talk about all the time, right? And then build an RNN on a time series. Wow. Feed-forward neural network. So what we've done so far, like in our deep neural networks, CNN and all that kind of stuff, it's been feed-forward. What does that mean? It means that the information only travels in one direction, right? So that's what it does. So in a recurrent neural network, you actually have a neural network that generates output that feeds back into its own input. So you kind of have recurrent iterations of the same data. So it can do. So what is the advantage of this RNN? Well, it can do one-to-many relationships or many-to-many relationships. And these are actually not possible with feed-forward neural networks, right? When you have the output dimension, right? Like say in the classification we did, right? If we had 2 classes, there were only 2 optional outputs, and that was all. It couldn't say anything else on that. It's like the output is fixed. So just wait a minute. If it doesn't make sense, it will make sense just in a few seconds. But this can generate sentences, right? Okay, so this makes sense, right? So imagine you have a neural network that needs to reply to you, right? So it needs to come with an answer. So sometimes the answer is yes or no. So that will be one neural network, right? But sometimes you need to say, yes, this is a case, this is a house, this is a building, or it has to analyze an image, for instance, and you say, on the image, I see 3 people, 2 buildings, a car, and a Doberman dog. Okay, so the output would depend on how many objects you identify or the machine learning algorithm identifies. So that is a one-to-many relationship. And it's especially also good for time series, and we're going to explore that. So what is a time series? For instance, when you look at the stock market, you have the stock price going up and down. That's a time series. Also with the weather data that we're going to explore in our project. It's going to be amazing. It's not the same weather data as from the first lessons we had, so don't worry about that. So just a few examples of recurrent neural network, or RNN. Google Translate, right? It's a many-to-many relationship. You type something in and then it translates it, and it's many-to-many. Voice recognition is also, Siri, or what's called on Android, I don't know, recognizing your voice. And video copyright violations also used. There are many examples. So some of the things we've been doing here in our machine learning journey here is quite simple, and some concepts are easy to understand, really easy, even though it's very complex what's happening below. And some of them, for instance, like the reinforcement learning, it is so simple that you just implement it from scratch. It's so simple, right? But RNN, I would say it is not that simple. I mean, you understand the high level concept of it, that data can feed back into the loop. That's what you need to understand. So let's just look at it. Well, it is complex. RNN is complex, but luckily, it's not needed to understand it in depth. It's not needed. So this is a quote by one of the authors of Keras, which we are using for this RNN. Well, let's just see what he says. You don't need to understand everything about specific architecture of an LSTM cell, which are the one we're going to use. Just that LSTM cells is meant to allow past information to be re-injected at a later time. So that's again it. You need to understand that, okay, you have past information and it is re-injected again. But you don't need to understand all the in-depth theory and all that. Forget about it. If this is your first thing, the power of it is still available to you. Remember, in the beginning I was talking about, right? Well, you don't need to be a car mechanics in order to drive a car. You just need to know there's an engine. And maybe you don't even need to know that, but you just need to know how to use the dashboard in the car. And that's basically it. It's the same with machine learning. You don't need to be the mechanic, the one developing the LSTM cells. You don't need to know all that. No, just leave that to the experts and just figure out how to use it. All you need to know is data gets re-injected. So what are we going to look at today? What are the libraries? Pandas, NumPy, Matplotlib, TensorFlow. Awesome. And then we have CSV. And then we have something new here, min-max scaler. So what does that do? So basically it transforms features by scaling each feature to a given range. And this is what we need. We need to make these normalization transformations all the time. So that's what it does. And then we have some of the things we know: sequential, dense, dropout, and then the LSTM. This is the short-term memory layer invented by this guy here. Okay. So if you want to read a bit more about it, you can read about it here. I don't know how much it actually says here. Used in guides, so you can actually get some guides here around it and play along with that. But let's start here. And what the first thing you need to do is import all that kind of things we're using here. There's a lot, right? And then we're gonna start by reading our data. If I could not mistype it. And today the data is in PD, read CSV, and let me think if I can remember what it is that we are reading. So it was Apple stock today. And since it's a time series, well, I'm not really sure if I want to parse the dates, true, and set now index call 0. Okay, so here we have the data head. Here we have it, right? So we have parsed these as states here. And why do I do that? Is because I want to transfer some for training and some for for non-training, and the data set here starts in 2000. You can get your own data set, your own stock data set if you want that instead. And the data set ends in 2021. We're only going to use it until 2020 because these recordings are done in 2020, and I want a full year of data. And so what we need to do now is to have the training data and the test data here. And let's do that. Data train. It's going to be all the data here from location, and we're going to take it from 2000 from the beginning until 2019, and we're going to take it on adjusted close. I'm actually not sure if we need it in NumPy, but let's just keep it in NumPy. Data, doesn't matter if we have it or not. Test data, log, and then we take 2020, and I know there's data in 2000, how's it called, 21, adjusted close, but we're gonna ignore that today. Perfect. So now we have the data train, as we see here. The reason why I actually want it as a NumPy is it's easier to do the indexing as it is than in a data frame. So here we have the data here, and so one problem here is that we need to scale it, right? So that's the first thing we're gonna do. It's like we're gonna use the min-max scaler, and so we take the scaler, min-max scaler, good. And what it does, it basically scales the data. Data train, scaler fit, or fit transform. So we both fit and transform. And take data train, where we need to reshape it. So what this reshape does, it is instead of having it in one single line, it will be one entry per row. Good. And then we have data test. We use the scaler again. Now it's fitted already, so now we can actually just transform. Oh, I've made a space here. Transform, scaler. Now it works. Transform, data test, reshape, -1, 1 here. Perfect here. So now we have it scaled, right? So if you just look at the data here, let's just take it all. So now you see here that like one item on each row, and the highest price is actually the last price. It is 1 here. And if we look at data test, we will see actually the price goes above here and goes down again and above again. And the reason why you don't what's called fit the data to an entire data set is basically you would tell the algorithm something about the test data that you didn't know at the training stage, right? So if you fit it here on all the data, it actually would be scaled accordingly to the test data. So that would implicitly tell something to the model that, because the training data would be maybe in the interval from 0 to 0.8, it would simply implicitly maybe get an idea. That's kind of the thought, right? That there's some data above that. And you don't want that. In this case, it actually would be there. Perfect. So what have we done? We have normalized the data with the min-max scaler. And let's go and make the data preparation. And this is a bit more involved, actually. So what is this we want? We want to take a history of data, and then we want to predict the next price. So we take the price for a size of 40, and then we take the label to be the next value. So we want to predict the next value. Okay. What do I mean? We'll get there. Def data preparation, maybe. And it takes data here. And what does it do? So we have the X here and we have the Y here to be lists. We're going to transform them afterwards to NumPy array. So for I in range. And what do we range for? So let's do the window size of 40 and length of data. And what do? We take x and append data from I minus 40 to I, right? And that's basically it. We need to take the correct frame. Why do we need to take this one? And why append data for I, right? I'm actually a bit confused about this one. This one shouldn't be there. So this is basically it. And then we take and say x is equal np array for x, and y is equal to np array for y. And then we need to x is x reshape. We need to reshape it, because this is why we need this 0 in order to keep the shape there. Reshape shape 0, comma x shape 1 and 1 here. So return x and y. Okay, so this is our data preparation. So let's try to see if everything went well. So data train. Okay, so this is not what I want to write. So it x train y train equals to data preparation of data train. Perfect. So now we see here x train shape. We have this shape here, and y train shape, we have this shape here, right? So now we get it, right? So we have apparently 4,991, and we have window sizes of 40, and we have this additional dimension here we need, and then we have the y training data, and this is just predicting the next price. So let's also do this for test. X test, y test, data preparation. Oh, I misspelled it. You saw that? Oh, that sucks. Data test. You have to live with that. I apologize. This annoys me. Okay, so we need to. So when you try it, it's not with this misspeller. Okay, perfect. So far, so good. Good. Now we want to make our model on this here. And it's going to be, again, it's going to be a simple model. And I highly advise you to do something more advanced. So model here, we take the sequential and then we add a layer here. And it's going to be this LSTM. And units, it's going to be 45. Return sequence. Okay, you cannot. Return sequence is true. That means you can have feedback. Input shape. X train shape. We take the first dimension. This is a 40 and then 1 here. Perfect. And model add here. And we take another LSTM. I cannot hit the keyboard here. Units. We just take 45 again here. I don't know if this is good, but let's try this. Return sequence. True. That means we can feed back in it. Model add LSTM units. I'm going to do 45 again here. And no return sequence, and then we take model add, and we do a dense, and it has units 1 here. Okay, perfect. So this is basically it, and then we take model, compile, and we do optimizer, and we do loss mean, we take the mean square error matrix accuracy. Perfect. So this is apparently not perfect. Probably some misspelling here. Oh, that's a long keyword. Understood. Return sequence. It's not called return sequence. Return sequences. Return sequences. Okay, perfect. There you go. And then we have model fit. Now we're going to fit our model. It's going to X train, Y train, and let's do epochs 5, and I just put batch size as well to 32, which is default. So this is fitting here, and it didn't fit very well here, and probably something unknown loss function, again a misspelling. Mean square error, squared error. There you go. Okay, so you need to type in everything correct, and when I type so fast here, I'm sitting here communicating with you, you distracted me a bit. So you know that. Yeah, you know that? Yeah. So I only do 5 here because I'm not gonna wait here forever. It's actually quite fast. It's also quite small one, but the idea is the 2 first layers have return sequences, so it can return the data inside here. And let's see how it works. So let's do some prediction. Pred, and it's a model and predict, and then we take X test. Perfect. And now we have predicted. So let's try to, okay, let's just look at the dimension here, pred shape. So one thing, oh, actually that's quite okay here. So we have 213 around the number of trading days in a year, so that fits pretty well. And let's try to map it out and see how it goes. Fig axis PLT subplots. Okay, amazing. And AX plot. And what do you want to plot first? Y pred here. And AX plot the real price here. Y test here. And color red. So here you go. So the red is the real price. You can see it's way more going up and down. It's way more, yeah. And the predicted is actually above here. You see it's kind of doesn't, I must say it doesn't do a well prediction. It is a kind of slow, but maybe the network is also too naive. So this is just to get an idea how you can get started. And you might notice one thing, that the intervals here are not the prices actually, but you can actually transform that back. So you can actually say Y unscaled, for instance, call it like that. And scalar, and you say inverse transform. Oops, and Y pred here. So then you get the real values, and yeah, let's just try to do that. Axis PLT subplots, and Y real values here. It is data log, and it was 2020, right? Oh, 20, and it was adjusted close. So we just read the real data first here to NumPy. Perfect. Oh, we're doing a figure. That was not what I wanted to do. So we have the data here. So X plot, and we have Y real here, and we actually plotted from position 40. Why? Because we skipped the first 40 values. Plot and Y. How's it called? Unscaled. Should we have a color? I don't know. It figures out itself. Right, so here you actually see the exact same chart here, but the difference is that here you have the prices in US dollars here, and then the day numbers here, right? So here you go. So you can see how to transform it back with this inverse transform, and yeah, that's basically it. So now we're going to do a project instead where we work on weather data, which is probably even less predictable than the stock market. See you in the next one. We're going to introduce the project. It's going to be amazing. See you in a moment. Are you ready for this project? It's going to be amazing. We're going to use create a recurrent neural network, and we're going to use it to predict weather forecast or predict the temperature in the future. Okay, so are you ready for that? So let's dive into it. So here the project is recurrent neural network. We're gonna approach a project on weather prediction on time series data. So it's similar to our stock data, just a bit more predictable. That's my claim, at least. So the first one is import the libraries we're gonna use. Perfect. And then we are going to execute this cell to download the data. Then we're gonna read the data. Awesome. And then we're gonna limit the data set, because basically it has measurements every 10 minutes. But as many people point out, it's not like the temperature is gonna, or the data is gonna change much within 10 minutes. What matters is maybe once an hour. So you actually do that by removing that. And it says here how to do that. So do that. Investigate the data, look at the correlation, inspect the columns that are correlated or not. It's often, you have a lot of data here, and a lot of it might not matter. Potentially some data could be transformed like this here, these wind velocities, but we're just going to ignore them in this one here. If you want to, you should transform them, because they are not really good for the model in the way they are. Then we are going to add periodic time intervals. So this is quite interesting. This is new. So the temperature is correlated to the time of day, right? You might expect it's warmer in the midday than it is at midnight. At least in most places on planet Earth, I think that's the case. So right now the model doesn't really understand time measurement. So you want to make a curve that goes from, maybe it starts on 1 at midnight and then 0 and -1 at midday, and then it goes back up, right? A sinus or a cosinus curve. It's actually a cosinus curve, that one, right? And the same with seasons, right? It might be warmer in summer than winter. So you also want to do one which is really slow, that goes 1 cycle per year. How do you do that? Well, try to follow along here. You made a data frame with the index, which is timestamp _s, for instance. Then you do a mapping, and then you have the day period and the year period, and then you follow these formulas here. Perfect. Then we split the data, and again here we do a validation set and a testing set. So this is also kind of new. Why do we have that? Well, this is about it. Read about it there. If you want to build a solid model, you want to follow specific protocols for splitting your data into 3 sets: 1 training, 1 validation, and 1 final evaluation, which is a test set. So you already saw previously that in some sense we had in the algorithm, we put a validation set along with it, and we're going to do that as well, and it's called validation set here. But we're also going to make a test set here. So what to do? Use the length of the data and split it into 70% training, 20% validation, and 10% for testing. Then we're going to normalize it. Yeah, you need the data to be in the intervals from 0 to 1. And how do you do that? You get the mean and the standard from this, and only do it on the test or train data. And then you do this transformation here, assuming the naming fits. And you have to do that with train, mean, and the transformation valid on test data is done similarly. On validation and test data is done similarly, but you, of course, with train mean and train standard, because you need to make the same transformation and not like that. And then we create data sets, and here I also explain a bit better with the input width, the offset, and the label. And in our previous one, we took input width of 40, and the offset was actually only 1, because we had 40 data points, and then the next data point was actually the one we wanted to predict. And here we want to have 24, so data for 1 hour, and then we're going to predict it in 24 hours. So we're going to predict 24 hours ahead in time. Wow. So giving all the measurements right now, what is the temperature tomorrow at the same time. Then we're going to make a function input with offset. Assume we always use a label with 1, right? This is a label with. Call the function create dataset, which takes argument all this piece here, and let it create 2 empty lists, x and y. Convert it. I mean, just try to follow along here. If you get confused, well, I'm there to help you in the next one. Then we create a model, and again here we make a really simple model. So don't expect fireworks if it doesn't get specific data. Perfect. And then we then we train the model. So actually compile and fit the model down here. We could have compiled it up there. We didn't do that. Do this in step 12. And then we try to predict data where x is assigned to the test data, right? And remember here, oh yeah, that was a thing to notice here. In our fit, we have validation data to be the validation data frames. Perfect. Or data sets, not data frames. And then we plot the results. We do that. One way to do it is like this. And then optionals, calculate the correlations. Perfect. Are you excited? I hope so, because this is actually going to be amazing. You will learn some new things along the way here. I often like that when you do something, you should learn something new. So here we go. We are getting more and more advanced. So I hope you enjoy it. So try it out yourself. If you get stuck, don't worry about it. I'm there to help you in the next one. So see you there in a moment. Bye-bye. And how did it go? Did you manage all by yourself? Let me know in the comment if it was too difficult or not. I'm also here to learn how to teach better, so please let me know. So let's get started. I hope you managed some of it on your own, and if you didn't try it all, I highly encourage you to try it before you see how it can be done. This is really how you learn. You don't learn by watching me doing it. You learn by doing it yourself. It's like, yes, you learn some tricks along the way, but it's like, for instance, imagine you want to learn to play soccer. I know soccer is maybe not a big thing in the US, but in Europe it's a big thing. And if you watch the players, yes, you'll learn some tricks, but honestly, you'll learn way faster if you go out on the field and play soccer yourself, right? Yeah? The same is with programming. Good. So let's jump into it. I introduced it already, so we import the libraries here. We download the datasets here. And then we need to read the data here from step 2 here. So there's a thing here, right? We have the CSV path here, and we need to use that path there. So this is actually where we downloaded the data. So let's get that. So PD read, oh, we need to say data, I guess. PD read CSV, but here we have to have CSV path there. And then it says parse dates to be true and index call to be 0. And let's just data head here. It's a good idea. And you see here, it's a big data set, so it takes actually quite some time to read the data here. Quite a long time, because it is a big data set. And it continues really long. I don't know how many rows there are. Actually, we should investigate that afterwards. It could be fun, right? And if we ever get the dataset online on board in our data frame, I'll be surprised if not, but you never know. Okay, here we go. And does the data look okay? It looks actually pretty okay here. So perfect. So let's just get the length of data here. And you see here, oh yeah, it's 420,000 columns of data, or rows of data, not columns, rows of data. Wow, amazing. But as we see already here, we're gonna limit the data set. So that's how we are gonna do it. So we're gonna only take every 5th column. So let's do that. Data 5::6, and then we have less data. So let's just see the length of data now, and you see we have 1/6 of the data, so we only have 1 data point per hour. Because if you look at the data here, it's like 10 minutes past, 20 minutes past, 30 minutes past, 40 minutes past, and so on. And now we can also look at that. Data hit. You see we start by 1 o'clock, 2 o'clock, 3 o'clock instead. Good. So let's investigate the data. So data, core. So what does core do? Remember, it's correlation, right? So we see that in the diagonal, it's a big set of data here, but in the diagonal here, you see you have ones all the way, and that's because it is the same against the same. But what we're really looking for is the temperature in degrees here, and we want to see are there some that are really low correlated. And you will actually see some of them, like these down here, are really low. So we are gonna remove them. The reason is that these data needed to be transformed in order for the model to make sense of it. So we are just gonna remove them, okay? So let's just put it in as a data frame and call data drop. And we're gonna drop this list here. I think I put a space there. I'm getting used to that. Perfect. I think we have to put axis 1 here. Axis 1. Perfect. And still not happy. We need a comma here. Perfect. So here we go, right? Awesome. I should actually just help you so you don't make the same mistake as me when you copy paste. And axis 1 is probably also one. If you don't remember drop, yeah, it's a bit difficult. Okay, perfect. So let's continue. So what to do here, right? We need to transform the temperature. So let's do that. Time stamps s. We have that to be data frame index here. So we have all the timestamps in there, and then we want to transform them. So let's do that. Timestamps s equals timestamps s map, and then we do pd timestamp. Oh, not stamp timestamp. Okay, so that's the transformation here. So now we have the data here as seconds instead. We can look at that. So here we have it as seconds instead of a date, right? So before here in this format here, just show it here, we had it as a time index, right? So what we did here was transforming it to seconds instead. And why do we do that? It's because then we can transform it easier to what we want. So do like this, assign the data frame index to a variable time. Okay, this is what we did. And then we make a variable day to be 24 times 60 times 60. And then year to be, oh, that's difficult, 365.2425 times day. Wow, who made this up? And then we make a column data frame. What is it called? Day sin. And np sin timestamp times 2 times n pi divided by day. And we need to do similar for cosinus, and then we need to do similar for year, right? Similar for year. Year and year. Okay, so now we have made these curves of the data instead of having seconds, which would be linear. Then we have these sinus curves and cosinus curves. We don't really know which one is going to be the best one, and if actually, let's just try to do this correlation thing here, and we find these down here actually with the temperature. you see here, actually, this one correlates the most with temperature, and then sinus second most on the daily basis, right? But of course, it's not going to be perfect, but there will be some correlation on it. It's at least something you can use, which is not, how's it called, which is better than the date, which it doesn't understand. Okay, so now we need to split the data. So let's just have a length of the data frame. We call it data frame, yeah. Train data frame, and what's that? It's going to be the data frame from 0, and then we need to take integer, and we take n times 0.7, and then we have validation data frame, and we take this from this piece here, and it should be 9 instead here, right? And then we do test data frame to be data frame, and we take it from this one here, colon. Actually, we don't need the 0 here, but it's okay. We just leave it. Perfect. So now we have 70% here, 20% here, and 10% here, right? This is the 20% and this is the 10%, right? So we added it up like that. I hope you understand that. Perfect. Then we need to normalize the data. And what we need to do is we need to find the train mean. We do it on the train data frame, and we actually just take the mean value on it. And then we have the standard deviation. No, train standard deviation, STD, right? And train D3 STD, right? So now we have these values there, and then we need to transform them. And for instance, we do it, let's just copy here and copy here and copy here. So here we have validation and test and test. So again, here we keep the train mean, and train standard deviation for all of them, because you do only the calculation on the training data and not on the validation and test data. Okay. And now for this one, this I know is a bit more complex, and again, I explained what all this means, but basically we give this as input data, this frame of 24, and we want a prediction down here. So let's see if we can make sense of it. So yeah, def create dataset, as it says up there, and which takes argument all this piece here. So it takes input width, offset. I don't know why I take, yeah, offset, offset 0. Okay, so actually we start with offset 0 by default. Let's do that first, and then you can play around with it afterwards with different sets. And let's just follow the manual there. Create 2 empty lists. It's just like we did in the lesson, and convert the data frame into NumPy and assign it to data X. So df to NumPy, and then we have data Y, which is df, and what do we have here? We have the predict column, and to NumPy. Perfect. So far, so good. Let's just add an extra line here so we can read the data. And then for I in range, and where do we range from? We range from input width. That's where we start, right? Oh, input width. And where do we end? We end at the length of the, data X, and then we minus offset. Okay, perfect. And colon here, and then we are. So then we take X append, And then we take data x here. And what do we take? We take from I minus I input width until I, and we take all the data here in this case, and y append, and then we take data y I plus offset, right? So this is offsetted because we are predicting, if we just took the first index, it would here and plus offset. And by default, we're going to take offset 0, and later you can play around with it with longer offset. Okay, perfect. Awesome. And then we are going to transform this into NumPy arrays. So x and p array x y equals np array y. Awesome. And what's next? Then we are going to reshape, return x comma y, reshape -1 comma 1. So it's actually just reshaping how y is. It's making from one long row to one column per thing. Perfect. Awesome. And let's try to do this. Train data frame, or data set, we should call it. Create data set, and we take the train data frame, and then we have validation data set, and we create data set, and validation data frame, and then we have test data set equals to create data set test data frame. Okay, perfect. So here we have it. And should we just take a look at the shapes? Train ds shape. It's not called train, it doesn't have shape. We need probably to index into it. Oh. So yeah, okay, so for each one train, oh yeah, of course, I returned 2 here, I just forgot that, right? So this is test, no, this is how it's called, features, and we have 49,000 here, and it's 24 and 15, right? So we have 15 features, we have 24 hours of data, and we have this many data sets. Perfect. Create the model. So we're continuing model. This is straightforward. Models, if I could type it sequential, maybe I just add these things here. So the key thing to notice here is that we have return sequences to be true. That means that we feed the data again. Perfect. Then train the model. And fit the model. And we're going to run 5 times here, not too overdue. If you want to play around with it, I can advise you to put it a bit up here. Maybe that will help. And again, here we have the validation data here. So you will validate. So for each run, it will train it on the training data, and then you will validate it. And finally, we will actually test the data. Predict the data on the testing data and see how it performs accordingly to that. And yeah, and again, just remember, this is quite simple model we make here. It's only this one layer here, and you should play around with that too. And here we have the last one to see how it goes. Perfect. Okay, so now let's get the test data. Test data set here, right? So now we have the test in there, and then we have y pred to be the model predict x, right? So now we actually predicted all the values, and yeah, I actually just want to show you ypred shape, ypred shape. It's not a, yeah, okay, it's like this, obviously. And you see here, you actually have 24 values for each one of the prediction, because it predicts all the way through there. So let's try to know that. So I actually think this is straightforward copying to plot the data. So this is the y data, and this, so that's y data is the real data, and the prediction data is called ypred for me. I called it ypred up there, so it should be called that. And notice here I take -1 index here, because that's the last value of this 24 here. Okay, and I is not identified, so let's just put it somewhere. It was just to make some index here. Here we go. So you actually see here, so the red one is the predicted data and the green one is the real data here. Yeah, so you see here's the temperature, and predicted from the previous temperatures. This is how it goes. I don't know if it's good or bad. It's not, doesn't look perfect at least, but it's there. But it's also a very simple model we created here. And yeah, so optional, calculate the correlation. So correlation between the two data frames. Okay, let's do that. DFC for correlation, so I don't overwrite the other data here. So PD data frame. And what do? We get the real data here, and the real data was called y, and the predicted data was called y underscore pred there. So here we have it, and then we just say df underscore c core. So what did I do wrong here? Okay, so obviously I forgot that this one here is not a single list here, so we have to take the -1 comma 0 here. Okay, perfect. It was not what I wanted. It was a comma here. And the same thing for this one, obviously. This is also an index. Okay, perfect. So here you actually see that the real value is highly correlated with the predicted value. So it's not that bad. So it means that they actually go pretty much hand in hand. It might be that it's like that, but so it doesn't say it goes like this, but it say that it's basically when this one goes up, the other one goes up, and the other ones go down. When it goes down, it goes down. So that's what the correlation says. So you can also measure it with accuracy and so on, and get some measurements and try to improve the model. I will highly advise you, for instance, to add some more layers and try to play around with it, and maybe increase this one here to get some more. I don't know. Actually, it says the loss was it was not that high. So maybe there are many potential to create it better. Never mind. I like to hear below there what you did and how well you did. What were your scores? And I'm looking forward to hear that. If you like this one, so please like, subscribe, and all that kind of stuff. In the next one, we're actually going to change what we're going to work with. We're going to work with text. So another big thing in machine learning is how to extract information from text. And we're going to explore some philosophies and some aspects of that. And then we're going to turn into information retrieval and how to structure data. How does Google actually figure out what's relevant in a document? That's really amazing. And how can you represent words actually as information and how they relate to each other? It's actually mind-breaking if you haven't heard about it before. So I highly advise you to continue this journey even though it's not your highest interest in text, because there will be some things that you probably never thought about. I promise you that. So unless anything, let me know in the comments, and subscribe, like, and all that kind of stuff. See you in the future. Natural language processing. What is that? Well, this is about machine learning, extracting information of text or generating text which is readable. Well, this is actually kind of a shift of what we've been doing so far in this awesome journey. If you're new to this series, this is a 15-part series about machine learning with Python. If you want to get all the material, then there's a link down there in the description. Click it, read about it, get all the material. You get all the notebooks and everything and the projects that we are doing here together. So let's get started. Let's jump to Jupyter Notebook and get started. So here we are, natural language processing. The goal of this lesson is actually to start off from the beginning. How is simple syntax of language can be parsed, or how it can be done, right? What is context-free grammar actually, often called CFG? And how can you use it to parse text and check if the grammar is correctly aligned? And then understand text in trigrams. And actually, we're going to look at n-grams, but we are going to use trigrams. And then see how this can actually be used to generate predictions, or actually generate text in this case here. What is natural language processing? Well, it is kind of an automatic computational processing of human language, right? So this includes that algorithm that takes some written things, written language as input, and generate something based on that. So that might be an essay on something, or a document, a resume or something, and it can parse that text and generate something out of that. But it also includes things that produce natural text, right? So this is a bit more difficult than you actually think, right? So how do you make a computer generate text? We see that all over right now, but just a few years ago, like 10 years ago, it was quite difficult. But now you have all these talking computers, Siri and all that kind of stuff. How does it do that? Good. So what does this include, natural language processing? Well, it's, for instance, making automatic summarization of a document, right? You don't want to read a 600 pages document just to figure out what it's all about. Well, if you can make an algorithm do that for you, that would be amazing, right? And it's also about a language in identification, right? Is this English? Is this German? Is this Swedish? Is this Polish? Is this Italian? Is this Asian, some kind of Asian language? How can you make the computer figure that one out? That's also one of them. And then obviously translation, right? Google Translate. How does that work? Well, it is based on this natural language processing subfield. It is amazing. So let's step to our first thing here, syntax. So one basic description of a language syntax is the sentence in which the subject, verb, and object usually appear in sentences, right? So how can you use that? Well, if you think a little bit more about it, we have something called formal grammar, which is a system of rules of generating sentences in a language. English has that, as well as many, I think most languages have that. And grammar is usually thought of a language generator, right? So if you have a grammar, you can actually generate language, or you can check if language is correctly structured. As you will see, though, you cannot, with a grammar, you cannot just generate, you can generate well-formed sentences, but they don't always make sense. And you can check if a sentence is in according to the grammar, but it's not easy to see if it makes sense for a human, right? So this is kind of some of the difficult parts. So the easy part is telling a computer, this is a grammar, generate some sentences from that, or check if this sentence is a grammar. But there's a catch, right? It doesn't really understand if it makes sense or not. That's the difficulty of that. If you want to read a bit more about it, there's a link to formal grammar on Wikipedia here. It's good in reading. So the first grammar that we talk about is context-free grammar. So what is a context-free grammar, right? It's a formal grammar is a context-free if its production rules can be applied regardless of the context of a non-terminal. Okay, so what does it mean? It means basically that the grammar is not dependent on the situation, right? The context you're in, right? So for instance, say if you ask something, it might implicitly mean something in the context you're in. For instance, if I ask, is this you? You will say, yeah, of course it's me. But for instance, imagine that there's lying a dead body in front of you and I ask you, is this you? and it's probably implicit, is it you who made something? Are you related to the crime scene here? Did you have an involvement in the crime scene, right? So you see, the context can make a difference on how you interpret the question. So in a context-free grammar, well, we don't care about the context. The context has nothing to say, right? Good, perfect. So programming notes. We have something new here. It is the NLTK, the Natural Language Toolkit. And this has been around for some time, and it's amazing. So we're going to explore a bit about that. And one of the things we're going to explore is actually how to generate these context-free parse trees here. It's going to be amazing. Just wait a moment. And we're also going to use the OS because we're going to read a lot of text. And I think it's also good for you just to know how to read a lot of text from a file system. And collection, container, data types, and Markovify. We will do something with Markov chains later here. It's I don't know if you remember, we talked about Markov chains earlier, and we're going to use them now. It's a mathematical thing. Again, if you don't really need to understand the mathematics behind, you just need to understand what it does. And then we have a chart parser. It's a generic chart parser, and we're going to use list comprehension and a counter. It's a subclass of counting hashable objects, so we can count how many appearances are of a specific object. We're going to use that in our project down there. And Markovify text is a created Markov model here. We're going to use that in the end here. So are you ready? So the pip install NLTK here, we need to install the library. So it doesn't come by default with the Anaconda installation, so you need to install that, at least not at the current time of recording. So you need to execute this one. I already installed this, I'm not going to execute it. So I'm just going to import the library here. Okay, so the first thing we're going to do here is actually generate a CFG, or a context-free grammar. And this is just for you to understand what's possible to do that with this framework here, and see what it is, also understand the limitations of it, right? So what does it do? Well, it creates a grammar, or a context-free grammar, by some rules. And we have, like, here we have one rule per line. And so there are like 6 rules here. And what it tries to construct is a sentence. And a sentence is constructed by a noun phrase afterwards with a verb phrase. So NP, noun phrase, verb phrase afterwards. So a noun phrase is constructed by a noun, or these are the pipes are indicating or, a D word, that's these small words here, and a noun. And a verb phrase is constructed by a verb, or a verb and a noun phrase again. Okay, and then we have the D words here. And so this list could be enormously long, but I just created this small one here. So it's like the, so a noun could be the city, the car. So that makes sense, right? And you can also see here already from a noun phrase, you can have a D and an N, right? So it will be the, she. It does make sense. But it's formally correct grammar. So this is correct grammar. So you can generate things like that. And then saw, right? So when you generate a sentence from this here, right, you can say a noun phrase. So let's just take a noun, she, and then a verb phrase. It could be a verb, she saw, or she walked. These are within this rule set here. So what can you do? Well, you parse this grammar here, and you can make it with as many rules as you want. And we're not going to dive into that. And as many words as you want here. We only have a few words here. And then we take a sentence, and then we try to parse this sentence here. So let's actually try to do that. This is actually quite fun here. So what can we write in this thing here? Perfect. So she walked. So let's try to do that. So it generates a tree here, as you see here. So it says it's a sentence, and the noun phrase is a noun, and it's she, and the verb phrase is a verb and walked, right? So this is how the tree looks like generated from here. So it says this is a valid sentence. For instance, if we said she, and she city, it would say nothing out here because this is not a valid context grammar. Because she city, it's a noun after a noun, and you cannot generate that from this sentence here. But let's take another example here, and it will be she saw a car, and you'll see this is actually correct again. So it starts by the noun phrase, it's she, and then the verb, it uses the verb and a noun phrase. Saw is a verb, and a car is a noun phrase. So you see how this works. But you probably already feel the limitations of this as well. Because right now, yes, you can check if a grammar is correctly based on this, but you have to sit there and program all these rules here, right? So this is not as good as you want in a machine learning context, because this is like limited to what you need to make it all, right? So this is kind of the challenge with CFGs, the context-free grammar, right? You need to encode all possibilities, because if it doesn't exist, and obviously this language here doesn't really express really a lot, but if it doesn't exist, well, you cannot generate it. So this is where an idea comes into the picture. Understand text in a small subset. What does that mean? Let's get there. So this introduces the idea of an n-gram. So it's a continuous sequence of n items from a sample of text. So basically, let's go for the word n-gram, is a continuous sequence of n words from a sample text, right? So instead of thinking of the whole sentence like we do up here, we actually isolate it to a subsequence of words. So just to clarify, sometimes they call it unigram is one item, bigram, trigram is often used. And we're going to explore the trigram. So what we're going to do is actually we're going to read a lot of text in, and then we're going to explore three words together. And you'll be surprised actually what you can make from that. And we're going to do that in the end. So what we're going to do is like word tokenization. So it's a task of splitting a sequence of words into tokens, consideration, comma, and so on. So all these punctuations and all that kind of stuff, you need to have an idea about them, because when you have a sequence of words into tokens and you have a comma or a punctuation or something, it might mean something in that context. So you need to deal with that. But we're not going to dive into that in this course. But you just have to realize that if you have a dot after something and it starts a word afterwards, maybe it means different in that, because you start a new sentence, right? So the first thing, you need to import collections and the counter that we're going to use. And then you're going to download this one here, because it's used by this how's it called, this word tokenization that we are gonna use. Good. And it's for me, it's already downloaded, but it will probably download it for you if you didn't do it already. Okay, so what do we want to do first? Well, we have a lot of files actually. If you go here in files here, you'll actually see here that in this is actually a folder, and it has a lot of stories here. It has all the Sherlock Holmes stories, and we're gonna read those into our little model. So how does that work? Well, I'll just want to show you one way to do it. Our content, I think I would call it. And this is for you to do it differently. It's up to you. It's just one way to do it. So file name in OS list dir, and files homes. Good. So what does this do? Well, you probably guessed it, right? So this lists all the file names. So if you do here file name, it actually lists all the files we just saw over here, right? So these are the names that it's listing here. So now we have the file name here, right? Good. And the next thing is we want to open it, right? So open, and there's a catch here, right? Because we only get the file name, and we need actually the folder as well, the location of it. So what do I do here? I use a formatted string, and we take files homes and then the file name, which is given here. and then we want to, yeah, let's just call it as F, and then we want to content append F read, right? So what have I done here? I read all the content here, right? So len content, and we have 21 files of content. So it just reads everything raw into this list. So we have a list of 21 files of raw content. So we need to kind of work that, and often you call that a corpus. And so for item in context, we need to turn it into word tokens. So corpus, we extend it. That means we expand the list instead of just appending. So if you appended a list to a list, it will be a list of lists, right? So this is why. And often when you want to work with text, you want to work it all in lowercase, because if it's uppercase, lowercase, it doesn't really matter, right? Or it matters for the computer. The computer sees it as two different words, if it's uppercase or lowercase, so just work in lowercase unless there's a reason for it. So we do the lowercase for word in NLTK, word tokenize, and we take item, and then we have some restrictions here, if any, because we need that it is alpha. That means that we have some characters in it for C in Word. Okay, that was a lot of things here, and it was not context, it was content. That was a lot of things here, right? So again, here it takes the word and makes it lower from word tokenization of item, and so item is a, yeah, so let's break it down. So item is the word, all the text, the full text, and then you make word tokenization, which actually takes each word out of it, and for each word it will make it lowercase if there is some alpha characters in there. So it's not only numeric or something like that, because then its alpha will not return, right? So it says if any of the characters in the word are alpha characters, then we'll keep it. You can make a different thing if you want, but here we do that. So how long is this corpus now, right? Length corpus. So we have 178,000 words right now. That's amazing. That's amazing. Good. So now we're going to do these n-grams that we talked about. And how do you do that? Counter. And we take NLTK and n-grams. And we take the corpus. And we take 3. So we do. So what it does, it takes words, 3 words in a row, and adds it to this counter, and this counter counts how many appearances are of each 3 words. If it doesn't make sense, just I'll show you here in a moment. So for n-gram, it actually takes the frequency here in n-grams and most common. Let me just take let's take the 10 most common here, and we do print, and we make a, oh, it was supposed to be like this, frequency here, and let's say frec colon, and then we actually print the n-gram here. Okay, so what do we have here? So what does this mean? This means 80 times we saw this sequence of 3 words. It was a, for instance, beautiful day. It was a nice gesture. It was a something like that. We saw that 80 times out of these 178,000 words. And 71 times we saw one of the, and 65 times we saw I think that. So what can we use that for, you think? Well, the idea is here that every time we see the word it often comes with, for instance, was a, or actually it's down here, it is a. So when we see this word, we see most likely the context is like this. Also, we could look at the middle word instead and say what is often before and what is often after in these trigrams. And obviously you can make bigger than trigrams, but you also have to think the bigger they are, the less the more input text here, the bigger the corpus you need in order to exemplify that. So this is actually what it does, right? So based on that, you can actually predict for instance, you have two words. What is the most likely word to be the next one? It was, then the most likely is a. One of, the most likely is the. I think that. So given two words, you can actually predict with which ones are the most likely. To make a very accurate model, obviously you need a bit more text than this, but you get the point. So what is a Markov model? Remember that? Well, again, there's a lot of mathematics and yada yada. We're not going to go into that. If you're really into the mathematics about it, you can read Wikipedia about it, and yeah, it can be a bit discouraging. But basically what it does is actually what I explained up here, that given something, what is most likely to happen, right? So for instance, it says here, given in two words, you have the probability of the next word, right? So obviously you would have it was in other context. I don't think there are any two words. That he, actually we have here, that he, probability is something for had, and that he was is also has a probability. And so for each two words, you have some probability for the next word. And that's what we're going to use. And it's not really interesting programming wise. And there's a library that does it all. So we have this Markovify that can do it for us. So we import that. And now we're going to import the Shakespeare and read it all. And then Markovify it. And then it will make sentence. So what does that mean, make sentence? Well, if we take two words that are likely to happen, what is the third word, and then next two words, and what's the fourth word, the next two words, then you can actually generate sentences. These sentences might not make any sense, but they are based on that. So for instance here, haply some poison yet doth dang on every three, the fair the parties of suspicion. So it made no sense, right? But what will you yet know not what an indirect and peevish fellow is wise enough to drink those men upon the wild thyme blows. It kind of you kind of get the atmosphere of Shakespeare. It's not really perfect. It's also she must lie there. I mean, this could be anything, right? But it's funny. It's based on this idea that you take some probability. If these two words are together, what's the third one? So this actually is the first mind-breaking thing that you can do about it. So you get the idea here. And what's up next? Well, we're going to make a project. And actually, this is kind of funny. So we're going to explore tweets. And based on some statistics we're going to make, can you actually predict, can you figure out who tweeted those? That's actually surprising, right? And again, we're using some statistics in order to do it. And that's the first step of understanding natural language processing, because there's a lot of that kind of thing in that. So see you in a moment where I introduce the project. See you there. This is going to be amazing. So we're going to use a natural language processing theory in order to, can we determine who tweeted this? So just a bit of words about this. So the tweets, I have changed the names to it's like John Doe, the default name, right? So you cannot really see who the person is if you look at the tweets. But we're going to make some trigrams and see, just looking at the trigrams, can you actually predict who made these tweets? Okay, it's going to be amazing and you'll be surprised. Okay, so as I said, can you determine who tweeted this? Okay, description. We will analyze a collection of tweets from one tweet account. And can you figure out the person behind the account? So we are going to import some libraries, the ones we used just in the lesson there. And then we're going to read with CSV. We're going to convert the content. So we're going to apply to list on the column in order to get it as lists. And then we are create a corpus and iterate over the content, extend corpus with all words in lowercase, if any character is alpha in the word. So you use this lower and you use this any is alpha for C in word. Then we check the corpus. We're going to check the length of the corpus and look at the first 10 words of the corpus just to check it. And then we're going to display all 3 grams or trigrams they're called. So use the counter ngrams corpus 3 and assign it to a variable and list the 10 most common trigrams and do that with the most common 10 here. Okay, from the result of counter. And then we're going to pre-print it, iterate over the result of in a for loop. For each loop gives an ngram and a frequency. And if you want, you can try it on, this was also optional, 4 grams. And I'm pretty sure you're gonna guess it here with trigrams, but if you want to do it with 4 grams, I advise you to do it. So are you ready for this? I think so. So let's get started. And if you're new to this series here, well, I advise you to stop the video, try it yourself. You can get the notebooks from the links down there below. You can download all the Jupyter notebooks and then try to do this on your own. If you don't succeed, don't worry about it. We've all been there, and this is about learning. You try, you see how to solve it, and then you'll slowly learn along the way. So, are you ready? See you in a moment. Okay, are you ready? Did you figure it out? Did you try it yourself? Oh, please let me know. Did you figure out who it was? Who's the person behind this Twitter account? Please let me know in the comments. It will be amazing to see if you all agree. So let's try to do this. Okay, so we already know what it's about, so let's get started. So we start by importing the libraries. Awesome. Then we're going to read the data. So let's try to see if we can figure this one out. Data, PD, read, CSV, files, tweets, and yeah, let's just also inspect the data here. Head. So as you see here, it says John Doe here, so we don't know who the person is. Okay, convert content to a list of content, right? So content should be, so as you see up here, we have a date of the tweet and the content. Okay, and the content, that's what we want. So data, content here. So now we have it as a list. If you add 2 lists on it, thank you for reminding me here. Perfect here. So now content is a list. Let's just say see how many tweets. 43,000 tweets. Whoa, that's a lot. Okay, so create an empty list called corpus. So let's do that. What to do? Iterate over content. So for item in content colon extend corpus extend, use do all the tricks that we're doing here. Word lower, and what do we do for word in word tokenization, word tokenize of item if any C is alpha for C in word, right? So I think that was the thing we did also in the lecture, right? So we do the words in lowercase, not to distinguish between that, and then we have this word tokenize, and we only take it if any of them is alpha in the word. So that means we exclude a lot of things. Okay, so check the corpus, find length of corpus. It is 850,000. That's a lot. And let's just check the first 10 words, corpus, 10 words here. And be sure to tune in and watch John Doe on. So John Doe is the person we need to figure out who is. Okay, display all n-grams. So let's do that. N-gram, it should be a trigram, but it doesn't really like when you start with numbers. We could also actually, no, let's just keep it as n-gram here. And then we do a counter here on everything. Boom. And let's do that. And then we do n-gram most common words here. And we need to add 10 here. So let's see it here. Okay, so the 3 most common words that are in these tweets are America, great again. Who can that be? I don't know. The United States. I will be. Make America great. So these are probably make America great again. So make America great again. Run for president. Somebody ran for president. One of the fake news, the White House. All of the, so I think here already we can conclude is somebody probably running for president. He wants to make America great again, and I will be something, and the United States. It's probably somebody in the United States. You guessed who it is? I don't know. Optional, pretty print this. So let's just do that for let's just call it gram frec in n-gram most common 10, and then print, and we do pretty print here, and we take, what do? We do frec first, and then colon, gram here. Perfect. So this is just a different way to print it. You could also do it even more pretty by taking the words here individually and print it America Great Again. Good. So let's try to do it with a 4-gram instead. So you figure out how to do that. I'm the lazy person here, copy pasting here, and most common words. I would bet my ass it's let's make America great again, right? The great state of the fake news media, art of the deal of the United States, the art of the, yeah, in the history of. Okay, I think most people would guess who this person is. And isn't that amazing, right? So just by analyzing these trigrams or so forth, you can actually get a lot of information about a specific person. I think this demonstrates pretty well. So please let me know. Maybe you should try that, something similar with somebody else or your own tweets. If you're really a tweeter, then try to see what are the words that you're using. It'll probably things you don't really think about. What are the 3 most common words I use in my tweets, right? So is this amazing? I think so. So if you like this, please like and subscribe and all that kind of stuff, and spread the words about this amazing series here. In the next one, we're going to explore sentiment of sentences. It's going to be amazing, right? So how can you do that? Also, we're going to explore text categorization, but also sentiment analysis. Is this a positive or negative? And that's actually an amazing piece of work that everybody should try. So are you excited? I hope so. Please remember, spread the word about this channel here, and I will appreciate it. See you in the future. Text categorization. So in this one, we're going to learn about how can you figure something out about a text. For instance, text sentiment. Is it a positive text or is it a negative text? This is often used with reviews, right? If you are getting a lot of reviews on your web page, you might wonder if it is positive or negative in general. So how can you classify that? Because maybe you want to deal more with the negative reviews, faster at least, so you want some kind of mechanism to do that for you. So this is what this lesson is about. So if you're new to this one, please click below. There is a link and you can download all the content. This is a 15-part series about Python, or it's not about Python, it's about machine learning with Python. And if you want to get good at machine learning, this is the place to start, but start at the beginning because we learned so much so far. So let's jump to Jupyter Notebook. So text categorization. So the goal of this lesson is to, what is text categorization, right? Learn about bag of word models. What is that? Well, don't worry, we'll get there. Understand the naive Bayes rules. What's that? Don't worry, we'll get there. How to use this rule for sentiment classification, text categorization. So that is meaning if it's positive or negative. And what is the problem smoothing solves, right? What problems smoothing solves? So, text categorization. Well, what are some examples? Well, the most known probably is the inbox and spam mails. So I don't know if you remember that far back, but when the emails started flourishing on the internet and everybody got an email address, you started to get a lot of spams, and it just became a worse and worse problem. Nowadays, that problem is not that big anymore, and you wonder how the Google inbox actually does that. Well, it's something similar to what we are learning in this one. And another big category is product reviews. Are they positive or negative, right? Because maybe the positives, you're just happy about getting them, but the negative, you actually want to deal with them, right? You want to reach out to the people and say something about it, or write something on their reviews. Or you want to investigate products in general, other customer products, and you want to see what are the customers saying. Are they positive about it or are they negative about it? So those are great examples, and that's why you should master how to do it, and you'll be surprised how easy it is. But first thing first. So in the last one, we talked about how you can make a context-free grammar, but we also learned about, well, they are not really dynamic in the sense you need to make all the rules. And then we talked about trigrams or n-grams in general, and this kind of says something about the structure of the language. But do we always care about the structure of the language? Well, this is what the Bag of Words model is about. Well, it says we don't care about the structure in the sentence. We're only cared about what are the words in there. So this is a bag of words, right? The structure is not important, works well to classify actually. So this is what we're gonna do. For example, imagine this: I love this product. What is really saying something about it? It's love. Do we care if it's this love I product or product I love this? Do we care about that, if it's correctly or not? No, we care about the words. Some specific words have higher meaning than others. This product feels cheap. Again, it's a cheap that gives a meaning to this sentence. Whether it's structured, this product feels cheap, or this product definitely feels cheap, or some other variation, doesn't really matter. Cheap is the key thing in it. This is the best product ever. You get this, you get the idea, I think, right? So specific words have higher meaning in it, and it doesn't really matter in which order. If best is the first word or the last word or so on, it doesn't matter. Good. Now to something a bit more complex, but I promise you this looks really, really complex, but let's try to nail it down so we understand it without all this mathematics. So the naive Bayes classifier. Well, there's nothing naive here, right? We like that already, because often the theory is very complex, and if you do it 100% correctly, then trust me, things become complex. But it's often shown that actually just some approximations are actually way better and often easier to understand and easier to calculate. So this is what this is about. This is about a simple probabilistic classifier based on applying Bayes' theorem with strong naive independence assumption between the features. And if you want to read more in depth about it, I can advise you on Wikipedia. So what is Bayes' rule? Remember, this is hardcore mathematics, and we're going to simplify that. And if this looks like gibberish to you, don't worry about it. We'll get there with good examples down here. So describe the probability of an event based on prior knowledge or condition that might be related to the event. Again, if you want to go in depth, there's a wiki page. So what does that mean? It means that what is the probability of B given that A has happened? So how can you say that? Well, what is the probability, like in the reviews down there, what is the probability that I love this product is a positive review? What is that probability? Well, it says here that this is the probability of A given B times B divided by A. And that's, wow. Does that make sense? I have no idea. Yeah, it does. If you do all the mathematics behind it, of course it does. But what we really care about is if we see I love this product, is it positive or a negative one, right? So let's try to explain it here. So probability of positive is something. It is a value. There's a possibility that something is positive. For instance, maybe 50% of all the reviews are positive and 50% are negative, or some neutral maybe. Okay, so what is the probability if you see I love this product that is intentionally being a positive one? So that means actually the positive is seeing these words, I love this product, is it positive or not? So Bayes' rule implies that this equals to I love this product, giving its positive times positive divided by I love this product. So it means what is the probability we see I love this product over I love this product and it's positive times it's positive. So this is a lot of mathematics. Or what's often reduced to is this is proportional. We don't care about this division down here because it doesn't add anything. It just normalizes it, you might say. So it is I love this product given it's positive times it's positive. So the naive part, we use this to simplify that positive times I positive, love positive, this positive, product positive. So the naive approach is like, what is the probability of I love this product is positive? We've seen all these together. We'd simplify this to say, well, what is the probability of it's positive? That's this part here. But then we say the probability of I, giving that's positive, what is that? So given in all the reviews we have, when we saw how many times did I show up in a positive review? How many times did love show up in a positive review? How many times did this show up in a positive review? How many times did product show up in a positive review? And just multiply it together. So this is the naive part, because this probability up here, the theory says something different, right? This is not equal to this one down here, but we say it is good enough for us. So you see here, going from hardcore theory for this formula here, which we cannot calculate, we do some naive approaches, and here we already know how to calculate these measures down there, or we know in a moment. I'll show you how to do this. Good. So exactly down there. So number of positive, the probability of positive, the first one here, is given by the number of positive samples. That's the number of positive reviews divided by the total number of reviews, right? So if, let's say you have 100 reviews on your web page, 50 of them are good, then it's 50 divided by 100. So that's 50%, right? Love, positive. So number of positive samples with love, right? So let's say 10 of them had love in it, and the number of positive samples was 50. So that's mean 10 divided by 50, that is 1/5, that's 0.2, that's 20%. So love shows up 20% of the time in the positive samples. Okay, so let's try this one here, right? So if we have I love this product, you have, in this case, we assume 47% are positive samples and 53% are negative samples or reviews. And the word I shows up in positive 30% of the time, 20% in negative. This is just some numbers, right? And then we have love. It shows up 40% in the positive and 5% in the negative. So actually, sometimes I love to hate this product or something like that. So it might happen that love comes into this sentence, right? It is more likely in a negative apparently, and product is basically close to even, right? So if we want to calculate giving this one here that is positive, then you calculate all this here, you get some number, but you need to compare it to something. So what you do is you calculate for the negative, all of them, right? And multiply these and these, all these, multiply all these here. You get another value here. And you see, this is smaller than this one. So that means that the likelihood can be produced that I love this product is positive is this value here, divided by the sum of these two, which is 83.3%. And I love this is negative is 13.7%, right? So it's way more likely to be a positive one. So now we actually have the theory in order to use this naive approach. And again, this is a simplification that works really, really well. And the theory, the hardcore theory, says something different over here. And it's pretty much impossible to calculate easily, at least. Okay, perfect. So there are obviously some problems in this model here. What if a word never showed up? Let's say that product never showed up in the positive review. So this one would be 0. Then what happens? Well, if you multiply something by 0, it becomes 0. Yeah, exactly. So then the positive review would be 0, even though you have this love here, which is really, really high. But the negative would be this value here, different from 0. So this way, it actually would conclude that it's a negative review. So you see the problem that if a word never shows up. So there are some different approaches, and one is just adding a value to each value in the distribution of the data, right? So you add one. So you just say, even though we never saw this word, we just assume we saw it once. So you add one to everything, so you even it out. Yeah, that's what it says here. Laplace smoothing, adding one to each value in distribution. So are you ready? I hope so. So let's look at it. So we use pandas, the NLTK, CSV. We have actually a list set dict comprehension. So we need to set a set. If you don't know what a set is, I highly advise you to check that out. Then we have word tokenization and naive Bayes classifier. Okay, are you ready? Let's start some stuff here. Import the libraries. Okay, and then we need to read the data. Read CSV and What do we need to read? Sentiment. Perfect. And let's just look at the data, like always. And what do we have here? We have some text here. Not worth it, negative. Kind of cheap, negative. Really bad, negative. Didn't work the way we expected, negative. Overpriced for what you get, negative, right? There's probably some positive as well in this here, otherwise it wouldn't. Maybe they are ordered, so let's just look at the tail. Yeah, so much fun, great product, would recommend. My grandson loved it. My mother really enjoyed the gift. Okay, so you also see here there are not that many reviews here, so it's just a small data set, and it's just to exemplify it. Perfect. So what do we need? So what we need is we need to kind of extract the words from the sentence. So let's do that. So we make a helper function here, extract words, and we take document, maybe document, and then we return set, and I just write it like this. You can write it differently, word lower. This is exactly the same we did previously. Forward in NLTK word tokenize document, and then we say if any C is alpha for C in word, right? So here we make a helper function so we can extract the words as a set, and then actually we're gonna create all the words. So words is a set, and then we are for line in data text, which is all the text up there, to list colon. So we iterate over all the text here. So we take one line by line, and then we take words, and we update it with our new words. Extract words from a line. Okay, so this is basically what we want. Then we have words here. It's a set of words. You see, there are not that many words, but it's also fine because it's just a simple example. And then we want to make some features, right? So we need to figure out positive and negatives, right? So let's try to do that. So features will make sense in a moment. So for row in data is a rows. So what am I doing here? It is actually we take the row of data. I'll just show you here. Row here. So row here is the text and the label. So you can actually say here, we iterate over it here, text, row, label. So you see here we have, yeah, there are not that many reviews here. Not worth it, negative, kind of cheap, negative, and so forth down here, right? So this is the data from our set here. So it's just one way to iterate over it. If you didn't know, iteros. Okay, and then we take features and we append it to our list. And actually we do a tuple here, and then we have a dictionary. So this structure needs to be exactly as our model will have it. So it's a word in row text. So we take all the word in the text as a set. Forward in words. So we take all the words that we have in our words in it, and then we put a label here. So it's a row label. I'll just show you what it is in a moment there. Okay, perfect. So features. Let's just take the first one here. You'll see how it is. So it kind of takes the words and put a truth statement if it's in there, right? So worth it. So if you take the first row, it was consisted. Let's take the head here so we can see it here. So not worth it, right? So actually we have removed all the small words. Worth it, no, we haven't. So it is true here. And I don't know what else we have here. Worth it. Yeah, so worth it here. And so it puts false and true on all the words that are there, and then it says it's negative, right? So if it's this is just a structure of how it will take it. Good, perfect. And let's make the classifier and NLTK naive Bayes classifier and features and feature. We need to train it so we have the features here in our naive classifier. And then what? Let's try to input something, right? So now we can actually input something, and let's make a feature here, and then we actually take word for word in extract words from S. So we extract all the words from S, and then we do it for word in words, right? So we actually create the same structure we do up here, but we do it for the sentence we just inputted there. Okay, perfect. And then result, and we take classifier, and we have to have probability classify feature, and then it says for key in result. You need to know all this. I don't remember this by heart. Print, let's just say key result prop key. Okay, perfect. So this was great. Let's try this one. Boom. And what do we do here? We have a dictionary properties. Object has no attribute sample. It's samples again. So this was great. Perfect. And then you see that the probability of it being negative is 10%, and probability of being positive is 98%. So this is obviously a very, very simple model, but this was great. I mean, you need to use some of the words that are in our dictionary and in our model in order to do it, but you kind of get the idea here, right? So building up a model where you model something with positive and negative labels, and you list all the words you've seen, and you do it in this a bit annoying way. I think this is a very strange way to structure things, but that's how they do it. And you could have some module in between that does that for you, but never mind. This is how this library works, and it creates great results, this naive Bayes classifier. And actually we're going to use that in the next one, where we're actually going to use it on a classical training set of, I don't know, a lot of tweets, and then we should be able to see if a tweet is positive or negative. That's kind of the goal. So are you excited about that? Let's get ready for the project. See you in a moment. So, are you ready for an introduction for the project? So, it's going to be sentiment classifier. So, we will make a model to determine whether a tweet is positive or negative. So, this is a classical data set that is part of actually the NLTK toolkit. And so let's try to dive into it, and it's a lot of fun to work with. I've done it many years ago as well, and done it again, and let's try to do this. So first, import libraries, and a lot of libraries here, so don't worry about it. It's because we need a few things along the way. That's also why it's a bit cumbersome, because you also learn a bit about the tweets, because the tweets we used in the last one, it was kind of, they were not really dirty, and we removed a lot of things easily in a naive approach, and here we need to do it a bit better because we have more tweets. And then we need to download a couple of things. In theory, you could call download and just empty parentheses and just download everything, but I think it takes up a few gigabytes, terabytes, no, gigabytes it must be, yeah, gigabytes, not terabytes. So these are the ones you need, so you don't need to download everything. And then the tweets, you download them by this line here, the positive tweets, and do something similarly to negative tweets. So you just write negative tweets here. And notice there are tweets with no sentiment. That means they're not positive or negative, but we will ignore them in this project. And just check a few tweets just to see it looks perfect. And then tokenize the tweets, right? So get the tokenized tweet as follows. So you take corpus, tweet sample, tokenize positive tweets, and similar for negative tweets. And why tokenize? To make processing easier, check a few tweets tokenized. Okay, perfect. Then remove noise. So this is what I talked about. So in the last one we did in the lesson, we deal with it very simply, and the tweets were not that dirty. Perfect. So what do we need here? So we are going to use, we will look at things that do not add value to our analysis. So for instance, Twitter usernames. They should not add any sentiment, or if it's positive or negative, it should not be based on the username, and they start with this @ And hyperlinks, I mean, some hyperlinks probably have some positive and negative sentiment, but we're just going to ignore that. So we remove all lines starting with this. And then punctuation, special characters, we just remove it simply with this string punctuation. And numeric values, we are not going to use them. And we are going to remove stop words. Those are the small words. And you can do that by stop word English. To simplify, create a helper function isClean that implements everything up here. And then another helper function, clean tokens, which the function takes tokens as a list of tokens as input. Then return a list of tokens where isClean has been used or applied to filter. Also, let's lowercase, so use lower. Finally, use the list comprehension on the list of positive and negative tweets to where clean tokens is applied on each element. Normalize the data. Okay, so this is also a step we didn't really have in the other one. The process of converting word to its canonical form. So the idea is that I'm not a specialist in words, but you know, words can be in different forms, like ran, runs, running, but basically it's the same word, right? So you want to transform those words, right? You want to transform them. So you create a lemmatizer, word lemmatizer, and then you use lemmatize, word lemmatize, and you create a helper function for that. Create helper function lemmatize, word and tag, and convert tag n or v. If tag starts with nn and bb, it's else a. So you have three categories of word: noun, word, and adjective, I don't know, and return a lemmatizer, lemmatize, word, tag. And then you create a helper function, lemmatize tokens, and return a list where each element of word, tag, position of lemmatize word, tag. And use list comprehension to normalize positive and negative tweets with word lemmatize tokens. Okay, prepare the data model. Okay, so example of normalized tweets: hopeless, TMR, negative smiley. Should become hopeless, true, TMR, true, true, and then it's negative, right? So this is a similar format we did in the previous one. We just ignore all the false one. And hence the list of tweets, positive and negative, should be converted. Hint, use the dict comprehension inside a list comprehension. Perfect. Prepare training and test data. Make the dataset of the combined positive and negative datasets. Shuffle. Use shuffle. Let the training dataset be the first 7,000 entries, and the dataset test dataset the remaining entries, right? I don't remember how many tweets are there, but so here's the shuffle, by the way. We imported that. I don't know how big the dataset is, but I think it's 10,000 maybe. Perfect. Hint, train the model, classifier, naive Bayes classifier, train data, and the accuracy, count the accuracy by classifier test data. Perfect. And show the most informative features. So this is kind of interesting, right? So we didn't explore that in a lesson. So what words are actually classifying most if something is positive or negative? This is going to be interesting to see, actually. It's like, for instance, in our thing, we might think that love is a strong word, or hate, and something like that, right? Test the model. Try your model as follows. Define a tweet. This is fun and awesome. And prepare a data model. You do it like this, and then you classify the data. And a bonus. This is actually not part of it's just a bonus. A pre-trained sentiment intensity analyzer. It's called Waiter. here you see what it's for, and then you can just try it down here. It's just for you to enjoy. So are you ready for this? I hope so. It's going to be amazing. Remember, try it out yourself. If you don't figure it out, I mean, some of the steps are a bit remove noise and normalize data are probably a bit difficult. But don't worry about it if you don't manage. I will help you here in the next one. So please try it out yourself. See you in a moment. Did you figure it out? Did you manage it all? If you did, well, maybe you don't need to follow along here, but I'm happy that we can share this experience together. So let's try to do that. Let me know in the comments if something surprised you. Please let me know. I often get surprised by things, and it's really funny to hear what other people find surprising. So let's get started. So the first one, import libraries. I think we managed that one. Shift, enter to execute. And download sample tweets. Let's do that. I think everything should be up to date for me. That's why it's so fast. Otherwise, we'll start downloading, and don't worry about that. Good. So now we need to access the tweets. You might wonder, if you did this so far, you might wonder, why do we do this step? Well, it's just to show you, you can actually get the raw tweets like this. So positive, I think called positive tweets. Oh. Tweets here, and in the next one we actually do the same again, but again it's just, if you have never seen it, you probably want to see the raw thing first, right? So positive tweets, positive, it goes really well. Positive tweets. So let's look at the first one here. Follow Friday, blah blah blah, for being top engaged member in my community this week. And next one here. Hey James, how odd. Please call our contact center and it will be able to assist you. So who worked on all these tweets? Well, it's not me at least, but somebody took the time to check if something is positive or not. Everything in kids section IKEA is so cute. Shame I'm nearly 19 in 2 months. So this was estimated to be negative. I don't know if it is actually. Hopeless for TMR, negative smiley. So this was classified as a negative tweet. Right. And basically, we need to do the same once more here. We just need it tokenized now. So let's do that. Actually, an extra space here. This annoys me, so I always want to change it. Actually, there are many things that annoy me, but negative tweets. But let's not get into that right now. Negative tweets. Okay, so here we go. We read them now as tokenized positive tweets. So how does it look differently? Well, you see here now you have a list of lists, and the first item has tokenized them into a list. And the same for negative. Negative. If I could spell it, right? Hopeless for TMR, negative smiley. Perfect. Remove noise from data. So this is where something new comes into the picture. So it says to remove all these, starting with this, starting with that, special punctuation, is numeric, and stop words. Okay, and create a helper function for that, is clean. So let's do that, is clean. And what does it take? I guess it takes a word. We can just actually put it as a string. It's not necessary to do that, but sometimes it's good because now the function knows it's a string, so you can apply string methods to it. What do I mean? We'll see in a moment. So if word start with, so here you see now I can autocomplete with start with. If I didn't have this string here, it wouldn't be able to do it because it didn't know that it would be a string, right? And then we do return false. If, what is the next word? Start with HTTP or word start with HTTPS, return false. So what I'm doing is just making this helper function. It just says, is it clean, is it not, right? If word in string punctuation, return false. If word is numeric, return false. And if word in, is it called stop words? Yeah, we have it here. Return false. Oh, actually we need to, it says up there, words, words English. You need to apply that, okay? Otherwise we return true, right? So the key thing about this function is it takes a word, which is a string, and then it checks, does it start with this? We ignore it. That means false. And it start with this, ignore it. If it has a punctuation, ignore it. If it is numeric, ignore it. If it is English stop word, and then if it's English stop word, ignore it, right? So this is handy when we need to work on here. And then it actually says, create another helper function, clean tokens. So let's do that. Def clean tokens. And tokens is probably a list. I don't know if you need that actually right now. Let's see what we're going to do. So the function takes tokens, a list of tokens as input, then returns a list of token where is clean has been applied to filter. Also, let's lowercase it all. So hint, use lower, right? So it also sounds a bit about list comprehension here, right? So word lower. Is this correct? Yeah, for. Actually, we do tokens instead, right? So it's not word, it's a token maybe. Let's just keep it at word. For word in tokens, if, how is it called? Is clean word, right? So what am I doing here, right? So what am I doing? Yeah, exactly. So I take a tokens list. That's a list of tokens, right? Because we're having a list of list in a moment, right? So it takes and returns everything in lower, but only if it is clean. That means it is not one of these words here. So only if this is true. That means if any of these here, it will not add the word to the list. Okay, perfect. And then we take positive tweets. A lot of ease tweets cleaned, and we take clean tokens for tokens in positive tweets, and we should do the same for negative tweets here. So let's do that. Negative. Okay, so let's just check this one out. So okay, this one is still running here, so it takes a few seconds. It's not expensive. So right, remember this one here, right? Follow top engage member community week, right? So this is, you removed a lot of stuff and it's been in lowercase, right? So here again, negative tweet, remember that one actually. And hopeless TMR, so it keeps all of them, right? Perfect. Normalize the data. This is also new to our things we are doing, so let's try to do that. The process of converting a word into canonical form, right? So without normalization, runs, and running would be treated as different words. We don't want that. So create a lemmatizer of word net lemmatizer and use a lemmatize word net lemmatize. Okay, perfect. So let's do that and create a helper function, lemmatize, helper function, lemmatize, def lemmatize, and it takes a word and a tag because we need to transform them, because what it does, it returns these capital N and VBs and a lot of other things which we are going to ignore. So if tag starts with, right, so tag here is actually a string, and now we cannot, the key thing is to use these thing here, because then I can autocomplete here, right? So tag starts with, right? Now I can autocomplete. That's really nice. If it starts with, then it is a N, and if tags start with, it is VB, then pass V, O, elif, else, A, as it says here, right? Perfect. And then we return lemmatizer, and lemmatize, and we do word and like that. Okay, perfect. This is what we're doing, and perfect. And create a helper function lemmatize tokens and tokens list here. Def, perfect. And I want you to do return a list where each element of word tag inputs tag of lemmatized word tag. Okay, perfect. So return a list here, and lemmatize word tag, and for word tag in post tag tokens. And you wonder about pos tags here, and is something we imported here. Perfect. Returns that, and then we do the same again. Positive tweets normalized. That's difficult. And what do? We do lemmatize tokens, and we do tokens for tokens in positive tweets cleaned, and then we do the similar thing for negative tweets here. Negative. Perfect. So it takes a few seconds here, and again, right, we use it's really nice to use these how's it called, list comprehensions. You see, you have, when you have list of lists, right, so you have two helper functions to make it easier for you to read it, read the functions as they're doing. Perfect. So let's actually just check here. Follow Top Engaged Community Week. Probably, I don't know if actually Top Engaged members. So members became members, right? And Community Week. Yeah, perfect. And I don't know if anything changed in this one. Hopeless, TMR, I think that's the same, right? Okay, but basically it transforms words into the normal form. Okay, example of normalized tweet. Okay, here we have it. Should become this one here. Hence, the list of tweets, positive and negative, should be converted. Hint, use dict comprehension and list comprehension. Wow, that is amazing. Okay, so positive data set, and it should be a list, and it should be tuples, list of tuples, and then we have a dictionary, and then we need all this thing here, right? So token true for token in tokens, and then we added positive. And what do we do in this list comprehension here? For tokens in positive tweet normalized. Okay, that's a long one. So, and then we do negative here, and negative here, and negative here. Okay, perfect. So what do we have here in positive data set here? Let's take the first one here. It is, now we have these words here, and it's a positive one, right? Just formatted it similarly as the other one, right? And And here we have this one is negative, right? So we have that these words are in there. So now it is prepared for training. Perfect. So we need to make one data set. Data set is equal to positive data set plus negative data set here. So that's a full data set. And then we have the train data set. Should we hold DS for data set? It doesn't say anything. Okay, we need to shuffle it, right? So data, actually we call shuffle on data set here because we need to shuffle it. And then we have a train data set to be data set of the first 7,000 here, and test data set of the data set here from 7,000 and forward here. Perfect. So now we have randomized them, and we have something for training and something for testing, like we always do. And then we're getting closer here. So we need to make a classifier here, and then we need to classify accuracy, right, on the training data, right? So we make a classifier by the train data, and then we actually use this classifier on test data to see how accurate it is. And okay, so actually we called it differently. And I didn't see that. Okay, so 99.6% accuracy. That's pretty good, right? Awesome. You might get a bit different because there's some randomness in it here. Don't worry about it. So this is actually some of the funniest part. It is what is the words that actually say the most of the sentiment of a sentence. So actually, maybe this is not a surprise when you see it, but the positive smiley says it has a negative to positive ratio of this one here, right? That means the negative smiley is way more likely. It happens 2,000 times more than the positive tweets, right? And this one here, the positive smiley, it is also a high ratio between it, right? And sad, bam, followers, community, welcome times 15. So that means it's most likely a negative tweet that has times 15 in it, right? And sick, also negative, 12 to 1. So isn't that amazing? This is actually fun. Okay, so maybe not surprising that the smileys are actually doing the most impact on the sentiment. Well, funny. So test the model. So let's try that. Let's take this tweet here. And then we create the tweet dictionary here. And then we classify this one here. And what does it look like? It looks like positive, right? So this is fun and awesome. And it tokenizes it as here. You can just look at what's happening here, right? We had this helper function here, so that's pretty good. And then we can just classify based on that. Good. And in the bonus here, you can just say, okay, there's a pre-trained model here, and you can see the advantage of this one is actually it gives some percentages of what it is. So this is fun and awesome. It actually has negative 0 probability, neutral 28, and positive 71, right? So this is pretty awesome. And this model here, it's probably if you just want to make some small project where you don't want to do it on specific data, it is available for you. But basically the recipe here is also you can use this recipe that is given in this project here to do it on your own data set, right? So if you have an enormous large data set of positive and negatives or something, you can follow this guideline here and create it on your own. It's actually a lot of fun. I've done that myself on actually I wanted to figure out or if people were more positive and negative about Python versus other programming languages, and just to see how that was classified. That was a lot of fun. Okay, so I hope you enjoyed this one, and the project actually gives you, as I said, the guidelines to how to do this on your own with your own data sets. And if you like that, please let me know in the comments there. In the next one, we're going to look at how do you actually extract information or information retrieval of something. It's going to be amazing, and Please remember to subscribe, like, and all that kind of thing. Spread the word about this channel. I'm happy to be growing, and I appreciate every single person putting a like down there. So thank you so much so far. See you in the next one. Bye-bye. Information retrieval. Well, what is that? Well, let me ask you a question. How does Google extract what is unique or what makes this document aware of what content is it? What's special about this document? How does it find relevant information? Well, this is about information retrieval, and we're going to dive into that. How to find this, what makes this document unique, right? Okay, if you're new to this series, this is machine learning with Python. It's a 15-part series where we have a lot of notebooks, a lot of projects we're making together, and it's been really awesome so far. So if you're new to this, well, there's a link down in the description. There you can get started and all the content. So let's get started. Let's jump to Jupyter Notebook and let's get started. Okay, so here we are, information retrieval. The goal of the lesson is to learn what is information retrieval, the topic modeling of documents, and how to use term frequency and understand the limitations. Implement term frequency by inverse document frequency. This is amazing, I promise you. This is gonna burn your mind. It's gonna be amazing. So let's think about what is information retrieval. Okay, the task of finding relevant documents in response to a user query, right? So this is Google, right? You Google something, and how does it figure out what is relevant for you? I mean, web search engines use the most are the most visible information retrieval applications, but you can also look here on Wikipedia if you want to read a bit more about it. Topic modeling. So models for discovering a topic for a set of documents. So the idea is you will think of a list of documents or a set of documents where you want to provide us with method to organize, understand, and summarize large collection of textual information, right? So this is topic modeling, can be described as a method of finding a group of words that best represent this information. And this is not as easy as you think, but in the end, you will think, wow, that's amazing. Okay, so approach one. So there will be two approaches, right? Term frequency. Term frequency. The number of times a term occurs in a document is called a term frequency. You can read about it on Wikipedia. And it's often denoted TF-TD, where the number of times a term occurred in a document D, right? So term, the term, it could be the word the, for instance, not an, it occurs pretty many times in English speaking documents. So that will be a term frequency. There are other ways to define term frequency. See Wikipedia if you want. So the library used here, it's NLTK, OS, math. The math is in the second part. We're going to use list comprehension and dict comprehension, sorted to sort stuff, and lambda functions again. So if you are new to these things, please dive into it before you start. But let's get started together. So import OS and so on. So the first thing we want to do here is actually we want to read some information or documents that we need. So we're going to read Sherlock Holmes files again. So let's do that. So let's call our corpus here. We'll use that in a moment, but let's start with for file name in OS listdir, right? Listdir, and we take files Holmes here. Good. And for open, and then we need, remember, how was it? We need to take the path again here. Files Holmes, sorry, I sometimes pronounce it as it is spelled because I'm not really good at spelling. It's okay. We all have our weaknesses. So the first thing we want to do is actually just read the content. So let's do that. So content, and content is read the content, and we're gonna actually tokenize it immediately to fast forward. We've done this already. If you want to do it in multiple steps, it's often advised, but let's just do it here where we lower the words here for word in NLTK word tokenizer, word tokenize f read. We read all the content. if word is alpha, right? Perfect. So if I do this, obviously we have an invalid syntax. File name, open file, file name as f. What's wrong with that? What's wrong with that? Okay, so it says for here. It should be with there. Sorry about that. Okay, so here we go. And now in content, so let's content has the last file we read here, right? So we didn't use content in here. So let's immediately start to use that, and we do a frequency analysis here, and we do that by a dictionary here, and we do it word by content, and we do a count word in our count content for word in set content. So what am I doing here? I take the frequency, I count the number of occurrences this word occurs in the content, and I take the set of the content because basically the set only takes each word once, so you don't go over the same words again and again. Actually, it doesn't matter because it's a dictionary, so we'll just overwrite the originally written there, but it will be maybe a bit faster. Corpus, file name, and frick, right? So here we have it. So it reads and it does all this. It takes a few seconds, I guess. Corpus, and we have the file names here. So we have in file name, we should have the last file name here, right? So let's just use that one here, corpus and file name. And what we have here is like a long list of word frequencies in it, okay? And we have that for each file name. So that's our corpus. So we have frequency count of each of the words for each file here. And now we want to figure out what words are most common in them, right? So for file name in corpus, we can do that. It's a dictionary of it. Corpus, what do we want to do? File name. And we do here, we take sorted because we want to sort them. Corpus, file name, items, and then we want to do it on key. And here's a lambda function because we only want to do it on, we want to sort it on the frequencies, right? And reverse true because we want it in reverse order. We want the higher in the beginning, right? So what do we have now? Now we have all the frequency, all the words. So let's just demonstrate what that looks like. So for file name in corpus, print, we print the file name here. And then we take for word score, we can call it, in corpus file name, and we take, what do we take? We take the 5 first, and then we print. We do here, we do, what do? We do the word, and then we have the score here. So what do we get here? We get all the text. So here we see the problem, right? So the text here are identified with term frequency, right? And then we get all the small words, the, and, of, a, I, and you can see these are pretty much identical in all the text. And this demonstrates the problem with term frequency, right? But then you might think, yeah, then we can remove all the stop words, all the small words, all the common words, right? And do the same again. But it actually shows out that this is a pretty difficult approach of doing it. So this is a problem of the stop word. function word, right? Words that have little meaning on their own, right? So examples are am, by, do, this, which. And so as a student's exercise, I'd advise you try to remove all this, and you can use this stop words list here and remove them from here, but you still come in the conclusion that actually the words that are most likely are often common words. So it's not really going to say anything about the text here. So how does Google do it, right? So how do they do that? They find what's relevant in a text. Well, here we have it. Approach 2. Amazing. Approach 2, TF-IDF. What is that? TF-IDF is a numerical statistic that is intended to reflect how important a word is in a document. This is what we're looking for, right? So how important is a word in a document comparing to a collection, a corpus, right? So what was this? TF, term frequency, IDF, inverse document frequency. Okay, so we have term frequency and inverse document frequency. Term frequency we just did above there. So what is inverse document frequency? Well, it's a measure of how common or rare a word is across documents, our corpus, right? So IDF of TD, D is all the documents. So it's a logarithm of n, and n is the total number of documents. So it's the size of n, and then it is the count of documents where the term is. So number of documents containing the term, right? So this is the inverse document frequency. Wow, who made this up? It doesn't matter. This is the formula we're going to use. So TF-IDF, well, it's going to rank. It will make a ranking of words that are most important in a document by multiplying term frequency by inverse document frequency. So we're going to do examples here, and then in actually the project, which is going to be amazing. So we have 2 documents here. So simplify. We have a document. This is the sample of the day. And we have that this is another sample of the day, right? So these text here are quite similar, but there's a difference, right? There's another in this one, and there's actually a difference on there appears double as much in this one here, but let's see how it affects this. So this is just to see how the documents are. This is the documents. So what are we going to do now? We're going to calculate the term frequency, and just to be honest, let's just do it simply here, and in the project we're going to do it a bit more nice, but for our purposes here this is fine. So word, what are we trying to figure out? We are trying to figure out how many times a word is there. So let's just do it doc1 here. It is count word, and what do we do here? We take it from word for word in set of document 1. How many times does the term frequency appear in document 1? And we do the same here for document 2. So let's do that. And we change this to 2 and 2. So what do we have here? We have term frequency 1 here. We have the term frequency of the words right here. So the only difference is that we have the twice here, and in the other one we have another, and the only ones here, right? So let's try to do these calculations here. So let's just do the term here, and let's start with another, because we know that one should be unique to one of the documents. That's kind of the case here, right? So let's say the IDS. Let's see the formula again here. So we need to calculate the total number of documents. We have 2 documents, and let's look at the number of documents containing the term, right? So we need to iterate over the terms there. Good. So what we're doing is we sum over how often the term in doc for doc in, what do we call it? We call it corpus, right? So we're calculating how many times it appeared in that one, and then we actually want to say, well, what's the term frequency of document 1 of this one here? And we have the term frequency, and then we take the term here, or actually right here we don't have a full set, but yeah, it's okay. We're not gonna do anything here, but we don't have the full set here, but we'll do it a bit differently in the other one. And then you have the IDS here, which we calculated above, and that's the term frequency of that. So another, okay, so that was document 1. Of course, this is what I said, we don't have that in the first one. So what can we do in order to avoid this one here? Well, get term, and then we say 0 instead, right? Because if it doesn't appear, then we just return 0, right? But if we take document 2 instead here, so the term frequency of this one in document 2 here, we will have 1, because this one actually appears only in this document here. And what about the? It appears in both documents, right? But we see it's more likely in document 1 actually, because it's double appearing, while it only appears 1 in that one. But I actually forgot to multiply by the EDS on this one here. Perfect. So this doesn't make any difference in this case here, but I just forgot about it here. Perfect. Let's just put the another here again, just to see that this actually becomes 2 instead of the 1 there. Okay, so now you have an idea of that this can actually extract information. For instance, here we see that another is only in this document here, so this must be an important word for that one. That's the philosophy behind it, right? And the is appearing in all the documents, but it is more appearing in the first document than in the second document. Okay, so in the project we're gonna do something similar on a bigger scale with this inverse document frequency, just to see how it works. This is just demonstrating the idea. The idea is to extract what words are important or specific to this document, and you're going to see why in a moment. So are you excited? Let's get ready for the project. Are you ready for the project? So let's see what you're supposed to do, and afterwards we'll do it together. So information retrieval, right? So we want to calculate the TF-IDF of the corpus files homes. So the idea is here that in the end of this project here, you should kind of get an idea of what is unique to one of each of these stories. It's going to be exciting, right? So the first one, import the libraries, then read the corpus. We use this list directory again here, and then we add them to the corpus file name. And then we tokenize the content. So we do it more step by step here. We use for each file name assigned to corpus file name, be the list of word in lower and word in word tokenize of the content. And if of file name, if word is alpha, right? So this is exactly what we did there, right? So use list comprehension and is alpha. Get words. So we take words is equal to set, and then we update all the words with the content and apply update on, because if you're not familiar with it, set uses update to update it. Calculate term frequency, so we do that, create an empty dictionary dict called TF and iterate over the file names, and for each file name we add the term word frequency and use the dict comprehension in words. Good. And calculate the inverse document frequency. So create a dictionary IDF and iterate word in words. For each word, calculate the number of documents word is in the corpus. Hint, frequency word in corpus file name for file name in corpus. And then we update IDF word to be the logarithm of number of documents divided by the calculated frequency. Calculated the TF IDF. Create a dictionary TF IDF and iterate over the file name in corpus. For each file name, calculate the TF IDF for each word and add it to its pairs word TF IDF. And use list comprehension, yada, yada, yada. Perfect. Sort the values. This is what we did, right? So we use iterate over the file name in corpus. And for each file name, sort the values of TF IDF by second item in reverse order. That is, we use sorted and we use a key here. Perfect. Print the top 5 words. So this is actually where it becomes interesting, right? Because now, remember what we did first? We just took the term frequency and it was like the, I, this, and so on. Now, what is it going to print? Is it going to tell us something interesting about the story, or is it going to be something that is identical for all of them? Well, hopefully not. And you should try it now, and let's see how it goes, and then we do it together afterwards. See you in a moment. How did it go? Did you manage? I hope so. Let me know in the comments, and let's try to do it together now. Okay, perfect. So the first step here, did you manage? I hope so. At least if you follow along, it should be Shift Enter. And then we need to read all the corpuses here, right? So read all the Sherlock Holmes text from files Holmes, create a dictionary dict called corpus. So let's do that. Corpus, a dictionary, right? There you go. And use, so for OS list here, and we do files Holmes. There you go. I'm a bit sleepy here, right? So for file name in this one, right? This is how you do it. Perfect. And for each file name, open the file with open, and then we need to remember, we need this one here, files, Holmes, and then we take file name as F. Perfect. For each file name, read the content added to corpus, right? So corpus file name equals to F read. Perfect. Awesome. So this is the first step of that. So now for each corpus, we have all the content. Tokenize the content, right? So let's do that. So for file name in corpus, we just override it, file name equals 2, and then we do word lower, right? We need to, yeah, it says so. And for word in word tokenize of the how's it called, corpus file name, if word is alpha. Perfect. I think that's it. Perfect. So now we have tokenized all the data, right? So now we have here in the corpus, we have all the words tokenized. Okay, perfect. Get all the words. So how do you do that? Create a set words. We need all the words, right? Set. And for each file name, for file name in corpus, what do we need? We need to update the set of words. So how do you do that? We take words, update, and how do you do it? We just take corpus file name, right? So because it's a set, when you update it, even though the words are multiple times, it doesn't really matter. Perfect. Calculate the term frequency, okay? So create a dictionary called term frequency. Oh, here we go. Term frequency, and iterate over the file names. So for file name in corpus, good. For each file name, add tf file name, and what should we do? With the word frequency. Hint, use tick comprehension, word. And what do we do? And we take the corpus file name, and we take count word for word in words. Okay, perfect. This probably takes a few seconds, because what we're doing here is actually we take for each corpus file name, we take and count each word for all the words in words, right? The list of words are all the words available. So some of these frequencies will be 0, but remember we needed that, or that's one way to do it. Perfect. Good. Calculate the inverse document frequency. Wow. Create an empty dictionary IDF. Perfect. Iterate over word in words. So for word in words, that's all our words. For each word, calculate the number of documents word is in the corpus, right? So hint, use frequency here. sum word of words in corpus. So this is basically the sum of word in corpus for file name in corpus, right? So we count how many times it appears, right? And then we update IDF word to be the number of documents, or the logarithm. Do we have a math logarithm? Log here. Good. Length of corpus divided by the frequency here. Some people like here. Perfect. So this also probably takes a few seconds because we iterate over each single word now here in this one here. And then we go through all the corpuses and check if the word is inside the corpus, and then we calculate the IDF, inverse frequency document, inverse document frequency, not inverse frequency document. Perfect. Calculate the TF-IDF. TF-IDF, create a dictionary. Perfect. TF-IDF, iterate over file names. So for file name in corpus. Perfect. For each file name, calculate the TF-IDF for each word and add it as pairs word TF-IDF. Okay, so TF-IDF for file name. What do we want here? So we need a list of words. So it says word, comma, TF. Oh, actually, I have the formula here, right? So why do I list it all there? Okay, so let's just delete this and enter this one here. Perfect. And this goes a bit faster because now it's only for file names, and for word and words, for words, it's apparently faster. Okay, so sort the values. So iterate over file names for file name in corpus. For each file name, sort the values TF-IDF by the second. Okay, so TF-IDF file name is equal to sorted. And what do we sort? We sort the TF-IDF of file name. And what do we sort it by? We sort it by key lambda x by x1, and then to reverse true. Okay, perfect. Print the top first words. So now it's really exciting, right? So for file name in corpus, let's try to do that. Print the file name, and then iterate over the first file elements of this one here. So what does it have? It has a term and score in TF-IDF file name, and we took the first 5 elements. Here we go, and then we print, and we print formatted here. And what do? We take the term and we take the score. So this is interesting. So is it just common words for all of them, or are they kind of unique? So this one, Roylott, Stoner, ventilator, stepfather, Stoke, this cottage, Monroe, Jack, Grant, Norbury, Claire. So you see, if you look down this list here, they're kind of unique, and it's what makes this document unique, right? Isn't that amazing? I must say. Wow, if you look at this list, this is amazing. So you kind of get an idea of what this makes this text unique in this corpus. That's amazing, and you have to admit that's amazing. Well, I hope you like this one, and please let me know in the comments if something was confusing or not. And please remember, if you liked it, subscribe and like. Yeah, you know that, a like button that's somewhere. And finally, this was the next lecture will be the last one, and we're gonna see something amazing. So when you work with words or text, how do you do that smart? How can you make some information? How can you represent words? Well, if you use the context around words, actually it shows up to be quite amazing. And actually, this is gonna tie together with what's called neural networks, deep neural networks. It's gonna be amazing, I promise you that. So see you in the next one. Bye-bye. Information extraction. What if you were given that Amazon was founded in 1992 and Facebook was founded in 2004? That was the input to the algorithm. Do you think it could figure out a way to find other companies' founding dates? Well, that's what we're going to explore. Also, how can you represent words based on the context as a vector? And is that useful? Will that give you something? And you will be surprised about that one. That is amazing. I promise you that. So if you're new to this series, this is a 15-part course of machine learning with Python. And this is unfortunately the last part. But if you're new to this, there's a link down below. You can download all the Jupyter notebooks and so forth. And I advise you to go to the first one and start all over because it's been an amazing journey together. So let's jump to Jupyter Notebook and let's get started. Information extraction. So what is that? Well, what is it? That's the first goal. And then extract knowledge from patterns. That's the second one. Then word representation. How do you represent words in a smart way? We'll do that. Skip-Garn architecture, and then to see how words relate to each other, to the others. And this is really surprising. Good. What is information extraction? Well, the task of automatically extracting structured information from unstructured or semi-structured machine-readable documents. That's it. That's amazing. So we will do it. So it's more easy to understand with examples. So extract knowledge from patterns. Given data knowledge that fit together, find patterns. So for example, I said Amazon 1992, Facebook 2004. If you were given only that kind of information, could you make a template? So for instance, say when company was founded in year, comma. This is simple but very powerful approach actually, and we're going to do it in a simple manner here, and so to demonstrate it, and you get the idea afterwards how it works. I think that's the best way to explain it. So what are we going to use? We're going to use pandas and then a new one, RE, regular expressions. If you're new to that, I advise you to read a bit about it so you understand what it is. This is what is used to find or create the templates. And then we're going to use CSV, read CSV, and this regular expression that I talked about. So in this one, actually, I'm going to cheat a bit because I don't think that the programming is especially learning very much from it. So let's just do it together with executing. So what I'm doing first is I import pandas and regular expressions, and then we read a CSV file with books. So, and then we convert it to a list, and basically what it has these two books here, and the book was 1984, and it was written by George Orwell, and then there was the book The Help, written by Catherine Stockett. So given that data, can you extract information or find some patterns, create some patterns, so you can get other books titles, book titles and authors? Well, so the idea here is I just take a random web page. It's called Penguin, this one here, and we read the corpus. And just to form it a bit differently, we just change new lines and tabs for space. Good. And now for this one here. So again, we could sit and program this together, but I don't think it adds value. So for the values, val1 and val1, that's the title and the author in book list. We only have two here. We print out what it is. And then for in range, we go over the corpus. It's one long string here. And we try to find in steps of 20, we take a pattern and check if val1 is in pattern and val2 is pattern. If it is, we'll print it, right? So this is pretty simple, straightforward code. And we'll see actually for this one here, we actually get this one here, this pattern here, and this pattern here, and this pattern here. And there's probably an overlay of that, right? You see this actually starts here, is the same here. so we actually see that this one here, author, goes here, and this is the same for this one here, the help. So you see here, somehow you get patterns on that. So you would have an algorithm automate these things and can we find patterns? And yes, we can. And so we see the prefix, which is common, is actually this / quote greater than. So this is the prefix of the titles. You see this comes in both of them. Then you have the title, then you have the middle. That means between here, we actually have this piece here. We have the same piece here. So we put that as a match here. And then after, we actually see that it has a description here. After. So this one ends here. And this one should have the same here. So you see that. So these are patterns. So it is a perfect, so these are making perfect matches. And then we make the regular expression on that. So that's it. And then we actually try to find all in the corpus. And this is, again, what is it doing? It makes a regular expression that takes a prefix, and then it takes anything of 50 up to 50 characters, and it should match the middle, and then the suffix, right? And we take prefix, so something that starts with this, and we have up to 50 characters, and then we have this middle here, and then up to 50 characters, and then it should have the suffix here. So everything that matches that, we will find all in the corpus. So what do we get? So the beautiful thing is, then suddenly we get a lot of information. War and Peace by Leo Tolstoy, and so forth down here. So this was based on creating simple patterns. You can extract information. Isn't that amazing? I mean, this is a great idea. I mean, it's very simple, but very powerful. That's surprising. And of course, you would make this more advanced. I just simplified this to show you a simple example of how this can be done. And yeah, it should demonstrate it. Good. Next subject here. One-hot representation. So the idea is, if we want to represent words, how can you do that? And we actually did that in one of them in the sentiment analysis. So represent word as a vector with a single 1 and the other values 0. We used true and false instead, right? But the problem is that if you have a whole dictionary of, I don't know how many words are there, let's just say your dictionary is full of 10,000 words, maybe 100,000 words, then each word will be represented by a long vector of 10,000 zeros and 1 somewhere. So representing a meaning of distributing across multiple values, right? So instead, you kind of make this distributed representation, right? So how do we define word as a vector? Well, the idea here is word is defined by words surrounded, right? So the context. So when a word shows up, you kind of look at what other words are surrounding it. So that's the context, right? So if you see one word here, and all the time you see this word appears, right? So this is words around it. So it's kind of saying, when you see this word, what words happen to show up around it? So then we have this word to vec here. So that's a model for generating vectors. So now we need to understand what it does. We're not going to do this programmingly, but this is just to get the idea, right? So a neural network, we know about those for predicting context words given in a target word. So given a word, that word shows up around in context. So example, we have the target word as input word here. And then we have a hidden layer, and then we have the context words right side here. So the weights from the input nodes, target words, of the hidden 5 layers give a representation. Hence, the word will be represented by a vector. So basically, the weights of the nodes here will represent the layer. So said differently, the number of nodes in this one here represent the dimension of the vectors, how big the dimension will be. So here it's 5, it's probably pretty small for a word, but it can be anything, right? And so on this side here, you would have the word that you're thinking about, and it has weights to all these hidden nodes. And over here you have the context words, which also have weights here, but we are using the weights on this side here to represent our vector. So the idea is as follows. Each input word will get weights to the hidden layers, right? So if we have a input word here, this one here, it will have weights to the layers. The hidden layer will be trained. So we train over here, and then each word will represent as the weights of the hidden layers, right? That's what I said. Intuition. If two words have similar context, they show up in the same place, then they must be similar, and they have a small distance from each other representations, right? What does that mean? Let's try it out. So programming nodes, we use NumPy, SciPy, SciPy probably, and cosine here. Perfect. So let's try to do this again. So here we have some already pre-trained words. So this is something that has been trained here, and it has the word representation of it. And again, I didn't find it useful to sit and program how to parse all that. All it does, it reads the words and adds the vectors to it. Good. So actually just in here, let's just see how one word could be represented. So we called it words, and I think A is in it. And you see it's just a vector. And how big is the dimension of that vector? I don't know. It has 100 dimensions, right? So each word is a representation of a vector of dimension 100. That is, each word has 100 numbers representing it. And then we make some helper functions here, right? So the first one is distance. And what distance does is it calculates the distance between two words. So what does that mean? Well, let's try something here. Distance. And we take a word. King. Oops. King. And word. Queen. 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 And string distances, oh, it's words here. So this has this distance. What does it mean? Well, basically that doesn't really tell us a lot, but if we took something different here, like Pope instead, we can see that the distance becomes greater, right? So it means that king shows, or queen shows up quite often next to king, while Pope shows up less often than to king, right? So this is a distance, right? This is just a measure of something. So is this useful? Well, wait a moment here, because closest words, now we can actually calculate what words are getting closest to something, right? So closest, or actually, yeah, let's do that. So closest words, and we take here words, king. We can just try that. What are the closest words to king? It's queen, prince, obviously king itself, and so forth. But let's try something interesting here. What if we take king minus words man and plus words woman, right? So we take the word king and we subtract man from it and apply woman to it. What will it print? It prints queen as the most likely word. So that's interesting. So you take king minus man and add woman to it, and it becomes queen. Isn't that amazing? Wow, I think so. Wow, that's amazing. So now we got an idea of how to represent words as vectors, and it actually showed out to be quite useful. I hope you enjoyed this part. Now we're going to do a project of this word2vec that we already introduced a little bit here, and it's going to be amazing, and we're going to explore something amazing things as well. So I hope you will enjoy it. So see you in a moment. Are you ready for the project? It's going to be amazing. So let's look at that. Create a word2vec model. So as always, it's a step manual here, or step through project. So first import libraries, then download stop words just to execute these. Then read the content and sentenize. So initially an empty list is called all sentences, and then for each file name in this one here, hint uses a list here, open the file and read the content and convert to lowercase and apply send tokenize on content. Use lower on content. Okay, perfect. And then we tokenize each sentence, and we applying this one here to result of all words. Hint use list comprehension. Remove all stop words. So stop words in English to filter all the words and words. Iterate over the length of all words, and each index use list comprehension. Remove special characters. Iterate over all words to remove words with special characters. It's like use is alpha. Install Gensim and Python 11stein. I don't know how to pronounce that actually. Let's execute these one here. Then we import another library, Gensim models. We do that. Import Word2Vec. Use Word2Vec in all words. Use mean words equals 2 to ignore all words total frequency, and find distances. So what are the distances between these two here? Try to run that and find the closest words. It's also kind of funny. So it shows what to do with there. So it's going to be amazing. I hope you will enjoy this last project here. It's going to be amazing. See you in a moment. This is it. Did you figure it out? Let me know in the comments. Let's try to do it together. So first of all, import the libraries. Let's do that. I just need to do this and then download the stop words. Let's do that. It's already done for me. And then we need to iterate over here, right? So initialize an empty list called all sentences. All sentences, an empty list here. Here we go. And then for each file name in OS list dir files homes, do this, open the file name with open, and then we do this again. Oh, we need this files homes and file name as f. What do we do? Open the file and read all the content. Content equals f read. There you go. And convert it to lowercase. We can just put it to lower here immediately. I think so. And open the file and read the content and convert it to lowercase and apply. And then on the content, use lower. So all sentences plus equals to NLTCO send tokenize on content. We could also put lower here actually. Maybe it's a bit easier to understand. Perfect. Awesome. And get all the words by applying a word tokenize on them and assign them to all words. All words, and we take NLTK. It says hint use word tokenization, world tokenize. And we take, what do we have? We have one list for all. We have all sentences there. So it's basically for send in all sentences. Perfect. Awesome. Let's just all words. Let's just say we take the first one here. And then we take the first 10 here. Perfect. The adventure of this. Yeah, okay. So this is the beginning of the story. It's the first one there. And we take the first 10 there. Perfect. Remove all stop words. So use stop words English to filter all the words in all words. Hint iterate over the length of all words. For each index, use a list comprehension. For I in range length all words. Okay. All words I equals to W for word in all words I. if y not in stop words, English. Okay, perfect. Here we go. It takes a few seconds here to run it. A few seconds, right? That's what I said. So maybe this was a bit fast here. So for W in all words, so it takes all the words for each one of them. And if W is not a stop words, then add it to there. Okay, perfect. Remove special characters, right? Iterate over all words. So let's do that. For I in range length of all words, we take all words I equals to V for V in all words I if Y is alpha. Perfect. Awesome. And it was not happy if W is alpha. String object has no attribute is alpha. Okay, I do this all the time. If you follow along, I think I've done this mistake before. Perfect. Okay, install these. They should be installed here. So I just requirement already. Perfect. And then we need to import this one. Perfect. And then what? Create a model. So model equals to word vec of all words. Mean count 2. Why do I have mean count? Well, if you look at the model here, it says here mean count is equal to 5, and we put it a bit down because we don't have this much content. Okay, so model distance between these. Try to run. This is quite close to each other, you would say. At least it seems it. So what does that mean? It means, so you have to have two measurements in order to see it, right? It means that when Holmes shows up, Watson shows up. Holmes actually also shows up with water, apparently. And not as much. So find the closest words. So we have words here, apparently. Implement the function closest words, def. Perfect. And then we need to calculate the distances of the words. And then we need the return the sorted distances. Okay, so let's do that. Then we figure out what the closest words are, and let's just take Holmes. So friend, actually I'm kind of surprised that you don't have Watson up there. Friend, back, mouse, Connell, hand, quiet, word, first time, without, come, eyes, hands, upon. Interesting. Well, anyhow, it's been kind of funny, this journey here. So this one here was working a bit with word-to-vec model, where you actually create your own model here. So you make a corpus of all the words, you prepare the data. So this is probably what you do. This is not probably this is what you do when you work with language or text like this. You need to prepare it and massage it and so on. Well, anyhow, I hope you found this project nice. So let me know in the comments below here. And finally, it's been an amazing journey with you. It was really nice to meet you, and I hope you enjoyed it. So if you did, please like and subscribe, and please tell people about this. I mean, this is free content. Everybody can use it. So I really enjoyed it. And also the feedback I get from people, I love it. It feeds me. And please, if you have any great ideas that I should do, please let me know, because I love to get ideas of what to work on next. So this has been a long but fruitful journey together, and see you in the future. Thank you.